the two-body problem. Now, why singularities? Because for some reason, for 50-some years, people have been trying to show that there are singularities inside black holes. In that same 50-odd years, there's never actually been a proof. So there's got to be a reason for this. And what I'm going to say is the reason is there are no singularities, except possibly in Schwarzschild when everything is spherically symmetric. Now, the first thing I better do is give a bit of a picture of the Kerr solution. This has got the inner and outer horizons.
No, excuse me, we don't see your slides. Are you sharing the screen?
Sorry, I changed the slide then. Did it work?
We don't see your slides. If you have problem with sharing, why don't you send us the slides? Then we will show for you.
Oh, if you don't see, you're not seeing the slides.
No.
This I've got my. Can you see? You can't see this. Jesus Christ.
No, just send us the slides. We will show it for you, please.
Yes, you can send your slides to me.
Okay.
I'm the chairperson of this session.
Okay.
I sent your email half an hour ago.
Okay, I'll try and do that. Why aren't they showing? Now, I'm doing my best. Okay, I'll just. What the Christ's sake? I'm doing that. I'll have it there in a moment. Here we go. Reply. Paste. Here they come. Okay, I just sent them to Yefei.
Okay. Yeah, I received your slides.
Sorry, have you got them?
Yes.
I sent them. Good.
Okay.
Okay. If you get slide one up, and then go straight to slide two.
Can you see my screen?
Ah, great. Yes, it's on the screen. Big.
Yes. So when you
Yeah.
are you going when you change the slides, please say next.
Please,
You see, when you want to change the slide, say next.
next. Okay,
Okay, let's start it.
try next.
No. No, no，这是我写的，是你写的，但不是你 slides 的。是的呀。
It was a PDF I sent you.
Yeah.
Ah, great. There, that's good. All right, now, here's the standard picture of the Kerr black hole with the inner and outer horizon. The area or the region in between those two, I like to call the event shell, because it's more like a shell than a surface. Now, inside Kerr, there is this singularity. You've got to remember there is no physical meaning to this singularity, this circular ring. Just like in Newton's theory, where the force due to a spherical body is m/r², that doesn't mean that at r = 0, the force is infinite. It just means there's matter there. So we can forget everything inside that inner region, because inside that inner region, there's going to be matter of some form or other, which I'll talk about later. Next slide, please. Okay. The problem with the question of singularities for the last 50 odd years is that nobody has actually proved that a singularity exists inside a black hole. What they've generally proved is that either a singularity exists or there's some light ray whose affine parameter is finite in length. Now, it has been claimed that this is a terrible thing, and that if there's a light ray of affine length somewhere, there's a singularity. What I'm going to show is that in the Kerr solution, there are light rays whose affine parameter is finite. They are not of infinite length. All this means is that the affine parameter is not a very good indicator of whether a curve is infinite or not. Next slide, please. Okay, there are three usual coordinate systems for the Kerr solution. The one that most people use is the Boyer-Lindquist form. Why I mention Achilles Papapetrou there is he is actually the person who showed that if you've got an actually symmetric, stationary, that's independent of time's solution of the Einstein equations, empty, then it can be put in this form of this Boyer-Lindquist type form whenever there's no singularity along the axis at infinity. And that's true of Kerr. So, and furthermore, in a beautiful paper, which I had a preprint of about the time I found my solution, in this paper, he showed that the transformation from the form that one has it in to start with to this Boyer-Lindquist form is quite trivial and just involves a bit of algebra rather than solving differential equations. Anyway, that's why Achilles Papapetrou's name is on here. it's time he got credit for this. Now, from the Boyer-Lindquist form, you can, using what Achilles-Papapetro showed, you can get to the Kerr-Schild forms by this simple transformation. I haven't integrated these two. What this means is that the new t is the integral of the old t plus this function of r. Now, this function of r is singular here, where delta equals 0. So if we go back to the Boyer-Lindquist form, delta is r squared minus 2mr plus a squared. So when delta equals 0, this metric is singular. There's a rho squared over delta. Basically, the coordinate system breaks down. Now, the roots of delta equals 0 are the two event horizons. That's one thing that is easy to pick out from the Boyer-Lindquist form, is where the event horizons are. They're where this delta is 0. Anyway, what this means is that when you integrate this, because of the singularity, the change in the time is actually infinite, either plus infinity or minus infinity, when delta is 0, i.e. at the event horizons. Now we can do this transformation, and I can't see all my slides, by the way. I can, there, I'm seeing a wee bit more now. There's another thing we can pick out of Boyer-Lindquist. If you notice, if you change the sign of t and phi, both, or dt and d phi, that's the only place the t and phi occur, then since this is squared, there's no change in the metric. There's no change in the metric here, and t and phi don't appear elsewhere. So the metric is invariant under this flipping of the time and phi. What this does is, if we knew where the principal null direction of that the Kerr-Schild metric was built on, if we knew where the ingoing one was in here, we could find the outgoing one just by a simple change in phi and t. So what this means in the end for us is that this transformation, I can either go one way to the original Kerr-Schild form with an ingoing null set of null rays going in through the event horizons, or I can go the other way to the outgoing null rays. So next, please. So that means that when I do that, there's just a few changes of sign in the metric. If I go from this rather nasty looking differential form here, which is actually flat space, that part, the first part before the 2mr over rho squared is flat space, that can be transformed to the form of dt squared dx squared plus dy squared plus dz squared. The other term, the squared term, is the square of what happens to be a light vector. Now, for those who don't know, the beauty of this form of the metric is that the determinant of it is independent of the mass, because this is a null vector, not only in the full metric, it happens to be a null vector in the background flat space. So that allows us to raised and lower indices very trivially here. If this is the covariant form of K, this is the contravariant form, and these are true in the background flat space or in the full metric. Okay, notice they're very similar. The only difference between the ingoing and the outgoing form of the null vectors is the change in sign. One is going in, one is going out, and A appears to change sign. Well, that's okay, because as you go, when you go from Boyer-Lindquist to Kerr, you have to do a spin of the whole coordinate system in order to straighten out the ingoing rays. Now, if you want to look at the outgoing rays, you have to do the opposite spin. So that's why there's a change in sign. Next, please. Okay, now, this is those are effectively the two sets of principal null vectors. Now, one of them is obviously obvious in the form that I originally gave the metric, because that's the principal null vector that was displayed in the coordinate system. What about the other? This isn't so obvious, except down the axis, because down the axis, since it's rotationally symmetric, neither principal null vector can have a component off the axis. So they both point down the axis at that point. Now that means that if I look at down the axis with d phi and d theta are 0, okay, just at the dt and dr part, then ds squared equals 0 gives me the two null vectors on the axis. This is just a trick that can be used there. So if I look at the roots of this has got a root dt plus dr also. So dr over dt equals -1 is the incoming geodesic. dr over dt equals this, so the r squared minus 2r plus a squared over the factor which has no zeros is the other one. This is negative between the two horizons. It's positive elsewhere. What that means is, on the outside, this vector can struggle its way out to infinity, traveling very slowly at the start, speeding up as it gets further out. Inside the horizon, both horizons, in the part that appears to have a singularity, again, this light ray can travel towards the inner horizon. It can travel, so you can have light rays going up and down the axis inside the inner horizon. Now, that actually says one thing. There's no trapped surface inside the inner horizon. So any talk about trapped surfaces and what they may imply doesn't tell us anything about what's going on inside this inner horizon. Okay, now that says, next please, that you can see that if you plot r dot against r for this outgoing null geodesic on the axis, if you notice it's positive here, positive in the left-hand segment, negative, then positive. Okay, what this means is that this on the inner, but on the event shell between the two horizons, this is doing its best to go out, but it can't, it's falling slowly in. It's asymptotic at both ends to the event horizons.
Open.
It's asymptotic at both ends there. Yes? The can I have the next slide, please? Okay. Ray-Shaduri's equation is what was being used by many people to prove there are singularities in various places. Ray-Shaduri's equation says that eventually, if you've got congruences with certain properties, the light rays will meet again at a singularity. The only trouble is,
Talk longer. Okay, we'll see.
I still online? The only trouble with this is Ray-Shaduri's equation fails if the null rays that it's talking about have not got infinite affine length. And since, as I said before, affine length is a very poor estimate of where a light ray is going, this theorem doesn't work in Kerr or anywhere else where one is trying to prove a singularity. There is actually no singularity theorem, either Roger Penrose's or Stephen Hawking's, which works to prove anything of interest, because they all require infinite affine length for light rays. And this breaks down in all the situations where we might get singularities. Next, please. Okay, now let's go back to the Kerr solution. Let's suppose you've got a neutron star, a rapidly spinning neutron star. The metric outside the neutron star is probably fairly well represented by the outside of the Kerr solution. Now, please don't mention singularities, because the neutron star has got its own internal structure. I don't know what that is, but it doesn't matter. Nobody is saying that a neutron star has got a singularity inside. Nobody's saying that the Earth has got a singularity inside just because Newton's theory would give a singularity if there wasn't matter present. Okay, the neutron star has got matter present, no singularity. Suppose we dribble neutrons or other whatever onto this and gradually increase its mass while keeping it spinning fast. What's going to happen? It's eventually going to reach a stage where there is not enough angular momentum inside this body to counteract the attractive forces, the Newtonian type attractive forces. So it is likely to collapse to a black hole. But it doesn't have to collapse very far before the angular momentum forces can counteract the gravitational forces, the other forces. So what I'm saying is, if this is a fast-moving neutron star, can we go back a slide or two, please? Well, it doesn't matter. What I'm saying is that inside the inner horizon, you have got a rapidly rotating neutron star, which, because the outside of it cannot be a light-like surface, it's got to be a space-like surface. Its outer boundary will not be at the event horizon, it will be inside. And it's as likely to be some R equals constant surface as anything else. Now, when does where does the singularity come in? I don't know, nor does anybody else. There's been 50-some years since I found my solution. And up to that time, there has been no theorem which says there's a singularity inside. Now, if you look more carefully at Roger's theorem and actually read it, what Roger says is either there's a singularity inside or there's a light ray of finite affine length. These light rays that Roger was talking about for the Kerr solution are basically a set of the second principal null directions, the slowly collapsing ones. If I take a trapped surface just inside the event horizon, the outer event horizon of Kerr, and I look at the principal null directions, these ones that are leaving that surface, but traveling very slowly. They're trying to point outwards, but they can't because everything points inwards on this trapped surface. If I look at those and I plot them in the only metric for Kerr that we've got that isn't either singular somewhere, have coordinate singularities at the event horizon, or talking about stuff that is supposed to have occurred back an infinite time before the Big Bang, which is a problem with a lot with the second Kerr-Schild coordinate system I put down. If we talk about outward falling Kerr, sorry, the inward going Kerr, then this set of null rays, the ones that Roger's talking about, all are asymptotic initially to the outward event horizon, but of course that's back before the Big Bang. Here we're talking about the actual formation of the black hole, just like with Schwarzschild. So you can forget it there. These null rays are falling in towards the inner horizon. They are asymptotic to it. They never reach it. Now, there are going to be people, and I've had them say this to me, that what about the maximal extension? You can extend this Kerr solution to a beautiful picture with 99 different blocks. Okay, the maximal extension. Well, the problem with all this is if let's suppose I stand on the North Pole or stand above the North Pole of this Kerr solution, and I start throwing rocks in. Now, I'll throw a rock in every time a new day appears for me. Okay, one rock a day. They will fall in a finite time, passing through both the horizon, the event shell, through the inner horizon, and will end up on the rotating neutron star inside. That, okay, because let's say I keep doing this, they will keep falling through and they will hit the event horizon at finite times in the Kerr-Schild formulation. Furthermore, because of the fact that this whole metric is independent of time, they will do it in a constant, they will do it, the time between their arrival on the inside will be a constant. So I can follow that. If I was living on the neutron star inside, I could watch these rocks falling time after time after time after time forever. And I'll tell you what, none of these rocks would fall into some magical other branch of Kerr. in some other universe. So, and they would all cross these infalling light rays that don't make it through the inner horizon. Inside the horizon, the inner one, between the apparent, this inner horizon and the surface of the neutron star, there's a region which is highly unstable, of course. There's no question about that. And there are going to be a number of talks given about this. But if I were alive on the surface of this neutron star, I'd have to be about a millionth of a millimeter in size to withstand the forces. But I could throw rocks upwards off the surface, which would approach the inner horizon and then fall back. I could even send light rays up towards the inner horizon. These light rays would fall back mostly, except for the ones which are actually the principal null direction. So things can happen in there, but they're very nasty. Next slide, please. I'm going to run out of time soon. I was going to talk about Einstein-Infeld-Hoffmann equations. Now, this 1938 paper by Einstein, Infeld, and Hoffmann was one of the most important papers in relativity. What they showed was that you could actually start to solve the two-body problem using these methods as long as things were slow moving. Now, there was a problem with their papers, and that was that what they showed in the first paper was that if you tried to solve the linear equations for the assuming very slow motion, then there were certain integrals which were zero. This integral here that I wrote down from their paper was comes from basically Stokes's theorem, used cleverly on the Einstein equations, these equations. Now, the trouble with this was they found that in order to solve the first order equations, they had to have the mass moving with zero acceleration. Then in the next order, they found that the Newtonian forces had to be zero. Well, obviously there was something wrong. They wanted the acceleration to equal the Newtonian forces. So they spent the next 20 years, or at least Infeld did. Einstein got out of it after a couple of years. They spent this 20 years trying to prove that they could do this. And finally, when I got started as a graduate student, Infeld had shown that one way to get around it was introducing dipole moments in every approximation order. Things had become a real mess. Now, I looked at these equations, and what I realized was that, first of all, there were more integrals that they had missed, which came from angular momentum, the conservation of angular momentum. They hadn't written down these, so they were never going to prove that they could solve their equations unless they satisfied the angular momentum equation. Next equation, please. Next slide, I mean. Okay, so what it came down to, you can read this for yourselves, was that you can't solve, you literally cannot solve the set of linear equations, phi mu nu equals lambda mu nu, in each order exactly. They cannot be solved. What you have to do is simultaneously solve for the mass equations and the accelerations and the spin equations. You can then get an approximate solution of these equations in each order if you do that. Okay, next slide, please. So the problem is you can't satisfy the coordinate conditions exactly simultaneously. One thing I did show back in 58 when I sorted this stuff out was that you could change the conditions from step to step, choosing whatever was convenient from the first order, second order, third order, etc. And in particular, what should have been done is that we should have started with the outgoing Kerr-Schildt black hole solutions, because these are exact linear, they're exact solutions of the linear equations. They give you a far better start than what was actually used, which was, something like the original Schwarzschild solution. Okay, so what I'm saying here, which slide am I up to? Is this the second last? What I'm saying here is that if the Kerr-Schildt form had been used as the first approximation in these approximation methods, it would have been, first of all, a hell of a lot better. See, the point is, if you start with the Kerr-Schildt form, all you ever get from then on out are corrections which involve not the m squared, but m prime squared. You never get any more self terms. They're always just cross terms. Well, next slide, please. Is there another one, or was that the last one? Okay. I think there's another slide in which I want to just say something about. Can we next, please? Or if not next, the previous. Okay, it was the previous, yes. Jose and Jorge et al. Showed that if you use a test body motion near a black hole, test body motion, that's what they used. They got results which were very close to those by numerical relativity with a tremendous amount of effort, and the efforts of the people who are using fast approximations and slow approximations. They actually got results which were practically identical. Now, why was this? I was there when they came up, when Jose produced his results, which only took a week or two, by the way. And I said at that time, it's because of the Kerr-Schildt form of the metric. So what I believe is that you can forget about all those massive calculations, use a Kerr-Schildt approximation, which is like what Jose used, except he started with the Boyer-Lindquist form, which is not so appropriate for this. So using that should give the templates for LIGO a hell of a lot easier and faster. So I better stop there because I've used up my time with screwing around with this, these slides and things. Finally, what I can say is forget the singularities. Anybody who thinks that there are singularities should provide a proof, or a proof that there are singularities inside black holes. Remember, Roger did not. He said either a singularity or something else. What I'm saying is it's the something else. And there is, in 50 odd years, no other proof. Thank you. I'll stop there.
Thanks. Thanks, Professor. So because we start this talk 8 minutes later, so we still have 2 minutes to take questions.
Okay. Good.
So you can raise your hand.
There is a question in Q&A.
Mathematics is a funny thing. You know, it gives clear-cut answers. Here we have what is more like a religion, in that people have been told for so long that there are singularities in black holes that they believe it, and nothing that people can say is going to stop their belief, because they know that somewhere there's a proof of that, only that hasn't been found, but somewhere there's a proof. I feel I should give a prize, say $1,000, to anybody who can actually prove there's a singularity inside black holes. Thank you. No more questions. There never were any questions.
Excuse me? Hello?
Hello, are we still there?
Yes. So my name
Now we can hear the next talk.
so my name is Julius Serbenta, and I don't know whether this was your response to this question I wrote in the Q&A related to exactly solving the geodesic deviation equation for Kerr black holes, because it can be
The interior.
Okay, well, for interior, either case, because we have Killing vectors and tensors, and this allows us to integrate these equations at least once. So I wonder whether the solution would bring a more compelling argument to this question.
Obviously, there are lots of solutions of the interior, and that's the whole point. I didn't mention it, but it is quite possible if you have, let's suppose you've got two almost Schwarzschild particles, very slowly spinning bodies of equal mass, equal small spin, collapsing together. Now, what are you going to get inside when an event horizon eventually forms? Okay, I am almost certain that what you're going to get inside is a region with two orbiting small spinning particles. They're not going to join together. They're going to stay spinning. However, they can't lose the orbital angular momentum, can't be sent to the outside because nothing can get out. So the orbital and angular momentum is not going to decrease. And so there's no reason why they shouldn't keep spinning forever. But that's sort of irrelevant. The point is that the outer horizon will form, the inner horizon will form, inside will be a big cavity with two small black holes orbiting each other. No singularity apart from the two slowly spinning black holes. So when you talk about finding an interior solution, there's an infinity of interior solutions possible. And that's where this whole business of the stability or lack of the inner horizon is so important. One believes that the black holes on the outside degenerate down to having only the two parameters, mass and angular momentum. What happens on the inside, though, is completely different. You could have a lot of quadrupole moment or anything else on the inside, and it's not going to radiate away.
Okay, thank you.
Okay. Due to we run out of time.
Okay. Okay. Well, onwards and upwards. Next talk.
Yeah.
I'm ready.
Yeah. Are
Yeah,
you ready? Can you?
Yeah, I'm ready. I'm going to share screen.
Yeah.
I'm looking for the PowerPoint right here. Share.
No.
Just a sec. Do you see it?
Yes, it works.
Can you see the? Okay. Yeah. I'm ready. If there's a connection problem, maybe give me 2 minutes to fix it. All right. Okay, I'm ready to begin. If everybody else is ready.
Yes, but we cannot see the full screen.
Okay, just a minute. Can you see it now?
Yes.
Full screen. I can begin, right? I can begin now. Okay, so yeah. So this is the title of my talk: The Irreducible Mass of Christodoulou, Ruffini, Hawking Mass Formula. Now, this talk is to celebrate the 50th anniversary of the discovery of the mass energy formula of a Kerr-Newman black hole in 1971 by introducing 3 new theorems in black hole physics. So first, congratulations to Dimitris Christodoulou and Remo Ruffini for their remarkable discovery of the irreducible mass of the black hole, one of the most important concepts in black hole physics. Now this year is also the 50th anniversary of the renormalization of Young-Mills theory in 1971. So congratulations to Gerard de 't Hooft and the late Martinus Veltman for their elucidation of the quantum structure of weak interactions, which is one of the great achievements of 20th century physics. Now here's the irreducible mass formula. On the left, we have the total mass m. On the right, we have the irreducible mass. Q is the electric charge and J is the angular momentum. Now, 50 years later, the irreducible mass has gained new significance besides energy extraction. It can also determine black hole dynamics and structure. To begin, we'd like to explain the definition of the black hole. The mathematical black hole has a singularity hidden by a horizon. However, neither singularity nor horizon has been observed. And compact objects like the one at the center of our galaxy are also called black holes in common usage, even though their nature is still unknown. This difference is emphasized by the 2020 Nobel Prize to Roger Penrose. The citation is for the discovery that black hole formation is a robust prediction of the general theory of relativity. And to Reinhard Genzel and Andrea Ghez, the citation is for the discovery of a supermassive compact object at the center of our galaxy. The term black hole is not mentioned. Now, between 1965 and 1985, several important theorems on classical black holes were discovered. They are known as the singularity theorem, area non-decrease theorem, uniqueness theorem, and positive energy theorem. Now, in recent years, 3 new theorems are found, which were previously unexplored in the Hawking era. They were discovered, developed by me based on quasi-local energy and angular momentum consideration. Remarkably, they all contain the irreducible mass. They are called the horizon mass theorem, external energy theorem, and moment of inertia theorem. Now, in part 1, we discussed the horizon mass theorem. The theorem can be stated like this. For all black holes, neutral, charged, or rotating, the horizon mass is always twice the irreducible mass observed at infinity. The horizon mass theorem is the final outcome of the quasi-local mass applied to black holes. Now, the meaning of quasi-local masses is this. The quasi-local energy is given in terms of the total mean curvature of a surface bounding a volume for a gravitational system in 4-dimensional space-time. The Brown and York expression from 1993 is shown here. It involves an integration over the surface curvature. Here, K is the curvature of the surface, and K0 is the curvature of a background surface, usually taken to be 0, and sigma is the metric on the surface. Now, applying this formula to the Schwarzschild black hole, we find the total energy contained in a sphere enclosing the black hole at the coordinate distance r is given by this formula here. Now here you notice a square root factor, which is the curvature in the Schwarzschild metric. Now at the horizon, the square root factor will vanish, and the result for the energy is very simple, and it simply gives twice the asymptotic mass of the Schwarzschild black hole. Now, so this is the first case of the horizon mass theorem. For a charged black hole, the total energy contained within a radius at coordinate r is shown by a similar formula. Again, you notice a square root factor, which is the curvature of the charged black hole space-time. Again, at the horizon of this charged black hole, the square root factor will disappear, and we have a simpler result. Now, the irreducible mass is the final mass of the black hole when its charge is neutralized by adding oppositely charged particles, extracting energy from the black hole. So the irreducible mass is shown by the bottom formula here. It involves the charge Q and the total mass M. Now, the horizon mass in this case is the mass contained within the horizon as seen by an observer at the horizon. It's given by this expression. And remarkably, when you compare this with the irreducible mass, it is simply twice the irreducible mass. And this means the horizon mass depends only on the energy of the black hole when it is neutral. So here we have the second case of the horizon mass theorem. Now, next we go to a slowly rotating black hole. The total energy now has only an approximate expression because the problem is very complicated. At the horizon, it is found that there's very little rotational energy. And this means the horizon mass is almost twice the irreducible mass, but not exactly. This work was done by Martinez in 1994. Now, for higher rotations, the calculation is extremely difficult and no useful expression can be found. So at this point, progress on quasi-local energy for rotation stopped because no analytic method or numerical evaluation could achieve an exact expression for the horizon mass. Now, a breakthrough occurred 10 years later when I explored this problem with the area concept. Now, it is known that the area of a Kerr black hole can be expressed in terms of the irreducible mass again. This was the work of Christodoulou and Ruffini. On the other hand, the area of the Schwarzschild black hole is given in terms of its asymptotic mass, as shown here. Now, the two can be related if we invoke Hawking's area non-decrease theorem. We see the area of a Kerr black hole is the same as the area of the final Schwarzschild black hole when rotational energy is extracted in a smooth and reversible process. And since the irreducible mass of the Kerr black hole is the Schwarzschild mass m, and since the horizon mass of the Schwarzschild black hole is proven to be 2m, therefore the horizon mass of the rotating black hole is twice the irreducible mass. Now, so this is an elegant proof. Now, we have therefore found all three cases for the horizon mass theorem. Now, so far the result is mathematical, but is this important to physics? Well, we have two processes to show that the horizon mass is absolutely important. First is the black hole collision using the example of first gravitational waves observed in 2015. Two black holes merged to form a final black hole, releasing gravitational wave energy. According to LIGO, the two black holes have masses of 36 solar mass units and 29 solar mass units. They form a final black hole of 62 solar mass units with 3 units left as gravitational wave energy. Now, if you look at this, this is energy conservation at infinity. Now, if you look at this process in detail, you find that there's something missing because the waves were produced very near the horizons of the two black holes. And they require a huge amount of energy to reach infinity. So where's the missing energy come from? So we can explain this with the horizon mass. By calculating the horizon mass for the two black holes, we found that one has a mass of 71 solar mass units. The second one has 57 solar mass units. The final black hole has a mass of 116 solar mass units. 3 units are for the observed gravitational waves. 3 units are the redshift energy, and the remaining 6 units are for other factors. Since we use round-off numbers here, and there were uncertainties in the determination of these masses by LIGO, and there's a further cosmological redshift, which requires energy. Now, the second process is none other than Hawking radiation. Black hole radiation is only possible if the horizon mass is greater than the asymptotic mass, because it takes an enormous amount of energy for a particle released near the horizon to reach infinity. And this energy comes from the black hole. Now, in part 2, we discuss black hole rotation. The external energy theorem can be stated here. The rotational energy and electrostatic energy of a general black hole exists completely outside the horizon. This is a direct consequence of the irreducible mass. By definition, the irreducible mass does not contain electrostatic or rotational energy. A rotating black hole does not contain rotational energy inside the horizon. Therefore, rotational energy exists outside. And similarly, an electrically charged black hole does not contain electrostatic energy inside. Therefore, electrostatic energy exists outside, like a metal conductor. Now, if we consider quantum particles, we see that quantum particles carrying electric charges and spins cannot exist inside the black hole. They can only stay outside or at the surface. Since all matter particles in nature are quantum particles, this makes the interior of the black hole completely hollow. Now, according to Tomonaga, every charged particle has a spin, and he observed that nature was not satisfied with a simple point charge, but required a charge with spin. Now, we can make this theorem more general by introducing the external energy paradigm, which states this: all energies of a black hole are external quantities. They include constituent mass, gravitational energy, electrostatic energy, magnetic energy, rotational energy, heat energy, and so on. Now we finish the second part. We go to part 3. This is about the extended structure of black holes. The moment of inertia theorem is shown here. A black hole with an angular momentum and an angular velocity has a moment of inertia. It is given by coefficient times the Kerr mass times the ergosphere radius squared. When the rotation stops, there's an irreducible moment of inertia, which is given by the irreducible mass times Schwarzschild radius squared. Now, the expression I equal to mr squared is the rotational equivalent of the formula E equal to mc squared. Now, the Kerr metric was discovered in 1963, and it ushered in a new epoch in general relativity and astrophysics. It is absolutely indispensable for the study of rotating black holes, and I believe that it deserves a Nobel Prize. The Kerr solution is shown here in physical quantities. This way we can easily read off the metric coefficients and apply to a particular problem. And this is what I do for the moment of inertia of the black hole. A puzzling question which was never asked was this: do black holes have moment of inertia? The definition of moment of inertia is always angular momentum compared to the angular velocity of a rotating body. Both these quantities are well defined in the Kerr metric, so we expect a definite result for this ratio. Now, if there's no rotation, both these quantities are zero. So we wonder what can happen here. Is there a result for the Schwarzschild case or not? So we calculate the angular velocity of the Kerr black hole at the event horizon. We obtain this rather formidable formula here. On the left side, we have the angular velocity omega. On the right side, we have the angular momentum J in 2 places and the total mass in 3 places. Altogether, there are 24 quantities here. In the end, they combine to give a single number, which is expressed in radians per second. Now, this is quite amazing. And this is an exact algebraic equation. Now, next, we rearrange the previous formula in a heroic way so that the angular momentum J is on the left and the angular velocity is on the right, and the remaining parts are the moment of inertia, is the moment of inertia of the Kerr black hole. The crucial step here is to be able to extract a radius factor, which is 2gm over c squared. Now here, the mass is the Kerr mass, including rotational energy. And this radius factor is actually the ergosphere radius from the Kerr metric. Now, so there's a numerator and a denominator. Now, the denominator involves the ergosphere radius, the angular velocity. They combine to give an ordinary velocity, and then divided by the speed of light, it becomes a number, dimensionless number. So the whole denominator just becomes a coefficient in this expression. And the numerator, we have the mass and the ergosphere radius. So the structure of the moment of inertia is a coefficient times a Kerr mass times the ergosphere radius squared. Now, when the rotation stops, we expect to have a Schwarzschild black hole. In this case, the angular momentum's angular velocity squared will become 0 first. The Kerr mass will become the Schwarzschild mass, and the ergosphere radius will become the Schwarzschild radius. So the moment of inertia of the Schwarzschild radius, Schwarzschild black hole, is irreducible mass times Schwarzschild radius squared. So the formula is very simple. I is equal to mr squared. So what we find here is that every black hole has a moment of inertia, including those that do not rotate. Now, since the Schwarzschild black hole does not have an axis of rotation, the center is the point of symmetry. And spherical symmetry requires all mass of a Schwarzschild black hole to be located at the Schwarzschild radius. So the black hole object is a hollow, massive shell, and singularity does not exist. So I have a physical reason for the non-existence of singularity. So the black hole is like a mechanical body. In conclusion, we see that these new theorems show that what is believed to be a black hole is a mechanical body with an extended structure. The mathematical black hole with a singularity was proved at a time when the moment of inertia was not known. This was 1965. And we believe that astrophysical black holes are likely to be horizonless, massive, compact objects from which light cannot escape. So this is the end of my presentation. And finally, I have a picture of Hawking and me in a conference in 1996. Thank you so much. Okay. Are there any questions? Professor Kerr? Okay, let me go back to.
Excuse me. I have remarked the following.
Yes, yes,
Yes, just to draw your attention to our talk,
yes.
parallel session thermodynamics about the same problem.
Okay,
The main result that you can derive the mass formula for horizon mass in some field theories, not pure gravity, Einstein Maxwell, and some generalization using Tonimatsu approach, which
all right.
can be found in citation in our talk. Thank you.
Okay, thank you. And Professor Kerr, can you hear me?
Yeah. Okay. So you want to have the black hole Schwarzschild replaced with a shell at the horizon. It's got a slight problem because everything that is moving near there is moving inwards at the speed of light, isn't it? I don't know. This, if you can do that, you could put anything at the center. You won't have to fit any boundary conditions or anything. And I think you'd have trouble fitting the boundary conditions of the outside of Schwarzschild with a shell at r equals 2m.
That seems right. That seems to be right, but the equation which I showed, they are exact. So how would you explain the presence of the moment of inertia then, if there's nothing at the horizon?
If I take a bunch of classical ideas and mix them with a bunch of non-classical ideas and definitions from general relativity and definitions from classical physics, I'm likely to end up in a mess and prove just about anything I want to prove. I don't know. It just and this is not just a problem with what you were saying here, but it's a problem in physics in general, in that a whole lot of ideas have been carried over from 19th century physics and attempted to be pushed onto onto universal size objects with general relativity rather than Newtonian physics.
Yeah.
So that's going to be a problem. It's a problem for me to understand what you've done.
Maybe, but so far the singularity theorem was proved with classical particles. And
no, there was never a singularity theorem. Sorry.
Yes, right.
Roger Penrose did not claim to prove the existence of a singularity. He claimed that either there's a singularity or there's a light ray of finite affine length inside the black hole. Or, and here's another one that I could mention, or the weak energy condition wasn't satisfied. Now, all these energy conditions are holdovers from 19th century physics. I have no idea what a classical approximation to a quantum mechanical universe should be, but I don't know whether this weak energy condition is anything but a desperate attempt to figure out something that can be used to prove theorems. just remember, if it hadn't been the weak energy condition, it would have been the strong energy condition or the left-sided energy condition or some other energy condition, whatever was needed to prove a theorem. So, for instance, with Schwarzschild, people say that you can't have a spherically symmetric body without a singularity, Schwarzschild. The trouble is that just because the angular momentum is at zero doesn't mean the body's spherically symmetric. It can be anything but spherically symmetric. It can have quadrupole moments. It can be what's the word? When everything is a real mess and bubbling away, and lots of things can be happening, in which case taking an average like these weak energy condition may be fairly meaningless. It is for me.
Okay.
Okay.
We certainly like to understand more.
Yeah. I'm sorry.
Right.
What is it when bodies are anyway, spherical symmetry doesn't solve the whole problem for bodies that aren't rotating.
Okay.
Okay. I think we should end this talk.
Okay, thank you.
Yeah. First,
Thank you for your talk.
can you share your screen? Yeah. Our next speaker is Lorenzo Amati. He will talk about the cosmology and multi-messenger physics with gamma bursts.
Yes, good morning or good afternoon. I will share my screen in a while.
Yeah.
Okay, you should see the presentation. So thank you very much. Many thanks to Remo, Gregory, Robert, and all the organizers for giving me the opportunity to talk to you about gamma ray burst and specifically their relevance for cosmology and multi-messenger astrophysics, which is still to be fully exploited. So for those of you who are not so expert of gamma ray bursts, most of you are aware, but just a very quick recap. Gamma ray bursts are huge flashes of X-ray and soft gamma ray radiations coming randomly from the sky, from random direction at random time with random like curves, so count rate as a function of time. You know, at these energies, we are counting photons. So these detectors basically are counters. So you count, there is a background like a seismograph, and then you have this, as you can see on the top left, these bursts. These were discovered in the second half of the 60s by military satellites. And then it was realized they were coming from space and not from the atmosphere, not from nuclear explosions, from nuclear bombs in the atmosphere. It took several decades before we could understand something of these outstanding phenomena. So the very impressive things here is that these are really outstanding phenomena occurring more or less once per day. At least they are detected once per day by low Earth orbiting satellites carrying on board these detectors. And for 30 years, we were not able to know the distance and so the luminosity, the radiated energy. So there were conjectures about the origin, the progenitors, the emission mechanism. But for 30 years, we were stuck with only basic information like the one on the top right, so that there are two main classes of gamma ray bursts, short ones lasting from a few tens of milliseconds up to a few seconds, and long ones which can last from a few seconds up to typical minutes. And then their direction in the sky, the direction distribution is isotropic, so they're actually coming from random directions. And then, as you can see on the bottom right, at the end of the 90s, thanks to the DepoSAC satellite and the efforts by many telescopes on the ground for following the localization, the first accurate localization provided by the DepoSAC satellite, it was possible to detect the so-called afterglow emission, so the fading multivalence emission following the burst in the X-gamma rays. The afterglow can instead detected from the X-rays down to the optical near infrared and the radio. And through absorption spectroscopy or direct imaging of the host galaxies of these events, it was possible to establish at the end that the distance scale is cosmological, as you can see. A long gamma ray bursts have been detected up to a redshift of more than 9, which means a few hundred million years after the Big Bang. And the radiated energy is huge. In the assumption of isotropic emissions, they can radiate more than 10 to the 54 erg in a few tens of seconds, which means more than all the energies that will be radiated by a star like the sun in all 10 billion years. So it's really, we're talking about the most extreme electromagnetic phenomena in the universe. The many efforts, observational and theoretical efforts going on also in the last 20 years, we came up with a basic standard scenario, even if, of course, the group by Remo and collaborators is developing a much more sophisticated scenario. This is the basic idea in the community, supported by several observations, that long gamma ray bursts are actually producing the core collapse of very massive peculiar stars that die where they were born. So they actually are located in star-forming regions within star-forming galaxies, whereas short gamma ray bursts are produced by neutron star onto star black hole mergers, and as was found and conjectured since many years, at least a fraction of them may be produced by neutron star black hole merging. So the merging of neutron star to star black hole systems. So why so much interest? Of course, gamma ray bursts are a phenomena, as said, so extreme that involve many fields of fundamental physics and astrophysics by themselves. Here I focus on their capabilities for cosmology and in perspective multi-messenger astrophysics. So of course these long gamma ray bursts that I said are detected up to the very early universe, as is sketched here. They can be originated up to the few hundred million years after the Big Bang, when the first stars and first galaxies were forming. And so we have with long gamma ray burst a tool, a cosmic beacon, that can pinpoint the explosions of the first stars, can illuminate, if you wish, the first primordial galaxies, and tell us not only their existence, the basic properties, but also the metallicity evolution, the neutral hydrogen evolution, and so tell us much about cosmic ionization, for instance. And also, furthermore, they could also be used, as there are many investigations using them as possible standardizable candles to be used for investigating the geometry and expansion rate of the universe. At the same time, as I mentioned, short gamma ray bursts, so the two main flavors of gamma ray bursts: long, much interest for cosmology; short, much interest for multi-messenger astrophysics, because as you know, of course, in 2017, there was this detection of the first gravitational wave from a neutron star merger by LIGO, and the simultaneous detection only 1.7 seconds after the gravitational wave signal of a short gamma ray burst detected by the Fermi Gamma Ray Burst Monitor in a direction, from a direction consistent with that of the gravitational wave. And as you can see on the right, on the bottom right, the detection of a near infrared counterpart, which was then found to be produced by the radioactive decay of the very heavy elements being formed after the merger, because in this very neutron-rich material, the radioactive decay of these elements producing near infrared emission and characteristic features. So let's start focusing on the use of long gamma ray bursts for cosmology, as already anticipated. Here, the idea is of exploiting the fact that they are so luminous and they emit most of their luminosity in the X and gamma rays that are poorly absorbed by the interstellar intergalactic medium, so they can be detected and are actually detected up to the very redshift. Again, you can see here on the right another sketch putting gamma ray burst in the cosmological context. And as you can see, they can be detected up to the so-called cosmic dawn, when we're talking about a few 100 million years or even a few tens million years after the Big Bang. So just at the end of the so-called dark ages, when all the neutral hydrogen was neutral, stars and galaxies still had to be formed. So instead, at this epoch, the first galaxy and stars start illuminating the neutral hydrogen, and the universe start to reionize the neutral hydrogen, starting the so-called cosmic ionization process. And as again, if I go to the next slide, of course, so you can see more in practice how impressive are the capabilities of long gamma ray bursts for these purposes. What you see on the bottom left is actually the direct image of a star exploding a few 100 million years after the Big Bang. So actually, there are nowadays a few very bright, very massive galaxies that have been detected by the Hubble Space Telescope Frontier Field, for instance, at this very, very high redshift. But these are only very bright galaxies, the tip of the iceberg of the bulk of the population of the primordial galaxies, and mostly through lensing. Instead, here with gamma ray burst, while catching the fading afterglow, as I mentioned, the electromagnetic, in this case, near infrared emission following the burst, we directly detect an object and the residual of the explosion of an object these very early epochs. So, for instance, if we simply could get a statistical sample of many tens of very redshift gamma ray burst, we could contribute substantially to the understanding of the evolution of the star formation rate up to the primordial universe. As you can see on the bottom right, this is the star formation rate evolution as inferred through many methods, and at redshift higher than 5 or 6, so the first billion years of the universe, where the understanding of the star formation rate evolution is fundamental, not only by itself to understand the formation and the population of first galaxies, but also because the first stars, the ultraviolet photons emitted from the first stars, are thought to be the main origin of the cosmic ionization. But this is still very much debated. So it is, of course, fundamental to know how the star formation rate evolves in the early universe. And as you can see, there is a lot of uncertainty if you consider the green points or even the shaded regions that are extrapolations from the very massive galaxies. There is a lot of uncertainty. Instead, if you consider the red points, this is what could be obtained with a sample of a few tens of gamma ray bursts at redshift higher than 6. So a huge improvement in the accuracy of the determination of star formation rate evolution. This is because, again, now this star formation rate evolution at redshift higher than 6, so first billion years of the universe, is inferred from the few very bright galaxies that are detected, and you have to make assumptions on the luminosity function of these very, very primordial galaxies that you actually don't know. Instead, with gamma ray burst, you can detect directly the exploding stars, but not only. If you have a look here at these 6 images, so on the top left, you see the fading after, as I mentioned, the residual of the explosion that is fading and disappears. So if you point a very sensitive telescope to the direction of the gamma ray burst, of this very redshift gamma ray burst, after this light is faded away, the afterglow fades away, you see nothing. These are images taken by the Hubble Space Telescope, so one of the most sensitive optical in facilities. You can see nothing. So we know that in these directions, at this redshift, there are 6 redshift galaxies, only because we were able to detect the gamma ray burst, to have an efficient follow-up, catch this fading emission, doing absorption spectroscopy of this fading emission with very sensitive telescope, and so establish the existence and the redshift and also the position of these galaxies. So this means that gamma ray bursts are providing us a unique tool, a unique mean for detecting, localizing, and making a census of the bulk of the primordial galaxies that are invisible. This means detecting invisible galaxies, galaxies that are below the detection threshold of the Hubble Space Telescope, of the VLT. And this will be true also in the future, of course, up to down to lower luminosity for the JWST, extremely large telescope, and so on. So the gamma ray burst providing a unique tool to unveil the bulk of the population of the primordial galaxies. But not only thanks to gamma ray burst, we know the existence, how many they are, where they are, and at what ratios they are, these galaxies. But if we can use and point to this direction before the light fades away, a sensitive, very sensitive telescope, we can do also absorption spectroscopy, as I mentioned, which tells us not only the redshift, but also the properties of these invisible galaxies, the metallicity, as you can see, the neutral hydrogen fraction through the Lyman alpha absorption, and also the properties of the intergalactic medium. So of these invisible galaxies that we would never detect without a gamma ray burst, not only we know the existence, how many they are, the distribution, but also the metallicity, the neutral hydrogen fraction, and the intergalactic medium around them. Of course, this is outstanding capabilities of long gamma ray burst, very well known by cosmologists. But the main issue here is that despite the many efforts, observational efforts by many facilities in the space and on ground, we are still stuck with only a few gamma ray bursts detected at Rashi 6. So only a few gamma ray bursts actually have been now detected in the first billion years of the universe. So this is, as I will show later, one of the main goals of all the future gamma ray burst missions that are being studied by the worldwide community. So put here a statistical sample of several tens of gamma ray bursts in the first billion years of the universe. On the other hand, as I said, short gamma ray bursts have been demonstrated, as was conjectured by many since many years, as one or the main electromagnetic counterpart of gravitational wave signals. This idea that gamma ray burst, a fraction at least of short gamma ray bursts, could be produced by the merging of neutron star binary system or neutron star black hole binary system was put forward since many years. There were several evidences, for instance, the location. So why, as I said, the long gamma ray bursts are usually located in high star forming rate galaxies and in high star forming region galaxies, in their galaxies, where you expect that these very massive stars are located. Instead, you expect that these systems, neutron star black hole systems, are very old instead, are in the outskirts of the galaxies and are not directly connected to any kind of particular galaxy. And this is what is actually found. But in 2017, we had this, the final proof, a gravitational wave detected by LIGO from neutron star merging system, and the short gamma ray burst associated to this event. As you can see, there is a 1.7 second delay between the gravitational wave signal and the short gamma ray burst. I will get back to this, but this is, of course, is telling us something. This event was at 40 megaparsec distance, and this is already telling us that the first direct demonstration, if you wish, that gravitational waves travel at the speed of light, or at least if there is a strong limit. This puts a strong upper limit to the difference between the two velocities. As I mentioned, in association to the gravitational wave signal, it was discovered not only the short gamma ray burst, but the other electromagnetic counterpart, the Kilo 9 emission. So this is on the bottom left. These are the light curve of this fading optical near infrared source in different filters. These are simply near infrared and optical filters. So this was a rising and then decaying source. And on the bottom right, you see the spectrum, the spectral evolution of this source, showing many lines. And as I show here, on the bottom right, these lines were actually the lines that are expected if this emission is produced by the radioactive decay of very heavy elements being produced after the merger, or during and after the merger, because of this very, very dense neutron-rich material through our processes. And this was supposed to be one of the main channel for producing these very heavy elements in the universe, and this also was demonstrated. So on the left here, you see simply a sketch on how this radiation is produced by or through the merging of two neutron stars, forming a black hole and accretion disk. There is then the launch or a supermassive, highly rotating neutron star, producing in any case a relativistic jet that produces the gamma ray burst, and also this wind, as you see, equatorial or polar, producing two-component emission in the near infrared that again is due to the mostly radioactive decay of these very heavy elements. So what can we do with this, putting together the gravitational wave and electromagnetic measurements for this kind of sources? Of course, we can get a lot of information and do many studies on the relativistic jet formation, a question of state of neutron stars, fundamental physics, again radioactive decay, so formation of very heavy elements in the universe, but also, as is shown on the bottom right, doing in turn also cosmology, multi-messenger cosmology, let's call it. Indeed, you know very well, as is shown on the left panel, there is this tension on the measurements of H0, with the CMB providing a lower value with respect to type 1a supernovae or other methods for the lower redshift universe. And of course, the idea here is that if you get again a statistical sample, in this case of gravitational wave signals with associated electromagnetic counterpart from which you can derive the redshift. So by modeling the gravitational wave signal, you get the distance of the source in a cosmologically independent way. And then you have the redshift from the electromagnetic counterpart. And so you can build the Hubble diagram, which is the distance as a function of the redshift. And you know that this relation depends on the cosmological model, on the Hubble constant, on omega m, omega lambda, if you use the standard lambda CDM scenario, or on the evolution of the dark energy, and so on, you know, of course, very well. With a few tens of these events, you could really assess the value of H0, or even study the evolution, as is shown on the right, of W0, if you assume a standard parameterization of the equation of state of dark energy. This is what was done, you see in red here, the Hubble constant as derived with only one measurement. So the only one simultaneous detection that we have up to date, as I discussed, the gravitational wave and gamma ray burst detected in August 17. So of it, only one event, you could already have this distribution of probability in the red line, peaking at around 70 for the Hubble constant. So in between the Planck and the lower redshift measurements. But then if you can get again several tens of these events in only 20 simultaneous detection between gravitational waves and electromagnetic counterparts, let's say GRB in this case, you could get this kind of constraint. So this is a kind of multi-messenger cosmology, very, very promising, of course. And this is just to mention that, of course, this link between gamma ray burst and gravitational wave sources is not only restricted to short, so to neutron star mergers, so to short gamma ray burst, because there are other possible sources much more unlikely, much more difficult to detect by the current and near future gravitational wave detectors. But in any case, it is worth to mention that also core collapse of very massive stars, if the core collapse is asymmetric, can produce gravitational waves, for instance, or other extreme sources like soft gamma ray repeaters, which are produced actually by these magnetars, so hugely magnetized neutron stars. If actually these soft gamma rays emissions, bursts of soft gamma rays are produced by quakes or instabilities of these neutron stars, which could also produce weak gravitational wave signal. So, given, as I mentioned at the beginning, these high potentialities of gamma ray bursts for the cosmology, for the multi-messenger astrophysics, of course, cosmology and multi-messenger astrophysics are the main goals of next generation missions and instrumentation for the study of gamma ray burst, mostly for the end of this decade or for the next decade. Also aiming at providing a a huge synergy with all the very large facilities that are being built in the electromagnetic domain. As you may know, of course, we are in a golden era on the point of view of observational facilities. We are building or studying, already developing extremely large facilities in the optical, extremely large telescope, ELT, the TMT, in the radio, SKA, in the very high energy domain, so SKA or Athena, mission by the European Space Agency in the X-rays. And of course, the same is true for gravitational wave and neutrino detectors. This is the path for the next, the end of this decade and the next decade. We expect further advanced second generation gravitational wave detectors in the second half of this decade. So extending the horizon, the cosmic horizon at which we can detect, for instance, in gravitational waves, neutron star, black hole mergers, up to a few hundreds of megaparsec. But there will be then a huge step forward with the third generation of gravitational wave detectors. This is for the second half of the 30s, very likely. And in this case, we will be able, as is shown here on the right, we will be capable to detect this kind of gravitational wave signals up to very high redshift. So this is the concept of this future gamma ray burst mission. I make the example of the TSIUS, Transit Energy Scanner Universe Surveyor. So this is an acronym, which was an European mission that has been studied by the European Space Agency, led by Italy. So I use this case, but this is the same concept that is adopted by all the other groups in the USA, in Japan, and so on. As I said, next generation missions for GRB aiming at full exploiting gamma ray bursts for cosmology and multi-messenger astrophysics and providing these great synergies with future observing facilities. So the concept here is, first of all, to extend the capabilities of current gamma ray burst monitor by extending the energy band down to the soft X-rays, up to the gamma rays, so to be and of course improving the sensitivity of this monitor, so to improve substantially the capability of detecting and localizing very high redshift, still keeping a very high sensitivity to short gamma ray burst and any kind of gamma ray burst. This is only a part of what we need, because of course, first of all, we need to detect many more high redshift gamma ray bursts, but we also need to know that these are gamma ray bursts at high redshift. How do we know? We know, of course, a measurement in the near infrared. As I mentioned at the beginning, it is thanks to the detection, localization, and spectroscopy of the near infrared afterglow, so the decaying light after the gamma ray burst, that we can identify the redshift, the host galaxy, and also characterize this host galaxy through absorption spectroscopy, the metallicity, the neutral hydrogen fraction, and so on. And to improve substantially, so to reduce the inefficiency, the current inefficiency in the process leading to the detection, localization, and redshift measurement of this near infrared afterglow that you need. The idea, of course, is to put directly a near infrared telescope on board and give the spacecraft the capability of autonomously following, so pointing in a few tens of seconds or a few minutes, this telescope in the direction of the gamma ray burst provided by the monitors. So the combination of this instrumentation and mission profile would allow this use and these missions, as is shown in this diagram, where you see the spectral peak energy, so the spectral hardness, versus the peak flux, so the intensity, the brightness of the gamma ray burst. So this combination of instrumentation and mission profile will allow this mission to detect any kind of gamma ray burst. So if you have a look on the bottom left side of the diagram, here there is the bulk of the population, of course, of high redshift gamma ray burst, which are expected to be soft and weak because they are redshifted, of course. And their emission is beyond the capability of current detectors like the Fermi Gamma Ray Burst Monitor, the red dots here, and still keep the sensitivity to detect harder, so spectrally harder gamma ray bursts like the short ones for multi-messenger astrophysics. So to give an idea, a mission like TSIUS for the high redshift gamma ray burst, and so the cosmology with gamma ray burst, the early universe with gamma ray burst. This is the current scenario in terms of, on the left, luminosity versus redshift, and on the right, in a cosmic context. This is the situation. So as I mentioned before, despite the many efforts of many facilities from space and ground, in the last more than 20 years, we could detect only a few gamma ray bursts at 3006, the first billion year of the universe. With TSIUS, you could instead get this kind of results. So improve substantially. These are the red dots, are the gamma ray bursts detected, localized, and identified as high redshift gamma ray burst by the spacecraft itself. So clearly a huge leap. You will get several tens of gamma ray bursts at 3006 and hundreds of gamma ray bursts at redshift, lower redshift, with not only the redshift measurement, but also a full multi-wavelength characterization, which is fundamental for understanding the physics, the mission, and the progenitors of these gamma ray bursts. At the same time, such a combination of instrumentation mission profile will allow TSIUS or similar mission to detect, localize, and characterize and measure the redshift of most classes of transients in the high energy sky. So in particular, as I mentioned before, those short gamma ray bursts, but also other possible X-ray emission associated to neutron star black hole mergers, which are up to now and will be also in the next years the bulk of the gravitational wave emitters that can be detected by interferometers on the ground. So just to give you an idea, this is again the observational scenario that we get in 2017 with again the detection of the gravitational wave from neutron star system, the short gamma ray burst, the kilonova emissions that in the near infrared that I already. And this again took the efforts of many facilities from space, from ground, many hours or days to take all this amazing observational scenario. And a machine like TSIUS could do all of it by itself, detect and localize the short gamma ray burst, detect and localize the possible, the kilonova emission or the near infrared afterglow of the burst, and also detect and localize the possible soft X-ray emission that some models expect to be produced after the neutron star merger if very massive, fast rotating neutron star and highly magnetized neutron star is left as a remnant of the merger. So really impressive capability. Here I would like to stress, as it can be seen here in this scenario, that as was demonstrated for this unique event, GRB 170817, that this very nearby gamma ray burst, short gamma ray burst associated to these neutron star mergers that are within the horizon of a few hundred megaparsecs of the current and near future gravitational wave detectors are most likely detected off axis. So this emission is most likely collimated into a jet, and usually we detect short gamma ray burst at threshold higher than 0.05, 0.1, not so nearby like 40 megaparsec. And if you are so nearby, you likely detect them very off axis. You see the gamma ray burst and their luminosity very low. You see them very soft because of course of Doppler relativistic Doppler effects. So the capability instead of these future missions, as I mentioned, will extend the detection of gamma ray bursts down to the soft X-rays, will unveil also the bulk of the population of local short gamma ray bursts associated to gravitational wave emitters seen off axis, which are again, these capabilities are beyond the current capabilities of current gamma ray burst detectors. And thanks to these capabilities, we expect several tens or hundreds of electromagnetic counterparts, short gamma ray burst, X-ray transients associated to gravitational wave signals detected, for instance, by third generation gravitational wave detectors like the Einstein telescope or Cosmic Explorer. So this is a sketch, a summary of what we can do with these multi-messenger observations. Again, here mostly focused on neutron star black hole mergers. This is a summary of what I already outlined. So I can go on, and this again sketches the huge synergies that TSIUS or similar missions will have with all the large, extremely large facilities of the future in the electromagnetic domain, but also in the gravitational wave. I mentioned also neutrino detectors because gamma ray bursts are also expected to be a major source of neutrino, even if this is still to be demonstrated. It has recently been demonstrated that they emit also very high energy, so TV photons, but of course, for neutrino, there is still no evidence. It is important to stress that all these facilities have gamma ray burst, high energy transients, multi-messenger astrophysics, cosmology with gamma ray burst in their core program, in their core science. So a machine like Theseus or similar mission is of course needed by these facilities to fully exploit their scientific capabilities. I would take the last couple of minutes to briefly go through what I would call as additional capabilities or assets of gamma ray burst. So what I described to you up to now are the commonly agreed impressive capabilities, or at least some of them, of gamma ray burst. But as I mentioned, gamma ray bursts are interesting, very interesting and very important phenomenon in modern cosmology and astrophysics and fundamental physics under several aspects. These are additional aspects. As I mentioned at the beginning, we can do cosmology with gamma ray burst not only with respect to the investigating the early universe, but also for investigating the cosmological parameters, evolution of dark energy, cosmological models, because there is a lot of activity in investigating correlations between, as I show here, spectral properties and the luminosity or radiated energy that are very promising for standardizing gamma ray burst in a way similar to what is done for type 1a supernovae, for instance, where for type 1a supernovae, it is exploited the so-called Phillips relation, so the relation between the peak magnitude in the light curve of this type 1a supernovae and the decay time of the light curve. Here, we exploit the correlation between the spectral peak energy, as you can see on the left, the typical spectra in new spectra of gamma ray burst have a peak, show a peak, and the photon energy at which there is this peak is called the spectral peak energy, which correlates, as you can see on the right, very well with the radiated energy and peak luminosity. So we can exploit this correlation, and actually this has already been done. There are many works, and this is a pioneeristic work that we did in 2008. What we did was to check if this correlation was dependent on cosmology. So if you could extract cosmological information from this correlation, and what we did was to fit the correlation as a function of the value of omega m by assuming a flat lambda CDM scenario. We varied the value of omega m from 0 to 1, with which is computed the luminosity distance used to compute the isotropic related energy. So we created a correlation for each, a data set for each value of omega m, fit the correlation with a likelihood that is well suited for this kind of study, and evaluated the goodness of fit, the likelihood, or the chi-square. And what we found is that the goodness of fit, or the chi-square, or the minus log likelihood, as a function of omega m, has a nice parabolic shape, minimizing at omega m 0.3. So this means that if we didn't know anything about type 1a supernovae, but simply we assume a flat universe, as is direct evidence from only the CMB alone, and the main expectation, of course, from
how are we with time?
Okay, I'm concluding. So from inflationary model, from gamma ray burst, we have independent evidence that if the universe is flat, omega m is around 0.3, so the universe is actually accelerating. And this is a very powerful demonstration. Then you can do much more. You can have contours in the omega m omega lambda plane, as you can see on the bottom right, which are, this is the pink contour from gamma ray burst, already competitive with the contours from other probes. And this is what you will get, or we are getting, for the estimate of omega m as a function of the number of gamma ray bursts that we are building in the sample. So increasing the measurements will increase this potentiality of gamma ray bursts. So to conclude, I just mentioned that gamma ray bursts, because they emit over a huge energy band, so several decades in photon energy, they release a huge amount of photons, and the detectors of gamma ray bursts, at least a part of them, have a timing resolution of the orders of microseconds. You can use, as is shown here in this formula that you know very well, you can use gamma ray bursts to test the Lorentz invariance and hence to test quantum gravity or to put limits on the quantum gravity mass, because of course you exploit the delay between low energy and high energy photons. This was done, for instance, in this case of this very bright short gamma ray burst. Of course, here you can see in this table the limits, the quantum gravity mass with respect to the Planck mass that have been derived from these studies on gamma ray burst.
How are we doing with time? How long have you been doing?
Okay, this is just to mention. So as I mentioned before, another important clue for fundamental physics from gamma ray burst is the delay between gravitational signal and electromagnetic signal, as I mentioned before. So this 1.7 seconds already put a very, very stringent limit on a possible deviation between the two velocities. So it is a direct confirmation that gravitational waves travel at the speed of light. And this is my conclusion. So sorry for being a bit long. If you want more information on the Theseus missions, it is one of these future missions exploiting gamma ray burst for cosmology and multidimensional astrophysics. You can go to the website or read the many articles on the archive. So thank you very much. Sorry for being long. Thank you very much again. This is all.
Well, I've been following this talk, and in a certain sense, the Roman used to say errare humanum est, but perseverare, etc. By the way, I think the Theseus mission, I hope you have explained, was not selected by ESA. And I think your presentation is a very extensive and detailed presentation, which was the soul of the Theseus mission. And I think you and everybody else should take care of rethinking the validity of this, and we will keep this as a document of what your thought for Theseus was. But let me explain one point. We are doing all the effort possible to look at the data and the theoretical interpretation. Yesterday, we had an entire session about the problem of H0, which was really profoundly interesting and not asking the help of solving the problem with 1708-17. Moreover, we are having a session still on the different interpretation of 1708-17. And all these pictures and things that you presented as given, we make a special effort in this MG16 to distinguish between things which are given and things which are the thing of interpretation, and focus on experiment that can clarify this situation, which is clearly sort of messy. Anyway, we will keep this presentation as an example of what a mission like Theseus was grounded, the mission. I thank you very much, Lorenzo, for this presentation, but I think we have to go on to the following speech.
Thank you very much, Remo, for the comments, of course. Thank you.
Okay, so we have no time to take questions. So our next to speak is Alina Pian. She's talking about the supernova of gamma ray burst 1901-14, please.
Yeah, okay, thank you very much, EFA. I will share my screen now. Let me try and see if I can succeed doing that. Yes.
Yeah, I can see you.
Okay. Okay, so thank you very much. So this talk will represent an overview of the state of the art of gamma ray burst supernova connection. And the final part of the talk will expand on this latest very interesting gamma ray burst. So gamma ray burst as already introduced by Lorenzo, so I will not dwell into this. They are very brief flashes of soft gamma rays that were completely, whose origin and nature was completely unknown until 1997. We now know that gamma ray bursts come in two flavors depending on duration and accordingly spectral hardness. So there is a majority of long duration, softer spectra gamma ray bursts, which we know are associated with supernovae, and a minority of short, hard gamma ray bursts, which we have learned recently are associated with binary neutron star mergers. And this talk will expand on will be concerned with the long gamma ray bursts. Here you see a view graph of isotropic gamma ray emission, the isotropic energy of gamma ray bursts, both short and long, as a function of redshift. The shaded orange area indicates roughly the subset of gamma ray bursts we will be concerned with, meaning long gamma ray bursts at low redshifts, because those are the gamma ray bursts that where the supernova can be studied best, most accurately. So all of the examples I will show are actually at redshifts, definitely redshifts less than 1. So the prototype of gamma ray burst supernova is this object, supernova 98 BW, discovered on 25 April 1998. The characteristic of this supernova is that it's a so-called stripped envelope core collapse supernovae. Supernovae come in two flavors: thermonuclear supernovae, type 1, so-called type 1a, and core collapse supernovae, which are the final fate of very massive stars. So gamma ray burst, we know today that gamma ray burst supernovae are all core collapse supernovae, very much stripped envelope, meaning without hydrogen, without helium, and in their envelope, in their spectrum. So what's special about 98 BW? Well, first of all, it's very luminous. I will show in a minute its luminosity compared to other supernovae, but especially the very important thing is that it's very highly energetic. You know that kinetic energy in supernova of any type is around 1 beta, 10 to the 51 ergs. Well, 98 BW was 5, 10 to the 52 ergs, so 50 times more energetic than the average core collapse supernova. And you see the spectra reveal this very peculiar characteristic, this highly energetic character. As you see here in the bottom right is the spectrum of 98 BW at maximum light is compared with maximum light spectra of other core collapse supernovae. Basically, the spectra look physically the same, meaning the atomic species in all of these spectra are the same, just the absorption lines in 98 BW are so much broader than in other supernovae, and therefore blended, meaning the velocities, the photospheric velocities are very high. They generate blue shifts. The high photospheric velocity since the material is coming towards you, is generating a blue shift in the lines and a broadening of the line profile. And we are the lines we are observing here, just to give an idea of the atomic species, is lines of silicon, calcium, iron, definitely not the Balmer line. We don't see hydrogen and we don't see helium lines in this type of supernova associated with gamma ray bursts. This is what I was mentioning before. The lines, these are spectral series of this prototypical gamma ray burst supernova, 98 BW, from immediately after the explosion to late times. If you follow the same line, for example, silicon 2 at 6300 and angstrom 55, you see that the same line is seen very much blue shifted at early times, and as time goes by, the blue shift decreases, and accordingly, you can derive a photospheric velocity, as you see here on the right. And here are the photospheric velocities of many gamma ray burst supernovae. The top 5, the red ones, are gamma ray burst supernovae, compared with photospheric velocities of other core collapse supernovae as a function of time. And as you can see, gamma ray burst supernovae have higher velocities than any other core collapse supernovae, and these velocities at the beginning can reach astounding values that are higher than 10% of the velocity of light. So we are speaking of very extremely high velocities. Curiously, rather significant gamma ray burst supernova, represented here by the star, supernova 2013 DX, that one is not very extreme, and I will show it's quite luminous, it's quite prominent, but its velocity and therefore kinetic energy is not as high as the others. This is a comparison of luminosities. This is the 98 BW that I mentioned before, very luminous supernova, more than a magnitude, more luminous than other supernovae, than core collapse supernovae. And the only supernova here in this view graph that is not connected to a gamma ray burst is 1994I, here in turquoise in the bottom, and as you can see, it's a dwarf with respect to these powerful gamma ray burst supernovae. And here is a comparison, it's a bit more physical view graph, is a comparison of relevant physical quantities of these objects. On the left, you see the ejecta mass in various core collapse supernovae, including gamma ray burst supernovae, as a function of the kinetic energy. And as expected, predictably, gamma ray burst supernovae occupy the top right corner of this view graph, meaning they represent the higher energy, higher mass tail in the distribution of all core collapse supernovae. And here it's highlighted 2013 DX, for which the kinetic, that doesn't land in the same locus as the other gamma ray burst supernovae, and because of its kinetic energy. Otherwise, it's very similar. Its properties are similar to gamma ray burst supernovae. On the right, you see the nickel mass of these supernovae as a function of progenitor mass. We are speaking of, in general, in core collapse supernovae, we are speaking of progenitors higher than 8-10 solar masses. Well, gamma ray burst supernovae have progenitor masses that are at least 30 solar masses. And the nickel mass is accordingly higher, namely these supernovae are more luminous than the average. There is a little note to be made about a special case that was detected some years ago, supernova 2008D, which is was seen as it's a core collapse supernova, was associated with an X-ray, with a high energy event, detected in X-rays, but not energetic enough to have the dignity of a gamma ray burst. It's let's call it an X-ray burst, an X-ray flash, whatever. Its energy is 10 to the 46 ergs, which, as you can see, compared to classical gamma ray bursts, 10 to the 46 is not even included in this view graph. It's too low in energy. So the energy of this event was definitely weak. It was associated with this supernova that you see here. There is the bolometric light curve in black compared to 98 BW, compared to other core collapse supernovae, gamma ray burst supernovae. It's quite weak. It's relatively less luminous. The interesting thing about the supernova was the spectra. There is as you can see here, there is an initial peak. If you look at the light curve, the black points, there's an initial peak around 4 or 5 days. And then there is a second much more luminous peak, which is the classical one typical of all supernovae. So the first peak is probably what is called a shock breakout emission. It's the emission that comes out in all wavelengths in optical, ultraviolet, infrared, and then cools. It's the emission. It's not that it doesn't have a radioactive origin. That luminosity is just cooling of a shock, of the supernova shock as it breaks out of the stellar envelope, out of the stellar surface. And so a spectrum taken there at the peak of this shock breakout of this early emission shows broad lines and no helium as a typical gamma ray burst supernova. Very curiously, at the time of the maximum, meaning at 20 days, helium lines are developed and can be observed. So if this supernova had been detected just like every regular supernova, after, like, starting from day 5 or day 6, after a week, for example, it would have been detected as a helium supernova, namely as a type 1b supernova, not as a type 1c supernova, not as a stripped envelope supernova. So this circumstance, the fact that the associated X-ray event is so weak, has so low energy, and the fact that helium lines are observed, which is very unlike supernovae associated with high energy events, made us think that there is a correlation between having helium lines, this circumstance, and producing only a weak event. Namely, if you have a significant envelope, meaning there is a helium mass, a helium layer of significant mass left over around the star when it explodes, a powerful relativistic jet cannot form. So you only see a midget, you only see a very tiny X-ray event. You don't see gamma rays. This is not a powerful, a fully fledged jet. So a special chapter is deserved by ultra-long gamma ray bursts. These are a minority of long gamma ray bursts. As you can see here, is the same view graph I've shown before. The duration of long gamma ray bursts is around, the majority of long gamma ray bursts range between 10 and 100 seconds. Well, long gamma ray bursts are much longer than this. They can be a few hours in rest frame. And it has been discussed what they are. I mean, do they belong? Are they the same machine, have the same progenitor, same mechanism as long soft gamma ray bursts? Well, the debate persisted. Here you see a prominent long gamma ray burst, 11-1209. The debate persisted until a counterpart was detected for one of these long gamma ray bursts. And you see here the light curve, the optical light curve. There is a detailed optical monitoring of this gamma ray burst, and the afterglow was found. Here you see here the decaying, the monotonically decaying afterglow, and then there is a bump in the light curve. That's the supernova. So let's go a little bit into some detail in the supernova. A spectrum was taken around the maximum of the alleged supernova. It's definitely a so it's shown in blue here in this view graph. It's definitely a supernova spectrum. Just it doesn't look at all like supernova 98BW. It is much more similar to the spectrum of superluminous supernovae. These superluminous supernovae are a subgroup of supernovae that has been relatively recently detected. They are truly superluminous, much more luminous than core collapse supernovae, or than regular supernovae for that matter. And this supernova 11KL associated with this ultra long gamma ray burst is more similar to those superluminous supernovae than gamma ray burst supernovae as we knew them before. You see here a comparison of light curves. At the center, you see in blue the supernova 11KL, which is intermediate in luminosity between superluminous supernovae. Here you see a couple of them, two representative ones, and gamma ray burst supernovae, 98BW or 6AJ. And the peculiarity, the interesting aspect of this supernova is that if you fit the light curve with nickel 56, just with purely radioactive mechanism, you need a lot of nickel 56, like one solar mass. But one solar mass of nickel 56 would require a much more severe suppression of the blue part of the spectrum, which is not observed. This spectrum is suppressed in UV, short of 2000 angstrom, 2500 angstrom. But the near UV and blue part of the spectrum is still very bright. It's not suppressed at all. So we suspect that there's something strange here, that there is some incoherence, which leads us to believe, to suspect that that the culprit, the responsible mechanism for luminosity cannot be ascribed to nickel 56 only, but there must be some other component which we tentatively identified with magnetar energy, meaning with the energy of a rapidly millisecond neutron star, highly magnetized neutron star, promptly formed neutron star. So this would be different from regular gamma ray burst supernovae, where we think that the final remnant, the central compact remnant is a black hole. So this is to give you an idea of supernova. It's a synoptic view of superluminous supernovae, just to put in context, to understand what we are talking about. Superluminous supernovae on the top of this view graph are compared with any type of previously known supernova, 1A in green, in turquoise, in light blue, and then black and green, light green is core collapse supernovae. So our 11KL supernova is here in between. It's at -20, absolute magnitude -20. Here is the top, the maximum is the -20. So it's truly in between. It's a gap. It's a bridging object. It's an object bridging the gap between superluminous supernova and every other type of known classical supernova. So we finally come to our object, the subject of this talk, which is the first gamma ray burst detected at TeV energies. This is the TeV sky, as we knew it until the detection of 190114C at an intermediate redshift, 0.4. 0.42 is definitely a low intermediate redshift for gamma ray bursts, since we know them, we know they explode. We've seen them exploding up to redshift 9 or 10. So this is definitely low redshift. But obviously for TeV detection, you do virtually need something at low redshift. And this is the light curves of the swift and magic light curves of the prompt event. So in light green is the swift but light curve of the gamma ray burst, and in red is the magic detection, and in blue here on the bottom you see for comparison the TeV level of the Crab Nebula. This is to give you an idea of the amount of power these objects emit in at TeVs beyond 0.3 TeV. This is the this is the isotropically radiated energy in gamma rays. It's a very respectable gamma ray burst, not one of the most energetic, but still very respectable. in gamma rays. This is a view, or a view graph of the multi-wavelength follow-up, multi-wavelength light curves of this object between radio and TV. There's virtually all frequencies in this view graph, light curves at all frequencies, and notably also in optical. You see them here in V band, R band, K band. So optical infrared are the green and purple little squares. So we see here, yeah, a better view of the optical. This view graph shows our own monitoring, which is published by one of our collaborators, Andrea Melandri. And this is the optical light curve that we have decomposed into a non-thermal, monotonically decaying afterglow and a supernova, shown as the turquoise pentagons. So the supernova, you see better here the light curve, the bolometric light curve of the supernova. Bolometric is a bit of an iffy definition here because this object doesn't have many data. We couldn't follow it up in many bands. So bolometric here actually refers to 3,000 angstrom between 4,000 and 7,000. So it's pseudo bolometric. In any case, the light curve, the bolometric, the overall light curve of this object is a little bit uncertain because it depends very much on the afterglow subtraction. So depending on how bright the afterglow we assume to be, you have two limits, two boundaries for the bolometric light curve of this object compared with other known gamma ray burst supernovae. So it can be as bright as 98 BW or lower or less luminous. And we definitely think that the most plausible light curve, most plausible case is actually the yellow circles rather than the orange circles. Namely, our object is more similar to less extreme gamma ray burst supernovae than 98 BW because the spectral appearance is definitely different from 98 BW. You see here in the panel, the top panel shows the same spectrum of this object in gray, in black and gray. So there are two because they are obtained under two different assumptions of the afterglow level, afterglow emission. If compared with 98 BW, definitely you don't see any similarity. While the same two spectra are more exhibit lines that are more similar, have similar widths to less extreme supernovae, core collapse supernovae like O6AJ, O4AW. So very remarkably or curiously, although this object, this gamma ray burst is TeV, emitted up to TeV energies, the accompanying supernova is not one of the most extreme objects. And this is interesting. So I have my summary of the ideas I have presented here. So it's been in fact more than 23 years from the detection of the prototype gamma ray burst supernova. And all of gamma ray burst supernovae we've seen so far, including those for ultra long gamma ray bursts, have rather large quantities, extreme properties with respect to the bulk of core collapse stripped envelope supernovae. The correlation that they exhibit a range. They are generally high in every property, but they exhibit a range. And curiously, we don't know how this range, how these properties correlate with those of the gamma ray burst properties themselves. There is no clear correlation. It seems that lack of hydrogen, the lack of a thick hydrogen and helium envelope is a condition to form a successful ultra-relativistic gamma ray burst jet. Ultra-long gamma ray bursts are potentially very interesting. Unfortunately, we have detected so far only one case. This is due to the intrinsic difficulty of detecting, the technical difficulty of detecting these ultra-long gamma ray bursts. They are associated with possibly the fainter tail of superluminous supernovae. And finally, supernova 19 JRJ associated with the TeV emitting gamma ray burst 1901 14C, the first known TeV gamma ray burst emitter, is a an interesting object, is probably as in the ballpark of gamma ray burst supernovae for what concerns the luminosity, but not as energetic. So thank you very much for your attention.
Thank you very much, Elena, for this beautiful talk and so rich of information, and presenting also the problematic which is clear between GRB and supernova, which appear diametrically opposite, in the sense that the supernova, the more we look at them, and we will present tomorrow 25 cases, including GRB 190114C, 25, they are practically the same peak luminosity, all 25 associated with the GRB. On the opposite case, the GRB instead are differentiated in three classes between 10 to the 52 and 10 to the 54, the 10 to the 48 to 10 to the 52, and below 10 to the 48, three different classes. But what is really incredible is that though the energy of GRB are very different, the luminosity of the supernova are the same. Therefore, this shown also in your presentation when you go from 98 BW, and you pointed out the difference with the structure of the supernova from 190114C, but we beg to understand why there is such a difference. Tomorrow we are going to attempt that. And the paradox is that the responsible for the different GRB, if you take into account the binarity, is still the supernova, that same supernova, but the condition where it acts are very different. And therefore, your presentation has been beautiful as usual, but also focusing on this paradox. And we will address this paradox tomorrow. Let's see if there are other questions. I'm sure they are, but let's see. Gregory, there are other questions?
If you see the question answer, maybe Elena can go and answer directly. Can you open question answer?
I think, yeah, I can, yes. So 2011 KL could also be a tidal disruption event. Yes, okay, misidentified as a supernova. Yeah, can I answer? Can I just say a word? Can I answer?
Yes.
Okay, so yeah, I would say the spectrum is quite revealed the blue here. The spectrum is a supernova spectrum. Anyway, it's similar to superluminous supernovae. Anyway, it can be, we can do, I mean, one can discuss in a better detail, but we have also identified the typical lines. So yeah. Is it safe to believe all core collapse supernovae and gamma ray burst connections correspond to supernovae 1C? Yes.
Yes.
Yeah, yes, definitely. Wherever we could study the spectrum well, which is not a given, you need to be at very low redshift. You need to have a very high quality spectrum in order to identify atomic species. When you are in that condition, which is you need to be at redshift less than 0.2. If the redshift is no larger than that, you can identify atomic species. In those cases, you never see hydrogen, you never see helium, except in this very peculiar case, which is not, technically speaking, a gamma ray burst. So yes, the lack of hydrogen and lack of helium is a distinctive sign, distinctive characteristic of gamma ray burst supernova. And it's related to the bareness of the exploding stellar cores, which make it possible to launch a powerful, relativistic, successful jet. Are ultra-long gamma ray bursts and superluminous supernovae conceivably related? I don't know. All I can say is that in Jochen Greiner's 2015 paper, we have argued that the possible role, partial role of a magnetar may help making both part of the luminosity of the supernova, of the superluminous supernova, and make an ultra-long gamma ray burst. I don't know so I'm not sure we have other elements to expand on this, to elaborate on this. Unfortunately, that's the only case. It's an isolated case. So we don't have much, we don't have a sufficiently solid benchmark with only one case.
I think we should end this talk. If you have any other questions, you can type your questions in the question answer box.
Sure.
And also Lina can answer your question by typing.
Sure.
Okay. So I think you should end, stop sharing your screen.
Yeah, sure. Let me do that. Stop share. Yes. Okay. Thanks.
Oh, thank you very much. So the last speaker of block 1 is Carlos Revulas. Are you ready?
Hello. Good morning. Yes, I'm ready.
So yeah. Yeah, we can see your screen.
Yes, but I have to move this bar here in order to. Oh, yeah.
You can show the full screen.
Yeah.
Yeah, perfect.
Okay. Good.
Yeah, you can start.
Yes. Give me please 1 second. I want to hide this bar in order to don't. Well, we put it here. Okay. Good morning. Thanks. Thank you. Now I will change topic a bit. This talk is about dark matter in the Milky Way. So it will do mainly to dark matter, but also it will be related to the central galaxy center, the central ocean in our galaxy, Sagittarius A star, and but also to massive black holes, as you will see in a moment. So this talk was the works. This talk is based on the works here you can see below. It's a series of papers we have published in the recent years with our collaborators from ICRANET mainly, Remo Ruffini, Jorge Rueda, Andreas Krut, Edward Becerra, and Rafael Yunis, also my student. Okay, let me start with the outline of the presentation. First, I will introduce some preliminarities about cold dark matter. Then I will move from Blasov-Poisson to self-gravitating fermions as dark matter halos. Then I will show the case of the Milky Way and the galaxy center. Then I will move to universality of fermionic profiles. And lastly, we'll introduce the concept of critical core mass and supermassive black hole formation from dark matter. Then I will conclude. So let's start with a bit of contextualization of this talk. So this talk will have to do with within the particle paradigm of dark matter. So let's assume you have a neutral fermion generic dark matter candidate, which was created just after inflation, and that decoupled from primordial plasma in the first fraction of a second prior to photon decoupling, and then due to the primordial density fluctuations, and the expansion and cooling of the universe, these fluctuations grew, and it generated the seeds of dark matter halos that then will act as a potential wealth for baryonic matter and lately galaxies as we see today. So these generic dark matter candidates are the basic hypothesis is that it is cold and collisionless fluid, and it has been given a very successful consequences for cold dark matter. So we can say that astrophysical observations such as CMB, BAO, Lyman alpha forest, and the local distribution and evolution of galaxies, ranging from horizon scales to the typical scale between galaxies, are all consistent with a universe that was seeded by a scale invariant primordial spectrum, and that is dominated by dark energy, followed by dark matter, 25%, and only roughly 5% of baryons plus radiation. So this is what is called the lambda CDM cosmology. And as we have seen yesterday, in the beautiful talk of George, that from cosmological perturbation theory, so the theory that describes how primordial density perturbation grow into galactic structures, gives this beautiful CMB anisotropic distribution. For example, for temperature distribution, which was measured with a precision of 1 in 10,000, remarkably, and one of the many consequences. But regarding dark matter, one of the strongest evidence for dark matter is that in order to explain the temperature fluctuations in the Bauer spectrum, you can demonstrate that these peaks in the spectrum are very sensitive to the amount of dark matter. For example, this is a qualitative example where you see that as soon as you decrease the amount of dark matter, the relation between second and third peak changes. And also, if you increase the dark matter, also the height of the peaks and the positions also shift. So this is out of this CMB data and lambda CDM cosmology, we can say there is a compelling evidence for non-baryonic matter in the CMB. Okay, so now let's move, as will be the main topic of this talk, let's move from large-scale structure to dark matter halo-sized structures. Therefore, this is a picture in the left to the Sloan Digital Scar survey of some years ago, where you can see that in the local universe, the distribution of dark matter is not homogeneous, but is in a form of a cosmic web with these beautiful filaments, nodes, and voids. And these are images of a huge amount of galaxies that cluster in this way. And interestingly, this kind of distribution, of local distribution, has been updated recently by the DES survey, the Dark Energy Survey, which reached to make photograph of more than 100 billions of galaxies, superseding these nice distributions. So when you point into a node and into an object inside this cosmic web of the size of a halo, let's say 100 of kiloparsec, you have this a picture of a dark matter halo arising from simulation in this case. And then we can see the role of dark matter in the halos, as you probably heard, that it implies generally that the rotation curve, so the circular velocity of stars around the galaxy, do not follow the expected Keplerian behavior in the outer parts due to baryons, but instead remains constant in a certain window of radii, showing the need of an extra matter component, which is not emit light and is roughly spherically distributed, ranging around an order of magnitude larger than baryonic matter. Okay, so now let's move a bit to some mathematics and how we can explain or attempt to explain these dark matter halos in terms of spherical distribution of fermionic particles. So let's start with the assumption of collisionless particles. So is dark matter, we can think of a collisionless system described by mean field Vlasov-Poisson equation, which is this equation here, where is in terms of mass density phase space, so a phase space density F, which is a function of position, velocities, and time, and is coupled with Poisson. So you can see here the F is coupled with the Laplacian of the gravitational potential. And interestingly, this Vlasov-Poisson equation, which is in terms of fine grain density phase space, can lead to an coarse graining, can make a coarse graining where the distribution function is separated into an average plus density fluctuations, fine grain density fluctuation, F tilde, and then you replace, and you can show this equation with the left-hand side resembles the Vlasov-Poisson, but then in the right-hand side appears a diffusion current where we have put all the fine grain fluctuation averaged. And so what we'd like to solve, which is the most likely distribution function at coarse grain level at equilibrium due to self-gravity. So one way to do this, because this is a difficult task to solve these equations, because you have to know the microphysics of the fine grain fluctuations. But a good way to proceed is to ask this effective diffusion current to fulfill macroscopic constraints, just a first and second law of thermodynamics, so energy conservation and entropy maximization. This is a form of a Lindenbell entropy, which when maximized, it tells you about the relaxation of the system. And this is a maximum entropy principle, which was shown in the original work of Chamonix in 1998. And so the key point here is that during this evolution, the system maximizes its rates of entropy creation while satisfying the contrarified field by the dynamics. So this is so-called the maximum entropy principle. So if you mix this entropy principle with quasi-linear theory, you can, as shown here, you can also write this coarse graining kinetic theory equation and put in the form of a modified Landau equation, which allows not only to obtain the expression for the current and calculate the relaxation time scale, which in these cases, the collisionless relaxation time scale is much smaller than the collisional relaxation times, and allows you to find a most likely coarse grain phase space distribution at relaxation, so stationary, when J is constant. So interestingly, the form of this phase space distribution of particles at relaxation is of the Fermi-Dirac type. You can recognize here in the denominator this Fermi-Dirac type, and the numerator has a cutoff in energy, saying that for energies of particles above cutoff energy, you don't, your particles, it talks about the evaporation of particles above a given energy. Interestingly, this stationary solution is a generalization of the traditional Lindenbell distribution function found in the beautiful work of 67 about binary relaxation. including for particle evaporation. Therefore, as you may remember, the Lindenberg theory was developed for classical particles, but it was extended also to include indistinguishable particles, such as neutrinos or fermions more generally. And in the case of fermions, therefore,
Yes.
In the case of fermions, the maximum accessible value of the distribution function, eta 0, is fixed, of course, by Pauli principle, which shows you that the maximum phase space density proportional to the particle mass to the 4 inverse to the h cube. Therefore, once we have a most likely phase space distribution of particles, in this case of fermions, at relaxation in a halo, we can proceed to solve which is the more general solution at equilibrium, the profile, the mass distribution at equilibrium out of this distribution. So a first important concept is that fermions under self-gravity do admit a perfect fluid approximation. This was demonstrated in this original paper of 69, Rufino and Bonassola. Therefore, we proceed to solve the Einstein equations for a semi-degenerate gas of fermions in hydrostatic equilibrium, so these Tolman-Oppenheimer-Volkoff equations in spherical symmetry. So here is just a sketch of the equations in dimensionless form. But the important point here is to see, well, the first, of course, is that these are Einstein equations, first and second, the only two relevant Einstein equations in spherical symmetry for this distribution. So the mass equation, the TOV equation, probably you recognize, and the third, fourth, and five are Klein-Tolman conditions of isothermality in general relativity and energy conservation in geodesics. So you have to couple this Einstein equation with the source, so with the equation of a state, with density and pressure, which are written in terms of the integrals of the phase space distribution, which is this of Fermi-Dirac type, which this has to be thought at Kurzweil level, which is exactly the one I showed before out of relaxation mechanisms. So one important point is that this equation of a state is not barotropic, is parametric equation of a state, where the temperature will depend on the free parameters such as the temperature of the effective temperature of the dark matter, the degeneracy, and the cutoff energy. The energy here is genetic energy, which is written relativistically, but depending on the regime you are, it can also go from non-relativistic, but also allows for relativistic regimes. So as you can see, this is a system of coupled, highly nonlinear, ordinary differential equations, and you have to solve for boundary conditions. So for a mass at the center, regular mass at the center, not singular, central degeneracy, we will search for solutions larger than 0, because the degeneracy lower than 0 goes to the traditional pseudo-isothermal sphere solutions. And well, given temperature, a given cutoff parameter. And this theory has 4 free parameters, which is the particle mass, the temperature, the degeneracy theta, and W, the cutoff energy, which we have to give at the center of the configuration. This is a boundary condition problem. So once you have the full system of equation, you can find that the most general solution out of this equation with boundary condition, with fixed boundary condition in agreement with halo observables. For example, in the case of a typical spiral halo with typical halo scale length of 10 to the 4 kiloparsec and halo masses of 10 to the 11, which is roughly here, with fixed boundary conditions, you can find, for example, a solution like this. You can see here the main feature of this solution is that at the center, it develops a dense and degenerate core of fermions, which uses the Pauli principle in order to reach this highly degeneracy concentration, and then continuously goes to Boltzmannian tail. So the central, in such a case that the central object is support against gravity by degeneracy pressure, while the outer atmosphere of fermions is support against gravity by thermal pressure. Interestingly, at the scales where most data are in far galaxies, the slopes and the distribution of this profile, well, of course, our profile are curved towards the center instead of cuspy, but in these windows of radii, all profiles such as a NASTO or either Barker or NFW coincide more or less at this scale. But the important point or the important question here is which is the role of this high density concentration of fermions here? First of all, it's important to say that it is satisfied quantum condition, so it can be checked for all solutions with degeneracy larger than 10, and the thermal de Broglie wavelength is larger than the 3 times interparticle mean distance, so satisfying the so-called quantum condition. And importantly, the dark matter profiles, mainly the feature of the course, will depend on the particle mass. And this is an example, typically with particles of 10 keV, you obtain this dense concentration, we start to fall inside the milliparsec scales. Okay, this is up to now the generic solution of these equations of, say, gravitating fermions, and then we proceed to apply to the best known case that we have, which is of course, our galaxy. So first, let me introduce some preliminarities about our galaxy. So the central parsec is governed by, as you know, by a dark compact object of roughly 4 million solar masses, presumably a black hole. Then the central kiloparsec governed by a inner and main spheroidal bulge. And then when we move to 10 kiloparsec, the dynamics and kinematics is governed by a flat disk or well, with some thickness, depending on the model. And in the outer region, of course, we have an extended dark spherical halo with a mass of 25 kiloparsec, roughly 10 to 11, as constrained by observation. So in the panel of down here and right, you can see the data of the rotation curve showing this approximately flat regime in linear scale here. Above, as you can see, this is from 2013, but above, let's say, a few tenths of kiloparsec, the error bars start to increase considerably. And this is a nice picture in the left, bottom left, in the logarithmic, showing that for the first time in the work of the world expert Sofue, he was able to link the kinematical tracers from a few parsec, so in the inner bulge of the galaxy. This is the peak of the main bulge. This is the inner bulge. Of course, the error bars here are larger because are showing the non-purely circular motion, because there are also a bar, as you may know, at the center of the Milky Way, but this as a defective circular rotation curve accounting for the non-circular motion, and well, here extended the rotation curve. So besides this data of the rotation curve, we can also look to the innermost first milliparsec of the Milky Way, and as you see here in the picture of the left, which is the S-star cluster, because the central region of our galaxy between milliparsec and few parsec consists of these young S-stars and molecular gas, following mainly in average a Keplerian law. So it has to be dominated by a very high mass and compact object. And interestingly, besides these beautiful S-stars with very precise data, as shown, which led to the Nobel Prize of last year, from the European and from the American teams, showing resolving with high accuracy the motion of these stars. It also, I will also include the G2 object, which first was, this G2 object is not fully well understood object yet, but first was thought to be a cloud, which orbits very nearby the center, Sagittarius A, with a pericenter very close to S2 star, which is one of the closest. And showing this, this is a simulation, the observation showed some stripping of mass around the when passing the pericenter, and either is the nature of this object is still discussed. It is more or less accepted that they should be not be of a gas, purely a gas, but it should be of a stellar composition, probably with some lost mass, because the main discussion here of Z2, let me say, is that if it is assumed to be only a gas cloud, then it should have been completely ripped off when passing through a galactic center, as the most refined simulation has recently shown. So, as you know, the best object to constrain the central mass in the center of a galaxy is the S2 star, constraining a central mass roughly of, well, this is a bit outdated value, 4.2 10 to the 6 solar masses within the first milliparsec, but now values are more roughly about 4.1 10 to 6. Okay, so the challenge here is to use all this data, so the outer part of the rotation curve, but also the inner bulge data plus the S-star data, the precise measurement, and ask if these core halo profiles arising from relaxation mechanisms for fermions can, the potential can explain this rotation curve as well as the dynamics of S-stars without introducing the black hole hypothesis. So this is a fair question to be asked in these kind of profiles. And of course, you have to, a hint is that you have to solve the boundary condition problem, fixing these known values from observations, which you can fix at the center, the core of this dark matter. You can fix with the mass of the central object, and two other values in peripheral observations, either at the intermediate halo scales or also at outer halo scales, by, for example, by Sagittarius dwarf galaxy, in order to constrain the outer part. So all this data is used, and very remarkably, so it is possible to obtain generic solutions, a family of solutions. I show here in black core halo profile of fermions for a particle mass of 345 keV, down to the core halo profile in dashed gray for particle mass of 48 keV. So this particle mass range, because a key feature of this profile is that the larger the particle mass, the more compact and dense is the central core, until you reach the critical value of collapse due to the field degeneracy reached by this core. Therefore, it's interesting that that you can find a family of solutions for particle masses around 10-ish to 100 of keV that not only matches the full rotation curve of the galaxy. Of course, here you have to add the standard bulge in green and disk in dash green contributions, but also in this plot here, I show the eight best resolved S-stars in average circular velocity, where you can see that this high compact dark matter core is inside the pericenter of one of the closest stars with this S2. Therefore, so it is possible to make this fitting, as I have shown here, and this is a zoom of the outer part of the rotation curve, given by either NFW fit in black and our model in red. So both can fit very well the outer rotation curve. But then this is, we can go further and ask, well, can not only the average circular velocity of these stars be fitted or be reproduced without the black hole with this core, but also the geodesic or the orbit or the full astrometric data of S2 and G2. So we have done this work recently, and so let me first clarify the data that must be reproduced here. So there is a large amount of very precise data from BLT, Keck 1-2, Gemini North, and Subaru, handled to a multi-year accurate astrometric data of S2 star around Sagittarius A, including for relativistic redshift, as was found very recently or are shown to be the case for S2 star in gravity collaboration. And but also I have to be able to fit the most currently available data of the orbit and redshift of the G2 object, which was also possible to be detected. And also the G2 post-pericenter passage deceleration, which in the case, in the paradigm of the black hole, was explained in terms of a drag force. Okay, so let's start with the S2. So the S2 orbit, here I show in these gray dots all the astrometric data of right ascension and declination of S2. And in red, you can see the best fit of our model of dark matter, how the central core reproduces these dynamics, and in blue, the black hole. So these models are calculated by solving the geodesic equations of test particles in the gravitational field, either of a Schwarzschild black hole of 407 × 10⁶ solar masses, and this is the average reduced chi-square, this is the statistic of 3.3. And in the case of fermion core with a particle mass of 56 kiloelectron we are able to fit this data with a similar reduced chi-square, even statistically preferred. Now, let's move to the radial velocity in the line of sight of S2. So now, first was the astrometric data, right ascension and declination, and now the radial velocity of S2. So you can see this typical curve of radial velocity with the star is approaching to us and what is preceding us. And here is the data from, as you can see, more than 20 years in the 1994 first data until almost today, when S2 passed 2 times of pericenter, 2 times pericenter passage. And we can see beautifully that the redshift excess, so this redshift excess means the difference between the total radial velocity of the stars minus the Keplerian, the Newtonian contribution. So if this difference is larger than 0, it means that there are relativistic contributions to the Keplerian radial velocity, and this is the case which was confirmed a few years ago by gravity collaboration in red for the black hole, sorry, in blue for the black hole, and this can also be equally reproduced in red by our dark matter core. So this relativistic redshift can also be reproduced. Now, but more interesting or intriguing is now the case of the G2 object, because of course, G2 object has an orbit which is larger in size, and the period is for S2 is around 16 years, while for G2 is quite larger, and therefore it cannot complete an orbit yet. So here is the data, and we again calculate the geodesic equation of a test particle in the gravitational field of a Schwarzschild black hole and the dark matter. And interestingly, when combined the fit with the radial velocity, here now is the case for radial velocity in the line of sight of G2 with this astrometric data, we found was very surprised, and we were very shocked to see this fitting, that for the same particle mass of 56 keV that you fit the precise astrometric data of S2, you can fit very well the post-pericenter passage, as you can see here, this 3-point after pericenter passage of G2, while in blue is the black hole model, that much better than the purely black hole, Schwarzschild black hole. You can see here the reduced chi-squares. In the black hole is 26, one in our case is close to 1. And so without the need of a drag force. So in the case of a black hole, this was explained by invoking a drag force with an accretion disk. though in extrapolating the physics of the accretion disk towards central regions where yet the environment physics is not well known, but by tuning some parameters, it was possible, it is possible indeed for the black hole paradigm to fit this data. However, the way it was done, it was needed to assume a gas cloud nature for G2, which is quite discussed recently. So there are different works suggesting that G2 should not be a gas cloud, but of a stellar nature, because otherwise it would have been ripped off by pericenter passage. And therefore, we find very intriguing that without the need of a transport, it is possible due to the continuous atmosphere around the core of dark matter, which cause a gradient of gravitational potential, generating these change in accelerations, able to fit this data. Very recently, we have extended our analysis and took the 17 best results as stars with the few data provided by the telescope I mentioned before. And by repeating the same procedure, we were able to also provide very good fits for all these 17 orbits. In red is S2. Well, the average chi-square, including right ascension, declination, and radial velocity of all the stars. In the case of a Schwarzschild black hole, is 1.5. Well, interestingly, the dark matter case is statistically similar or equivalent, but sorry, in the case of RAR is 1.5 model. In the case so a bit statistically preferred slightly than respect to the black hole, but statistically, let's say, equivalent. It was shown recently in this paper and published in Notice letter, where we say here that for these 56 Kev fermions, you can have reproduce these dynamics together with the S2 and G2 objects. Okay, now in the last part of the talk, I will move fast to what about the universality of this profile. If you can apply for same particle mass, this core halo distribution to other galaxy types, from dwarfs to ellipticals to galaxy clusters. Well, we have attempted this phenomenology and have shown that, for example, taking the 8 best result Milky Way satellites, but also a sample of nearby things sample and some ellipticals by wheel lensing, so we can have observational well constrained mass and radius at the halo scaling radius, these green dots, and have explored the full family of solutions of dark matter profiles that are able to match this data to show that there are a family of possible degenerate cores of dark matter. We are able to fit this data, and interestingly, it can be shown, for example, in the case of dwarfs, that the core masses. Yeah, here this is mass in the upper plot is mass in the y-axis and radius in the x-axis. You can see that mass of the core ranges from roughly 10 to 4 up to 10 to 6 solar masses. So it's a nice natural indication of intermediate mass in black holes, but not collapse, but in terms of interpreting in terms of high density cores of dark matter and not black holes. In these spirals, the core masses rises and goes from 10 to 5 up to 10 to 8 solar masses, up to the typical masses of active galaxies, and the same for larger elliptical. So we have further tested the correlation of these central core mass, halo mass, which there are correlations from data, which is this Ferrarese correlation. So Ferrarese not only have shown the more maybe known as M sigma correlation relating the central object mass with the bulge mass, but also correlations really for large galaxies, relating the central object mass with the halo mass. So this is shown in this strip here, light blue strip, and we have in the full coverage of our parameters, we have shown that there are always families of profiles that can match this correlation, And in gray, these dots are profiles which are core halo, as I showed before, but with halos, with the tails of the halo following a power law similar to the one of simulation of given radius. So another important point is that, well, in diamond is the Milky Way here, but another important point is that the maximum mass for a particle mass of 50 keV, the critical mass of the central core, is 2.2 times 10 to 8 solar masses, interestingly. So this is the case that the degeneracy pressure, when becomes highly relativistic, can no longer support gravitationally the gravitational and become unstable while reaching this critical mass. This thing I'm showing here in words can be demonstrated theoretically and formally from this was shown here from the turning point criterion in general relativity, but also from thermodynamics, showing the second variation of entropy until the system became unstable. So on both criterion coincide. This is very nice to show that this concept usually applied to neutron stars can be extended and generalized for system of fermions of finite temperature as this one, and lead to this critical mass. This is interesting value because this value may provide initial seed for formation of supermassive black hole in active galaxies, because you can imagine that when this halo, that the halos now are born of core halo nature at high redshift, and therefore you don't need to start with a population 3 star and then undergo hyper-enton accretion in short times to form the observed supermassive black hole, for example, at redshift 7 of 10 to 8, but you born with this, out of this theory, it is possible that the central core is already born at high redshift, and then if the conditions are given, it can collapse to a supermassive black hole directly, and then, of course, keep growing up to 10 to 9, 10 to 10 solar masses later on. So this is my last slide, showing that from our results, our results suggest that normal galaxies, so non-active galaxies with central object masses of 10 to 6 up to 10 to 7, may not be, which of course do not show generally jets nor activity, may not be supermassive black holes, so singularities, but dense cores of dark matter, and that's why you don't see activity. But for larger galaxies, or active galaxies, which masses of the central object typically larger than 10 to 8, you do, which have jet emissions and hard X-ray, you do need a black hole at the center, but in our model, it may be produced by the collapse of dark matter. Okay, so I will move to the conclusions. And so accounting for the quantum nature of the dark matter in the relaxation of halos, let me emphasize that this is not possible actual cosmological and MADI simulations we do for classical particles. So it's important to introduce the quantum nature of the particles.
Lasciato tutto il meeting.
Yes. So can lead to novel profiles, which are long-lived and develop a compact nucleus surrounded by a dilute halo. These core halo profiles can explain the galaxy rotation curves, but also provide alternative to central black holes in non-active galaxies, offering explanation, for example, to natural explanation for intermediate massive black holes in terms of these dense cores. Then, for particle masses of 50 keV, both the black hole and the core of dark matter can explain precise astrometric data of S2 clusters, of S-cluster stars, including S2. But besides the S-star cluster and the Milky Way rotation curve, altogether, this continuous core halo distribution can explain the post-pericenter passage of G2 without invoking a drag force. And interestingly, and finally, for the same particle mass used to explain our galaxy, the critical mass for gravitational collapse of these high-dense dark matter cores can lead to a supermassive black hole formation of masses of up to 10 to 8 solar mass. Okay, I stop here, and thanks a lot for your attention.
Okay, thanks, Carlos. So I have a very short question. Can you model explain the precision of S2 star?
Oh,
Precision.
Yes, this is a very good question. Indeed, indeed we can. Let me say a few words about that. Precession, relativistic precession of S2 star was up to now measured 2 years ago, or by European team, showing that it is consistent with general relativity. So indeed showing a precession, which of course it wouldn't exist in Newtonian gravity, when the star was passing at the pericenter, at second pericenter passage. Interestingly, it was shown also recently by the American team that the precession of S2 happens at, or is more visible at apocenter. And it is very interesting that we are calculating right now this, the precession, and it may lead to some surprises because we have to wait to the second apocenter, well, third principal apocenter passage of S2 to see which model is preferred, if a black hole or a dark matter core, given that, as you can already imagine, the extended distribution will generate an extra precession effect due to the extended mass out of the orbit.
Okay, thanks.
But new results coming soon. New results coming soon.
Okay, we're looking forward to see.
Okay, so good.
I think this is the end of the block 1 because the chairperson of block 2 is not here. I continue to chair the next block. Yeah. So Raymond, should we have coffee break or should we continue?
Sorry, there are a couple of questions.
So I mean, we should continue, or we should have a coffee break.
Yeah, it's better continue. Yes, it's better continue. We are a little delayed.
Okay, okay. So, Carlos, can you stop sharing your screen?
Yes. Give me why. Oh, yeah.
Our next speaker is
Carlos. Beautiful talk.
Okay, thank you. Thanks a lot.
Yeah, thanks. So the next speaker is Professor Di from National Astronomical Observatories of China.
All right, I'll share my screen. Let's see whether it works. Can you see my presentation? Hello, can I be heard?
Yes, we can hear you. And we can see the beautiful image of your radio telescope in the beautiful hills of China.
That's good. Should I start?
Please.
All right, thank you. So it's my pleasure to have this occasion to report on the FAST telescope and its view of the transient sky. And FAST was largely motivated by the revolutionary concept of Arecibo. And if we look at the radio antennas, the largest fully mobile antenna is the Green Bank telescope. So it's roughly the size of Statue of Liberty and weighted over 7,000 tons. And that's practically the limit, the engineering limit of such a concept. And then there's Arecibo with a fixed spherical primary and rather complex secondary and tertiary optics. So FAST is represent a major advance in that it utilizes a active primary surface. So it's a primary focus semi-mobile telescope, and it's reformed 300-meter of its 500-meter geometrical aperture into a parabola, and that can do tracking and changing sources. And it's the primary surface consists of more than 4,000 panels. Each one is 11 meters. On one side, a triangle, and we put those triangle on this tensioned cable mesh system, and you can connect 6 triangle with this metal plate, and then pull it down with an actuator. So by changing the tension distribution of this cable mesh, the reshaping of the dish and tracking can be realized. And to do that, to the required precision, we use near-infrared laser that's shining on an optical target. So each actuator, there are about 2,000 of them, are attached to this optical reflector that's made up of a set of lenses. So this picture was taken in 2015. I just climbed up on one of the measuring towers. And at the time, there was exactly 0 lights on site. So all the sort of light points you are seeing here is at the moment when I click on the flash, and it's reflected back from those optical reflectors. So the whole site light up like a Christmas tree. And this is an animation showing the concept. So by moving those connecting plates within roughly 1 meter, it's sufficient to change it from part of a sphere to a parabola, since they are of the same curvature radius. And it's a primary focus telescope, which means you also have to fly the focus around on a curved aperture plane by a few tens of meters. And that is being realized by 6 very thin cables. It's hardly perceptible if you're standing beside the dish. You can also see that tiny shadow of the receiver dome, which basically can be translated into a very clean primary beam. And the whole project cost about $180 million. Given its size and complexity, is relatively cheap, I would say. So the working horse of our receiver right now is a 19-beam focal plane array. It has a 1-beam gap. Basically, it's a 19 separate receivers, feed horns. And when you project it onto the sky, it covers roughly 20 arc-minute across. However, it covers only 1/4 of the full area of the aperture plane. So what we can do is rotate the feed to a certain angle, change the dish, reshape the dish, and let the Earth rotate. So so one of the most efficient survey mode is this so-called drift scan, which take about 5,200 hours to cover the full northern sky, accessible to fast, which is about 2.3 pi solid angle, or 57% of the full sky. And there are 5 primary science goals, and in our band, the so-called L band, the obvious target, primary target are hydrogen gas and pulsars. And if it take, say, 5,000 hours to do one drift, it probably would take 20 years to do the surveys one by one. So there's the galactic H1 imaging survey, the galaxy survey, and the pulsar survey. And now, of course, there's also the transient survey that largely motivated by fast radio bursts nowadays. And if we look back into the history of large major telescopes, starting from Arecibo, there's Green Bank, Effelsberg, and a slew of other famous instruments. There have never been a simultaneous survey of H1 and pulsars. So that makes us thinking and looking into the challenges of realizing a simultaneous survey, or so-called commensal survey. It turns out that the key challenge is the calibration of the H1 image. So here is a representative image from Arecibo. Those scanning patterns come from short time gain drift of the receiver, which can be calibrated out by injecting an artificial calibration signal, which is basically an electronic noise. However, the pulsar astronomers just hate that, because you inject an artificial periodic signal that mess up the power spectrum that you use to search for a real periodic signal that are pulsars. So from 2016, we collaborated with the Berkeley team led by Dan Wassenheimer that utilize a modern backend that can process a very high volume of real-time data stream. So this is a demonstration of that cal injection. So if we inject a, say, 1 hertz, a cal signal every second, and Fourier transform it to get the power spectrum, you get a 1 hertz peak. However, there are also the harmonics that at 2 hertz, 4 hertz, 8 hertz, so on and so forth, and it will mess up the power spectrum. So our concept is very simple. We try to inject the cal signal as quickly as possible. At the moment, we do it at the sampling rate, which is about 100 microsecond, which means we inject a cal 10,000 times every second, and we process them through 4 conceptually independent backends. So pulsar backend, spectral backend, and transient backend. And the spectral backend separate into narrowband signal and wideband signal that are for galactic and extragalactic H1. So this concept was developed since 2015 and has been fully demonstrated by the end of 2018 and led by Mark Kirchhoff, that is my academic sibling from Cornell and now a regular staff at NAOC. So based on this concept, we designed a so-called commensal radio astronomy fast survey that can realize this unprecedented commensality and record simultaneously pulsar H1 galaxies, galactic H1 imaging, and fast radio burst data. And the main challenge of such a survey, of course, is the data rate. So we basically fill up a hard drive of one, say, a laptop every night, and it's translate to about 5 to 10 petabytes for this one program. And we do real-time compression so that and the data product is about 1 petabyte per year. And so far, this drift scan survey has discovered more than 120 new pulsars and more than 40 millisecond pulsars, more than 20 binaries. And those solid red stars are those that we have already obtained phase-connected timing solution. And those crosses are an upper limit to the p-dot, which we have not follow up sufficiently or have not achieved the timing solution. So we have 2 timing papers, one published last year and one is still under review. And led by Weiwei Zhu, also of NAOC, that he already found the first double neutron star system in the CRAFTS data. It seems to have a very small total mass, since unfortunately we cannot measure the Shapiro delay, so we probably need to do more timing to further constrain its mass. So the imaging part is always more challenging, and it has been improved from year to year. I think by now we have achieved publication quality. And one nice feature facilitated by both this innovative mode and also the absolute sensitivity of FAST is that on average, we have about 1 detectable quasar per square degree. So so that gives us a point source grid on the sky that when we cover a substantial fraction of the full sky, it will facilitate a making of a very good quality and well-calibrated H1 images. And at the same time, we can also search through the band for redshifted H1 signal that come from galaxies. So the current state of the art of gaseous galaxy catalog is from Arecibo that contain about 35,000 galaxies. And by the end of the craft survey, we are looking to increase that by 10 to 20-fold. For the fast radio burst, from very early on, we realized that FAST is not competitive in terms of number of discoveries. Just less than 1 month ago, Chime published close to 500 new fast radio bursts. That's really a game-changing instrument. However, we can do much deeper than anyone else. So that's what we are aiming for, to try to find the faint pulses and extended the detection range in terms of redshift. So far, in 2 papers, we have published 4 new fast radio bursts, and they are all within the DM range somewhere between 1,500 to 2,000, and which actually translates a full sky event rate of more than 120,000 per day. And actually, it's not that surprising. It's a simple extension of previous estimate down to the sensitivity limit of FAST. So if this trend continue, which means fast radio bursts still exist at even higher redshift, by the time of SKA, we are looking toward somewhere between 1 million to 10 million events per day. So it's regardless of whether we can understand its origin, it will be a significant astronomical phenomenon. And this is just another representation of our detections. So we are now looking into the estimated look-back age of the teenage years of the universe. And for the brightest pulse that roughly give out 1 year's worth of solar energy within 1 millisecond, FAST will be capable of detect them up to redshift of 10. So one of the new discoveries is a very active repeater, and we were able to localize it with VLA, real fast system, and follow it up with optical measurement. And the publication is being prepared. But the punchline of this system is that it has 60 to 70% of its DM coming from its host galaxy. And we hypothesize that this is a sign of its in the complex magneto-ionic environment. And in turn, it's also a sign of a very active repeater at its early evolutionary state. And this drift scan simultaneous survey pattern also allow for multi-band joint campaigns. So this is one effort led by Jian Jiang, try to doing joint observation with the optical telescope. So we will see how it turn out in the coming month. So this is just a representation of the crafts concept, and hopefully with one drift cover of the sky, we are looking toward about 1,000 new pulsars, 500,000 new galaxies, about 10 billion voxel H1 images, and a few tens of fast radio bursts that should be on the fainter end and extend the redshift range of the current sample. So for during the drift, we are only looking toward equivalent of 6 seconds of integration of a point source. So with much longer tracking observation, we can go much deeper. The first millisecond pulsar discovered by FAST was toward a previously unassaulted Fermi source. So it around 500 megahertz, it roughly have 60 microjansky flux, and neither Arecibo nor FAST can detect it in other bands, which translate into a flux limit at 1.4, around 1.2 gigahertz below 20 microjansky, so making it one of the faintest radio pulses ever detected. Actually, we have this MOU and collaboration with Fermi-led team. So we are systematically searching for Fermi point sources. Right now, we are looking at 5 new pulsars, and one of them is in the compact, relatively compact binary system. It's a 4.2-hour orbital period. So dedicated tracking observation of known pulsar system also produce interesting science result. So this is a scintillation study toward pulsar J0538 in supernova remnant S147. What we did is to analyze the scintillation pattern in terms of its relative configuration of the pulsar when the pulse is passing through the electron screen that represent this supernova remnant. So this gives us a constraint on its radial velocity in conjunction with the analysis of the polarization and the proper motion provided by VLBI and X-ray. We were able to constrain the 3D configuration between the spin of the pulsar and the spatial velocity. So this is a little animation. So this is supernova remnant. It has a age estimated to be 35 kilo years. And the punchline of this work is that within the uncertainty of the data, we found the first evidence for the 3D alignment between the spatial velocity result from the NATO kick of the supernova explosion and the spin. And it's still not well explained by any of the, say, supernova explosion simulations. So it's food for thought for the origin of the neutron star spin. And to better utilize this survey time, we have also built a dedicated transient backend that can in quasi real-time search for SATI signal and fast radio burst. And we were lucky when we sort of first put on this system to catch a very active episode of the burst from 12/11/02. And this is a pulse from August 30th, 2019. And in the subsequent campaign that lasts a little more than a month, it's quite amazing. So we basically keep seeing burst on some of the peak days. And you can see the background image is from HST, and on the upper left corner is the time of the burst, and the brightness of the burst scale to the radial fluxes. So in some of the peak hours, the rate can reach close to 120 bursts every hour. And there's no obvious periodicity. So it's certainly not from a single neutron star. And this is showing the cumulative burst numbers and burst rate. So I will just discuss one science aspect, which is the energy distribution of the burst rate. It has a clear identifiable peak energy, roughly about 5 times 10 to the 37 erg. And the full distribution can be better described by 2 functions. One log normal function at lower energy, which possibly represent a stochastic processes, and a Lorentzian function on the high energy, which can describe the ratio between two independent random variables. So that could be 2 stochastic process that coincidentally correlated with each other. But given the current observations, we cannot go much further in terms of its underlying physics. So one of the famous event last year is the galactic fast radio burst that has been associated with a magnetar. So FAST has done a subsequent follow-up and provide a very stringent limit on its radio flux. So it's roughly 8 orders of magnitude deeper than the discovery pulses, which means such bright pulse are still very rare from a magnetar. So this is a time domain analysis. So the upper left is the waiting time distribution of 121102. So it has no identifiable periodicity or quasi-periodicity, which is very unlike 1935, which for a few months at least is basically a radio pulsar. So I think at least for this very active fast radio burst, its underlying process is stochastic in time. So other than fast radio bursts, there are also other transient. One thing that has been looked at for a long time is planetary radio burst. So this is a little forecast that I co-wrote with Francis Zaka. The power, the radio power, are expected to be scaled with the incident magnetic power onto the planet. And so far there have been no confirmed direct detection of radio bursts from planet, but we are looking at brown dwarfs, which are perceived to have similar emission mechanism, but much stronger magnetic field. So during the drift scan survey, we estimated we may detect somewhere between 100 to 200 radio bursts from brown dwarfs. There's also the neutron star merger, the EM counterpart of this gravitational wave event. Its radio flux is very detectable by FAST. It's at the peak flux is about 1 millijansky at 3 gigahertz band. However, we are a single dish that are much constrained by confusion limit, which is also about 1 millisecond in our band. So this could be challenging, or we need a VLBI or interferometric concept. So this is my last slide. This is the commonly used phase diagram. The vertical axis is energy. The horizontal axis is the duration of the transient event times the frequency band. So it's a dimension is a number that roughly represent its time scale. So we can see this large blob of dots that are radio pulsars, and the right dots are new discoveries. And if you go up 8 to 10 orders of magnitude, there's fast radio burst. And there's the green dots, the galactic burst. There are 2 green dots, but they're basically one event. And we don't have any underlying physical reason to believe that there's this empty space on this phase diagram. So I think the major contribution expected for FAST in the coming years is to fill up this phase space, to discover more transient events that are still hidden somewhere in the universe. So, thank you.
Thank you very much. So is there any question or comment?
Well, splendid talk, very beautiful, and I'm sure there will be many questions and really unique development since Arecibo to this new fantastic telescope. And we all look forward for understanding the systems thanks to this new data.
Thank you.
If there is no further question. So let's thank Dee again.
Thank you. Yeah. Thanks
you.
for the opportunity.
So next speaker is Jianglai Liu, Professor Jianglai Liu. He's from Shanghai Jiao Tong University. He will talk about the latest progress of PANDAX, a deep and ground liquid xenon observatory. Let's welcome.
Thank you. Can you see my screen?
Yes.
Very good. Let me speak here to the deep underground. I'd like to first thank the organizer for this very nice opportunity for me to representing the collaboration. I actually changed the title of my talk into the first results of PANDAX photon. So this is a photon scale liquid xenon dark matter direct detection experiment. As you heard at this conference, after 100 years, it's ironic that there are still too many possibilities for dark matter, from black hole to particles to ultralight waves. Now I'm going to focus on only a certain type of dark matter candidate, namely the WIMP. Its detection has been outlined by Goodman and Wheaton some 30 years ago. However, still up to now, in the direct detection business, we have not seen convincing signals. On this picture, which is cross-section, spin-independent cross-section versus the dark matter mass. Actually, I borrowed this figure from the APAC report. You see all these exclusion limits, where you also see the so-called the ultimate neutrino flow. Now, at the large mass region, the front runners are 3 xenon-based experiments. And let me just bring your attention to the sensitivity of these detectors. All these, this upper limit or the sensitivity correspond, roughly speaking, to a few events. For every ton of target exposed to 1 year of exposure. Therefore, we are really entering the multi-ton era for the dark matter direct detection. Very quickly, let me go over the xenon TPC technique, which is used by all the xenon experiments. This is basically a tank of liquid xenon cooled at negative 100 degrees. You make it, basically it's a scintillator. Therefore, any energy deposition will scintillate. At the same time, some of the energy converts to ionized electrons. So the scintillation light is called S1. The ionized electrons get drifted in the electrical field upward into the gaseous region and get amplified to the second scintillation light called S2. A combination of S1 and S2 gives a reconstruction of energy, a reconstruction of position, and also if a background typically multi-scatters several times will end up to be multiple S2 signals that you can identify. Furthermore, for the signal that we search, the dark matter interacting with the xenon nuclear producing nuclear recoil, in comparison to the background, which is gamma rays kicking out the electron, producing electron recoil, the ratio between this S2 and S1 is a natural differentiator. Therefore, it's a good, provide a good rejection power for background. Now, let me talk about the 3 xenon experiments in the world. There's in the US Sanford lab, LZ experiments with 7-ton liquid xenon. In Italy, the Gran Sasso xenon N-ton experiment with 6-ton of the target. Both experiments are in preparation or under commission. So likely the results will also coming out very soon. So let me talk about the program in China, the 3rd experiment called PANDAX. Now the experiment is located in the China Jinping Underground Laboratory. This is in the south west of China, underneath a mountain, Jinping Mountain, with overburden of 2,400 meters of rock, the deepest underground lab. The phase 1 laboratory is a smaller space which hosts 2 experiments, PANDAX and CDEX, using 2 different methods to detect dark matter. And in the past few years, the 2nd phase of the Jinping lab, CGPL2, has been in partial occupation. This is a much expanded lab space with now 8 experimental halls, each with a dimension of 65-meter long and 14-meter by 14-meter cross-section. Currently, there are 3 experimental halls in occupation: Panda-X, CDEX, and the 3rd hall occupied by JUNA, which is the particle nuclear astrophysics experiment, which also recently completed commissioning. Now, for the Panda-X experiment, here is sort of the timeline. The collaboration was formed 12 years ago, and we have undergone 2 completed phases of experiments. The first phase of the experiment has 120 kilograms of the target. The second town, Panda-2, has 580 kilograms of the target. In particular, have produced several leading results on the dark matter direct detection. Now, since August 2019, the new generation of the experiment, Panda-X Photon, officially moved to the second phase of CGPL2. This is a recent picture of the collaboration. So we are now up to more than 10 institutions. This is a very young generation collaboration, very vibrant, with 70 people also. Let me just give you a flash of the recent results from the completed Panda-X2. In 2019, we finished the 130-ton day exposure. On the left, you see the final data sets, which increased by a factor of 2.5 in sensitivity for searching for WIMPs, but we have a bit worse than the upper limit because of the background fluctuation. Now, also, we in the electron recoil signal, we are looking directly for the solar axion signal and the anomalous neutrino magnetic moment from the solar neutrinos in light of the recent xenon 1-ton access. However, in this region, we are contaminated, data is contaminated by the tritium background, falling into the same region of interest, therefore with limited sensitivity, as you can see here. On the right, you see a new search using very low threshold data by giving up S1, but using the ionization only signal. Thus, we can push the energy threshold to 80 electron volts. Therefore, we can look directly for the WIMP direct scatter with electrons. And because of our threshold, we explore part of the region around 25 MeV in WIMP mass, which was previously unexplored. Now, let me now switch gear to talk about Panda-X Photon. This is an overview of the experiment. What you see here is a big water tank now acting as a shielding of the detector. At the middle of this water tank, you see a platform where the detector resides. This ultra pure water tank has 900 meter cube capacity. And at the center, the TPC, the time projection chamber, has a height of 1.2 meter and diameter of 1.2 meter, hosting 3.7 ton of liquid xenon. On top of the bottom, as usual, it's covered by roughly 400 channels of 3-inch photo tubes. Here is the major milestone for Panda-X Photon. We actually got the official permission from the CGPL management to start the construction in April 2018. And in the summer 2019, we complete a temporary infrastructure construction and detector installation was started. By March last year, the offline distillation of all the xenon that we procured was completed. And roughly 3 months later, the entire detector installation was completed. Starting from November last year to April this year, that was the period of our commissioning run, which I will show you some results. Here are some pictures of during the construction. These are early days in 2018. We are given an empty experimental hall, so everything has been started from scratch. This is showing the frame for the clean room as well as the crane. Here are the early stage of the water tank construction. This is a completed water tank with 13-meter total height. So here are the pictures showing the water purification system. This is the class 10,000 clean room where most of the instrumentation serving the detector is located. Here you see actually a 2-meter diameter acrylic window, and through which you can actually see into the water tank where the detector resides. This is the entrance to our smaller clean room plus 1,000, which we're all the TPC assembly happens. And to actually avoid radon contamination, the air goes into this class 1000 clean room were purified for radon. This is the most precious piece of the equipment, the gas storage system for all the 6 tons of liquid of gases, xenons. And this is the cryogenic systems serving the making sure the detector is cold. This is the krypton distillation tower, removing krypton from the detector. Here are some pictures showing the TPC installation. This is the TPC viewing from the front. These are the photo multiplier arrays viewing from the bottom. And this is a picture when the TPC gets rigged from top into the inner cryostat. This is showing the completed class 10,000 clean room. You see all the tubings, the circulation loops, the cryogenics. At the far end of this room, you see the full electronics where the phototube signals get bring out channel to channel into digitizers and get dumped direct to disk. And through this acrylic window, this is when we are viewing the water filling, which is during the summer of last year. Let me now talk about the some of the performance of the system during the commissioning. The cryogenics was very stable. In fact, the heat load of the system is only 50 watts. And the maximum cooling power by design was roughly 100 watts. So we are way over. We have 2 circulation loops trying to clean to clean out the electronegative gas, out gas from the detector with a rate of 40 kilogram per hour. So throughout the stable running period, taking apart the loop maintenance period, the detection was the detector is very stable with both the pressure and temperature stable within 0.5% and 0.1 Kelvin, respectively. Now this is showing something which has changed from the early version of Panda X. We now have an electronics system that does not have a trigger. So we are using much faster digitizer with 250 megasample per second, and every channel is read out separately. Whenever the signal is about a third of a photoelectron, we just read it. This is a typical single photon signal, so we read it out, no problem. The average single photon efficiency is 95%. Now the trick is that you have to dump the signal fast enough. The DAQ maximum bandwidth is 450 megabytes per second. So this page summarizes the TPC operation conditions. In between the anode and the gate, this is the extraction and the amplification signal for amplification region for S2. The gap is very small, only 10 millimeter. And then between the gate and this cathode, this is the drifting region with 1.2 meter of gap. And below the cathode, we actually have a 10 centimeter shielding region to remove the background, to suppress the background. During the running, it turns out that we have to set the high voltage of these electrodes at a few settings in order to avoid excessive discharge generated on these electrodes. But overall, in between for within these sets, the data is stable. This page summarizes the data taking history in terms of the electron lifetime. So it turns out the electronegative impurities during the drift can eat electrons while it's drifting. Therefore, we use a so-called electron lifetime to characterize the attenuation of the electron during the drifts. This electron lifetime is also in situ vertical uniformity calibration for S2. Now, overall, across the board, you see that electron lifetime is about 1,000 microseconds. In comparison, the maximum drift time for the TPC is 840 microseconds. Therefore, you can tell that from the top to the bottom, the uniformity for S2 is roughly, the difference between the top and bottom is roughly 2 to 1 or 3 to 1. In total, we have a stable data running period of 95 days in total. So just to show you some lower level data selection cuts. This is a well-known trick in the liquid xenon TPC that after violent events, there's lots of electron being generated, and the electron gets extracted much slower. Therefore, you have to reject some time. Here we have a 22 millisecond rejection cut after violent events, leading to roughly 7% loss of the lifetime. And we also have some cuts to remove the period when the single rates are unstable, costing about 2% of the lifetime. On the right, you see some lower level cuts event by event. Now this the upper cut is showing a cut for the top bottom asymmetry for the S1 signal, just to remove those spurious signal which could come from some accidental dark rate of one array and in random coincidence with, say, the other array. And on the bottom, this is showing a so-called diffusion cut. As the electron is drifting, the electron cloud gets widened, reflecting into a widened width of the S2. Therefore, as a function of drift time, you see this clear correlation. Now, applying this correlation can reject quite effectively those accidental backgrounds. The very important aspect of the experiment is calibration. Just as what the previous speaker talked about in the fast radio, we also need to have multiple ways of calibrating the detector. Now, we have three workhorses for the calibration. One is a gaseous source injection, where we can load in radioactive krypton and radioactive radon into a detector, and they are short-lived, but randomly uniformly distributed into the detector, so you can have very nice calibration of the energy response. Also, we have the traditional calibration loops, where a source can be going into these loops at different height of the TBC, calibrating the detector response. Lastly, we now have a deuteron-deuteron fusion generator for electron, for neutron. This produces semi-mono energetic neutrons, which are then beamed through a collimated beam pipe into the directly into the detector. So I'll go over these calibrations one by one. Now, first, the uniformity correction. Uniformity correction is important to remove the event-by-event fluctuation that's correlated with position. By doing, we load this krypton-83 metastable source into the detector, and you see that they're uniformly distributed into the detector with a characteristic 41.5 keV total X-ray energy. You see the S1 and S2 correlation with a very nice reconstructing energy with 70% resolution. So the uniformity for S2 and S1 can be calibrated. Just look at them across the board. For S2B, the RMS variation in the fiduciary volume is 12%. And then for S1, the RMS variation is 20%. Using the same data set, we can also look at another parameter, which is called the electron amplification, or in short, the single electron gain. Every electron being drifted out and amplified converted to a number of photoelectrons. Therefore, we're trying to calibrate this gain by looking at the smallest S2 signals, okay? And these signals can be fitted with a very nice Gaussian. They're uniformly distributed into the detector with a RMS variation of only 13%. The top and bottom ratio for these low energy S2s are also very stable. In the end, we determine this single electron gain to 4.6 photoelectron per electron. For the energy reconstruction event by event, we can use a linear combination of S1 and S2, okay? Given that you know the efficiency for detecting them. Now, these two efficiency correspondingly are called photon detection efficiency, PDE, or the electron extraction efficiency. Now, every energy point, gamma energy point in the detector can essentially be lined up onto a straight line. Therefore, you can fit for the PDE and EE. This is a standard figure, so-called Doki figure, that you can fit for these two nice parameters. And then just for the check, the reconstructed energy after applying these two fitted parameters is shown on this page. These points has been used in the fit, and then we use two more data points, independent data points produced by illuminating xenon with neutron and look at some de-excitation gamma rays from the xenon. And you see that they are also at the zero line, but with larger uncertainty because of these neutron, de-excitation energy contains some of the nuclear energy fraction, which causes uncertainty. In any case, you see these parameters are determined for set 1, 2, 3, 5. And also to check the stability of these reconstruction, we can look at another internal in situ calibration source, which is the activated xenon 131 metastable state. Well, after neutron bombardment of the xenon, some of these short-lived isotopes with roughly 10 days of the half-life will stay in the detector and decay away. But you see this 134 keV lines throughout the detector. This is showing their variation over time with a systematic uncertainty of 0.3%, which entered into the previous fit. So the other aspect of the calibration is to determine the low energy response of the detector, particularly relevant for the dark matter search. Now, the dark matter, if we interact with xenon producing a low energy nuclear recoil, the best calibration coming from the neutrons. Neutron hit on the xenon produce the same nuclear recoil. This page summarizing the nuclear recoil calibration with the DD neutron band. Now, DD neutron band, I said, generating a monoenergetic neutron, roughly speaking, 2.2 MeV. And then because it's beam, you should see a forward-going full head-on collision peak. On this picture, which is show the log of the ratio of the S2 over S1, a proxy of the energy. So these are standard bands you'll see later on. You see the distribution of the data points, which can be compared with a signal model. You see a 1D projection of the S2, where you see clearly data agree with the Monte Carlo, also with this head-on collision peak setting the energy scale. This data set is used in combination with the so-called MB data set, another neutron source, to tune all these parameters in the signal model, as well as the fluctuation in the signal model. This is a similar page showing a different neutron source, MB neutron source, where because of the broadening of the energy spectrum, it no longer is showing this nice peak. But again, you can look at the distribution as well as the projections to compare the data on Monte Carlo. Now let's move on to the electron recoil calibration. This is also critical to understand the majority of the background behavior. Now, as I mentioned, we use this injection panel to load in some of the radon isotope, radon-220, which has only 55 seconds of the lifetime. And then once they go in, one of the decay progeny, lead-212, is a beta emitter producing a flat energy spectrum at low energy. And these are how these beta events were distributed in the same band. On the same plot, you see the medium of the neutron calibration in this purple band, in this purple line. Now, one way we characterize the rejection power is to simply count how many events were leaked underneath this nuclear recoil medium line as sort of a measure for the rejection power. And here, out of 1,400 events, we see 6. Therefore, the rejection power is 0.4% with roughly 50% uncertainty. Here again, is showing a projection showing the data on Monte Carlo agreement. Using the same electron recoil nuclear recoil low energy data set, we can also determine the efficiency for both S1 and S2 selection. And for the calibration data set, they should be in common, and we determine them as these two curves. Now, using these two curves, we can also cast the efficiency as a function of the so-called nuclear recoil energy. Now, you see that at the plateau region, at 40 keV nuclear recoil, we have efficiency of about 78%. Let me now move on to describe the background. As you know, background is really the key for this business. Now, the first usual suspicious background is material background from the detectors. Here we bring our detector into several regions, top, bottom, the edge, as well as the center. They're sensitive to different kind of background and compare with the background model. Now, because of most of the background were produced by the gamma rays, which are MeV-ish, we compare mostly the integrated rates for these data versus model above 1 MeV. Overall, in these 4 regions, the agreement between the two is 14%. Now, on the other hand, converting all these high energy events into the low energy where the dark matter, where you mostly care in dark matter region, it's a minor background with 33 events. Now, the radon background is more more important because radon distributed uniformly into the detector, and they come out also through the emanation of a material through the material surface. Now, radons, on the other hand, can be identified quite easily through their decay progenies. There are very nice alphas that you can identify into the detectors, as well as some alpha beta coincident signals. So from these very well identified signals, we find that the radon rate is 5 microbecquerel per kilogram. Now, just compare this number per kilogram with that value we achieved in Panda 2, we improve 6 times. On the other hand, the radon level was in fact not stable during the commissioning run. You see that in one of the periods, set 4 had a higher radon rate. And the reason we know the reason is because we turn on the online krypton distillation, wanting to distill further krypton background as we're operating. However, we see that some radon gets emanated through the tower into the detector, setting up more higher radon background. On the other hand, by taking the difference of these background in these two regions, we can have a very model independent estimation of the radon background in the low energy region. Therefore, this is the extracted background in the dark matter region, 347 with a 60% uncertainty. Now, krypton, another noble gas, is another used to be a big problem for the early stage of Panda X. This was looked into through a traditional technique using the beta and gamma coincidence. So we see them very clearly in the detector. In the end, we only identify 4 of these events in the dark matter data set in the fiducial volume, translating to a 0.33 ppt krypton to radon, krypton to xenon ratio. This is improved by 20 times from Panda 2, actually also beyond our sensitivity to directly SE these radon background. Now this translates into a low energy background of 53 plus minus 34 events. Another noble gas, xenon 127. Now, the 127 normally do not have in the xenon, except that you expose the xenon to, for example, surface. Surface muon activate these xenon. Some of the xenon 127 was produced in electron capture. So they produce cascade gamma and X-rays. So through these very characteristic gamma X-rays, we can really track them in time. They are decaying away. Fortunately, there's only 36 days of the half-life. Now, the real background in the dark matter region is the 5 keV X-rays. The 5 keV X-rays, the K-shell X-rays. On the other hand, we can actually tag these backgrounds through the 33 keV L-shell electron, L-shell X-rays, and they are nicely identifying the detector to be this value, therefore converting into the 5 keV, it's only 9 plus minus 2 events. Now, notice that I intentionally covered the dark matter search window within 20 keV. So what's there? This is the spectrum that's during one run set. You see, on top of the normally expected flat background, we see something, a triangular shape of something. And this is, unfortunately, we know this is the tritium spectrum being identified from the data. Now, where do they come from? We actually think they are likely being originated from a tritium calibration at the end of the Panda 2, where we load a lot of this tritium into a detector, trying to calibrate the detector, and also trying to see how well we can remove them. Unfortunately, the removal is probably inefficient, leaving some of the residual xenon into our data. In our fit, we left this tritium component to be fit, to be float, and they actually translated into 10 to the minus 4 mole per mole concentration, a value that one cannot really see with direct SE measurement. Let me move on to one of the background, which is called surface. This is also related to the radon background. A lot of these radon has long-lived progeny attached to the wall of the surface. Now, these events can be clearly identified from the data by looking for example, a long-lived polonium alphas. They are close to the wall, and you can actually get both the position distribution as well as the S2 distributions and model its distribution, estimate how much of these background could leak underneath the dark matter search window. Another feature is that such background, now, after you build the model, we find that the lower you go into, you cut more into the fiducial volume, you see that the value of the S2 also becomes smaller. And this is also expected because the smaller S2 you will have worsened position resolution, make it more prone to be leaked into the dark matter search window. However, the expected background for these wall surface events is 0.6 plus minus 0.2 events. Now let me talk about the last one, the neutron background. This is used to be known to be really the enemy of the dark matter detection because it generates directly nuclear recoil. Now, however, these neutron backgrounds, once they enter into a detector, they could also multi-scatter and eventually get captured onto xenon, producing high energy capture signals. And both processes are benchmarked by our neutron source calibration as well, which I didn't have time to dwell on. In any case, we're searching our dark matter data set. We actually identify 3 multiple scattering events, and this can be converted into the single scatter background that's remaining in the dark matter data set. Similarly, we identify 30-some high energy neutron capture signal. This can also get translated into how many of the nuclear recoil, single nuclear recoil signals. In the end, the neutron background is 1.3 plus minus 0.6 events in the dark matter set. I forgot to mention the accidental background. This is really forming by an accidental, no correlation S1, S2, but randomly into the same drifting window, as I mentioned, because they don't have real correlation. So using cuts, for example, like the diffusion cut I mentioned, was very effective of removing them. Also, the distribution into our band is well known. The expected accidental background, in fact, was actually suppressed in comparison to the Panda 2 times. It's only 2.4%, 2.4 plus minus 0.5% events. Now, the final fiducial volume determination was actually a combination of the background from our previous knowledge, as well as the combination of the radon background and the tritium background that was measured in situ. So we used both components and try to define a figure of merit, maximizing the sensitivity. So you see that this is the best fiducial volume with, essentially R square versus Z, but cutting 2 corners to remove some of the background. In the end, NEM2 be 2.67 ton of target mass, and same cut was adopted in the real data. All right, so here is a recap of the background composition. This table recaps what I said in earlier slides. Now, for the radon, krypton, and the material background, on the other hand, although one could determine them individually, at the same time in the data, they can also be determined through the sideband using the data itself. So here I'm also showing the sideband determination of the so-called flat electron recoil background. Now, overall, you see that in the total background, it's the tritium, this from the actually fit to the data, and the radon, the flat ER background dominates entire budget. Now, on the right, this is showing the components that could leak underneath the nuclear recoil medium line. And you still see a dominance of the electron recoil background, and the rest of these background contribute to roughly 30%. In total, taking these table inputs, we find roughly we should expect 10 events plus minus 1. By the way, this background per unit target is improved from the Panda X2 by 4 times under 10 keV. Also impressive improvement. Here is the documented candidate after all the smoke clears. Again, in this familiar band plot. Now, there are in total within the window 1,058 candidates. Now, below this red line, we only identify 6 of these events. Okay. Of course, the real analysis has to be using all data, not just using the 6 data. But this, again, 6 data give you some idea of how data is distributed relative to this nuclear recoil medium. Here are the distribution of these events in R square Z and X and Y. You see that there are the above nuclear medium line, and also these 6 events underneath the nuclear medium line. They're all kind of uniformly distributed in the detector, no special features. Expected if everything is dominated by the tritium and radon. So as I mentioned, this 1,000 some events gets all fitted with unbeing likelihood fits, including both the signal background probability density distribution function in both S1 and S2. Okay, it turns out we didn't find an excess. The fit was actually very nice, consistently with the background only with a high p-value. Now, how does it agree in terms of spectrum? Here's showing this, the projection in the S1. You see that the tritium plus a flat ER, the data agree with the model also in spectrum. Here is showing sort of the likelihood of these 6 events. Just looking at these 6 events, what are quote unquote their component, or the likelihood of being individual background components. The light is tritium, this greenish is flat ER. You see that they're dominated really by a leakage of these electron recoil signal leaking underneath the nuclear recoil line. All right, let me summarize. Without seeing a trace of the excess, we're still able to put a bound on the WIMP nucleon spin-dependent exclusion with a 0.63 ton-year exposure. We have a sensitivity which improved from the previous PanDAX2 final analysis by roughly 3 times. Now at 40 GeV benchmark point. Now in comparison, our new results is red exclusion limit in comparison to Xenon Wanchang. You see that we are slightly edged Xenon Wanchang. For example, at 40 GeV, we are 1.3 stronger than the Xenon Wanchang limit. But Xenon Wanchang has a slight upward fluctuation. We have slight downward fluctuation. Now, lucky or unlucky, depending on your point of view. In any case, with this data, we definitely dive into previous unexplored territory. Just to put you into the stage, here are some SUSY contour plots given through these references. You see that we are going deeper. Also, if you look at sort of the low dark matter mass region, we're also cutting slightly into the low energy neutrino flow. This is also interesting. So with more data accumulating, we may also seeing the interesting neutrino coherent status signal from the solar neutrino. All right, let me quickly conclude and give you a quick outline. We, as I mentioned, have completed the first commissioning run with a 0.63 ton-year exposure. We were able to produce the first scientific results, putting the strongest WIMP and the nucleon interaction constraints. The paper will be in the archive shortly. In fact, this demonstrates the physics potential of a highly sensitive multi-channel liquid xenon detector. I didn't dwell on the neutrino part, but these large detectors will be more and more sensitive to neutrinos as well. Now, because the tritium is an issue, PanDAX is currently performing an offline tritium removal campaign, and our aim is to reduce the electron recoil background by at least a factor of 2. Now, in parallel, for the future, the collaboration is developing a plan for the next generation experiment and CGPL. So thank you very much for your attention. That's it.
Thank you very much for this very interesting view of all the new technology, very impressive that you are developing. And let's see if there are questions on the chat.
No, there are no questions on chat.
Well, then let's congratulate again.
Thank you very much.
Thanks.
Let me quit the sharing. Thank you.
Yeah, thanks.
Appreciate it.
Yeah, our next speaker is Marcus Aspel-Meyer. He will talk about gravitational cupping. Are you ready?
So, thank you very much. Yes, just need to share the screen.
Well, this is, we have to look with very much attention to the dimension of this experiment. Please show us as much as possible.
So you see, it's so small that you cannot even see it. No.
Okay.
Excellent.
We see it.
Very good.
See it. Thanks.
So first of all, thank you very much, Remo and the other organizers for having me. It's a real pleasure being here. And I also have to say I'm extremely impressed by the experimental progress that has been demonstrated here by the previous speakers. And I will introduce a change of scales now. So I will go to much smaller scales. So we will be looking now at several orders of magnitude smaller scales with respect to the experiment. We will be looking at tabletop scale experiments to actually probe gravitational forces of extremely small masses. So before I go into more detail, sometimes it's interesting to take an historic perspective of things. And it's quite interesting to note that if you go back to the early 1950s, that the situation of gravity back then, the gravity research, was less than favorable. And it was back then, many of you may know that on the initiative of John Wheeler and the De Witts, that a conference was initiated, the so-called Chapel Hill Conference, that discussed the role of gravitation in physics at that time. And sometimes this is also referred to as the GR0 conference. And with respect to experimental questions, there were two topics that actually stood out, that were discussed in detail at this conference in Chapel Hill. First one is, do gravitational waves exist? And the other question, do we require a quantum description of gravity? So now that, let's say, the first question is it's decisively answered now, after almost 60 years after the conference, I think we can now put our attention to the second question. So there are several approaches how you could probe the quantum nature of gravity. The first one is one that we heard also already in several talks over the last couple of days. We assume that there exists a quantum theory of gravity, and then we probe its consequences. Typically, we probe its low energy consequences because we don't have access to the high energy scales of the Planck energy. And those low energy testing those low energy consequences typically does not require by necessity measurement of gravity itself, but one looks at consequences in, for example, the dynamics of degrees of freedom of other systems, which can be, as I said, non-gravitational measurements. There are beautiful works here, for example, by Klaus Lemmerzahl, how this could work, and also in the context of solid-state mechanical systems, there has been some recent progress, and here you can find a couple of examples where people have studied both in theory and experiments the consequences on the dynamics of massive mechanical objects under the assumptions that some aspects of quantum theories of gravity holds down in the low energy limit. So for reasons of time, I will not go into this one, but I will focus on the second one. Okay? So the second possibility to probe the quantum nature of gravity would be to assume nothing at all and probe the consequences of a quantum configuration of gravitational source masses. And this, of course, requires gravity measurements, ideally at very small scales, because we will expect that having gravitational source masses as quantum objects will more or less require experimenting with small particles. So let's have a closer look at this second point. So first of all, let's ask the question, what about how do quantum systems react to gravity? I think it's well known also here in this community that quantum systems are extremely sensitive probes of all kinds of external fields, and in particular, of course, also gravity. There are many beautiful experiments, and all of them are very well understood in the framework of, let's say, in the most extreme case, quantum field theory in space, in curved spacetime. And I just give you two examples here, both in a more or less Newtonian framework. So in the one case, this is the famous experiment by Colella, Hauser, Overhauser, and Werner, also called the Cow experiment after the initials of the authors, where they test the effect of Earth's gravitational field on the wave packet, so the quantum wave packet of a neutron. And what they do is they prepare a neutron in a superposition by splitting it here at a beam splitter inside an interferometer. And the wave packet acquires, while traversing through an external gravitational field, a dynamical phase. And once you have the neutron in a superposition, what you actually collect is the phase difference, because that's the only thing we can measure in quantum physics. And after recombining it, you get an interference pattern, and depending on the height difference in the gravitational field of the interferometer, you get different output, and therefore obtain here gravitation-induced interference fringes that are due to the impact of Earth's gravitational field on the wave packet of the neutron. There are other beautiful experiments, like here in the group of Dave Vineland, where they probed the gravitational redshift on an optical clock in Earth's gravitational field by lifting the whole experiment in their their lab in Boulder by 30 centimeters and observing a shift in the frequency of the optical clock. So this was more than 10 years ago. By now, optical clocks are even more sensitive and can measure gravitational redshifts, frequency shifts in optical clocks down to the centimeter level in Earth's gravitational field. So again, the point I would like to make here is using quantum systems as probes, or if you may, as test masses in external gravitational fields is well established and with beautiful results, and in the domain really of precision tests of gravity using quantum systems. Now let's turn it around. A question I would like to ask is, can we imagine having quantum systems as gravitational sources? Yeah, so what does that require? And what are the consequences? Again, an historical side note, these are of course questions that people have been addressing before. Most prominently, I take here two examples. At the Chapel Hill conference, this question was already addressed by Feynman, and other well-known scientists like Bill Unruh, for example, have been working on these questions. So we would like to ask the question now, not how does a quantum system react to gravity, but how does gravity reacts to the presence of a quantum system. So if you briefly focus on this Gedanken experiment that Feynman presented here in the 57 Chapel Hill conference, the idea is a very simple one. So the idea is, let's assume you have some sort of Stern-Gerlach device, which is a device of which we know that we can prepare an object in a superposition in space. So it behaves as if it were in two places at once. We have a coherent superposition of this object, let's say here, being either up here or down here, right? So we have actually now position states up and down, and this thing couples now to a second object that is separated from the first one, and basically, so this is our source mass, and this would be our test mass, and we allow only for gravitational coupling between those two systems, the one being a superposition. So what happens as a function of time, of course, is that you see this one will be attracted more here, this one here. We have a superposition of the two possible states of the object, which means that after some time the system evolves, we will actually get an entangled state with the upper one is now related of the source mass is now related to a, let's say, upper state of the test mass, and the lower one of the source mass will be correlated to a lower one of the test mass. And this is actually an entangled state. So the point is that starting with a source mass in a superposition state by just the laws of quantum physics will create via gravitational interaction entanglement between these two objects. Now, from a quantum perspective, by the way, this is a more or less trivial statement. Of course, if you have two objects and you start an interaction, then you will generate entanglement. From a GR perspective, this is far less obvious, because from a GR perspective, if you think about geodesic motion in a fixed spacetime metric that is given by the source mass configuration, whenever you start out with a separable state between the source mass and the test mass follows a geodesic in this in the metric given by the source mass configuration, you will never be able to generate entanglement. So the generation of entanglement requires that also the spacetime metric is in a superposition in order to generate entanglement from a previously separable state. This is something that Christodoulou and Rivoli pointed out in a recent nice paper. Now, let's now do a sanity check. So the task that is set out is it possible to use quantum systems as gravitational source masses? So let's check the landscape of quantum systems, and let's and compare it with the landscape of gravitational measurements. So what I have here is sort of a plot where I compare here coherence times in experiments versus the mass being used in experiments. And I split it into a gravity world where basically the notion of coherence times doesn't make sense. And what the plot here is essentially what are the size of source masses for which a gravitational field has been measured in the laboratory. On this side here, the quantum side, I actually look at experiments where people have prepared quantum superpositions of center of mass degrees of freedom of massive objects and compare their coherence time versus mass. I'll come back to this plot in a second. So let's just first stick to the gravity case. And as you can see, still up to last year, the smallest source mass that was used in experiments was on the order of a gram, also in tabletop experiments. So there were two beautiful experiments, one by Mitrofanov back from the 80s. These were inverse square law tests of gravity, and recent experiment by the Edelberger team and the Earthwash experiment. Now, we asked the question, well, how small can we go? So can we, because you see the goal is now, of course, essentially somehow to push those two domains together. So can we actually have objects, quantum systems with long coherence times and large mass, where the mass is so large that we can exploit its gravitational field in experiments. So this is why the task is to bring these two domains together. So we want to push the right sides to the left to lower masses. We want to isolate gravity as a coupling force for as small object as possible. And at the same time, we want to push quantum systems to larger masses such that that we come in this region where we can then exploit gravity as a coupling force. So in other words, the two questions that we have to address is how massive can we make a quantum system? And on the other hand, how small can we make a gravitational source mass and still isolate gravity as a coupling force? Let me first focus on this first question. How small can we make a source mass? So we started out with the idea that when we have small source masses, we can of course manipulate it more easily. So we have a source mass here, and so here's our source. And the idea was to essentially modulate the position as a function of time, and you can do that on larger time scales, typically for small source masses. And of course, what happens is then here on the test mass side, you produce time varying gravitational potential here. The test mass will be rung up, so we'll experience a time dependent acceleration, and this can then be measured in an experiment. At the end of the day, what we ended up doing was essentially a miniaturized Cavendish type experiment where the test mass was part of a torsional balance oscillator, the position of which was read out via here just an optical lever. The source mass was a gold mass attached here to more or less a motor where which we could displace. And the idea is now, of course, you see when you displace the source mass here, you modulate it, the position as a function of time, then you generate a time-dependent gravitational acceleration for the test mass. Because of the nonlinearity of the gravitational potential, you not only have a linear response, but you also get a quadratic response of the system. So you would expect that the test mass oscillation not only has signatures at the modulation frequency here, but also at double, triple, and so on of the modulation frequency due to the nonlinearity of the gravitational potential. The few parameters, so the mass that we use is in the order of 90 milligrams. This is a gold mass. The modulation is on the order of a few millimeter of the source mass, and the minimal distance between the source mass and the test mass in our experiment is on the order of 400 micrometer. There's a Faraday shield in between to prevent electrostatic coupling. The overall acceleration modulation that we obtain with this parameter set is on the order of 10 to the minus 10 meters per second squared, or 10 to the minus 11 G. So what are the challenges in such an experiment? As you can imagine, what we want to measure here are small displacements in the torsional oscillator, small accelerations of the torsional oscillator. So typical displacements here due to accelerations of that size on the order of a few nanometers. So you need to shield your whole experiments, of course, against external influences. The most relevant one is, of course, seismic noise. And you see here an example of our torsional pendulum with the test mass and a counter mass here. It is suspended with a small tapered optical fiber. And what we see here is measurements of the frequency noise, so amplitude and frequency space as a function of time. You can see dark is nothing, and yellow is there's a lot of large amplitude in the response. What you can see is there's well-defined stripes here. So there's a strong response on the order of 10 to the minus 2 hertz, so 10 millihertz. And this coincides very nicely with the traffic light cycle of the road crossing that is approximately 100 meters away from our lab. So trains and cars stopping, passing, and so on. And higher orders of that, of course. And what you can also see is there are stripes where there's essentially nothing. Okay, this is where the tram traffic stops. So which leaves us with a couple of hours during the night where we have extremely low noise. But you can also see the coloring is not uniform. You always have 5 dark stripes and then 2 more yellowish stripes. And these are actually Friday, Saturday nights where people are on the street, are going out, partying, and so on. And only Sunday nights it's quiet again, and people stay at home. It's also a very sensitive measurement for not only for the tram traffic, but also for the Vienna City Marathon, we found out. So actually, we were very sensitive to the first finish of the Vienna City Marathon, which happened like 2 miles away from our experiment. Now, there are also other things to consider. We have something like Newtonian noise. So what we did was we projected the Newtonian noise. You can see an image here. Here's our lab. Here is actually the road. So this is the road crossing that I was talking about that produces seismic noise. We also projected by GPS trapping of the tram traffic. All these purple things here are tram stations. The Newtonian noise due to the gravitational field generated by the Vienna trams, they are 90 tons and they actually pass by our lab here in a 60-70 meter distance. And it turns out that the Newtonian noise, the projected Newtonian noise is not negligible. It's actually quite, and it's on the same order of magnitude as the signal that we expect from our small source mass at our test mass location. However, since we do have a torsional pendulum configuration, the gradient at the location of experiment is negligible and does not couple in our torsional mode. But if you would use another configuration other than a torsional configuration, you would actually be limited by Newtonian noise already at that level. So last but not least, I would like to point out to you that this experiment was designed as a proof of concept experiment and not as a. So we did not, from the beginning, try to minimize systematic influences. We took great care of characterizing our systematic influences just to make sure that we understand what's going on. And of course, our next steps in improving the experiment is not only going to smaller masses, but also improving our handle on optimizing the systematic influences. So we have not corrected the data for the known systematics. We have simply tabularized our known systematics. And well, as you can see, the biggest uncertainties, they come from the usual suspects. So the mass distribution, so density inhomogeneities, and actually geometric inhomogeneities in the particle, the distance measurement, electrostatic, some gravity corrections, and so on. So in summary, what we observe now, so here you see the displacement, so the amplitude spectrum. And this is the test mass oscillator, and with its resonance frequency. Here you see the modulation frequency of our source mass. We drove the system of resonance, and you see that our test mass is close to thermal noise limited, and the red curve here is our force signal. The yellow is the force residual. So you see very nicely that we observe a linear acceleration modulation here at the modulation frequency, and also a quadratic acceleration at 2 times the modulation frequency. The third order is hidden in noise at the moment, and all of that is produced now from our 90 milligram gold source mass. The acceleration modulation that we resolve in this experiment is on the order of 10 to the minus 11 G. The accuracy is 10%. This is our systematic deviation, and the precision is on the order of 1%. So that really means we have a precision of experiment after 30,000 seconds of averaging of 10 to the minus 12 meter per second squared. As I already mentioned, so the systematics here is on the order of 10%. We understand them very well. And the observed value that we have deviates by the co-data value by 9%, but this is within the known systematics of our experiment. And again, we did not correct for the systematics. If we would do that, then these would sort of coincide with a large error. Okay. So at the end of the day, what we managed to do here is to isolate gravity as a coupling force for a gravitational source mass as small as 90 milligram, which means that if you look at our plot here again, so we sort of expanded now this domain, so down into this in this regime here. So we're now at the level of around 10 to the minus 6 kilograms. And our next step, what we want to do is we want to go to smaller masses. We would like to jump the next 3 orders of magnitude, which is then on the order of the Planck mass for our source. So let me now come to the second part, which is this one, the quantum part. So how massive can we actually make a quantum system? And as you can see here in this plot, you already see a trend. You see there are beautiful experiments in quantum physics with small particles like atoms, or even from a quantum perspective, macroscopic particles like molecules. So they contain like 10 to the 4 atoms. And they have extremely long coherence times. These are free fall molecular beam experiments with seconds of quantum coherence time. What you can do is now you can try to increase the mass. But right now, the experiments where the mass is increased, they go to solid state systems, and you see the coherence time goes down dramatically. So somehow we need to increase the mass in order to become gravitationally relevant, so to become relevant for gravitational source mass. But somehow there seems to be this trend that when you increase the mass in an experiment, the coherence time goes down. Okay, and I can show you here. These are 2 examples of current experiments that involve the delocalization, also large superpositions or superpositions of massive objects. Here's the experiment that I just showed you. This is the experiment using macromolecules of my colleague in Vienna, Markus Arndt. So they're holding the world record of the largest superpositions in quantum experiments. They have these large molecules with typical superposition sizes larger than a few hundred nanometers, so much larger than the particle itself. So the particle really is driven into a superposition of being here and somewhere here, really macroscopic. On the other hand, you have these solid state devices. Here's a nice example from Andrew Cleland's group back then in Santa Barbara, where they have this solid state mechanical resonator, and they have thickness oscillations of this bulk of mass here that contains 10 to the 13 atoms, and they can produce superpositions of this thickness oscillations, which puts the atoms, or the center of mass actually of the atoms, in superpositions with sizes on the order of 10 to the minus 16 meter. So you see there's a trade-off. You can either have right now in experiments large superpositions and small mass, or large mass and small superpositions. So in both of these experiments, although they're totally different, the product of mass and delocalization that you get is on the same order of magnitude. And it's actually this one that is relevant for the Feynman type Gedanken experiment. So what we are pursuing at the moment is we try to sort of combine the best of two possible worlds. That's on the one hand, we have the large mass of solid state devices. You have lots of atoms crammed into the smallest possible space because you have the high solid state densities. And on the other hand, you have this method of matter wave interferometry, free falling molecules with long coherence times. So what we try to do is now we try to combine these two methods by having free falling solid state objects. And the way we manipulate them is we trap them in optical or magnetic traps. And in that case now, we want to achieve trapping of solid state objects with high densities, large number of atoms, gravitationally relevant at some point, and we control them by means of quantum control techniques inside these traps. And then we can, of course, also, we can manipulate the traps, we can switch them off, have free fall, so we have a high degree of flexibility here in the potential landscape that the particle sees, which is relevant then for quantum experiments. So I just would like to give you one example before I end. So how do we make a quantum object out of a solid state sphere? Okay, so here's an example. The solid state sphere is a glass particle. So it's a silica particle, 150 nanometers in size. So that's a billion atoms inside this thing. Okay, what you can do is you can use tricks from optical trapping. You can use just a focused laser beam to trap this particle, so levitate the particle in front of a microscope objective. This whole configuration is inside vacuum. You can use the light that is scattered off the particle to read out the position X, Y, Z, and feed back this information about the position again to the light that is used to trap the particle to stabilize its motion. In that way, you can trap this particle at very high, very low pressures. So down to, as you can see here right now in experiments, 10 to the minus 8, 10 to the minus 9 millibar. The next thing you do is you use a microscopy technique to read out the position of this particle to the best possible extent. And the best possible extent is actually a measurement being limited by the Heisenberg limit, okay? And so what we do is we use confocal backplane imaging to read out the backscattered light here in a homodyne measurement. And the point is that this confocal backplane imaging allows us to have a sensitivity in the readout that is limited by the Heisenberg uncertainty relation. So the product of uncertainty in the imprecision of the measurement and the back action onto our measured object due to, in that case, radiation, so quantum fluctuations, which is shot noise in our laser beam, is very close to h bar, only 1.7 times away. So we are reading out now an object in a room temperature environment, solid state, so macroscopic object at the Heisenberg limit. This is and this allows now, once you have that, with a good state space model, also known as Kalman filtering or Wiener filtering, this allows you now to extract the position of the particle in phase space with a precision down to the quantum ground state fluctuation. So we can monitor in real time the quantum trajectory of the particle in the moving in a room temperature environment. And of course, once you can monitor the quantum trajectory in real time, you can also use a feedback. And in our case, this is all established on an FPGA board, feedback to now tranquilize the motion and stabilize it in its quantum ground state. And this is what we've been doing. So we read out, we measure the particle at the Heisenberg limit. We have a state space model that allows us to obtain the quantum trajectory, and that we use in a feedback loop to cool the particle to its quantum ground state of motion. And what you see here is actually, this is an image of our 150 nanometer glass sphere, cooled to the quantum ground state of motion in a room temperature environment. So you see here an actual image of a quantum object in our experiment. Now, I just mentioned in passing, there are other ways to obtain ground state cooling, so to prepare our objects in a quantum state. So there's another method that we have developed together with Vladan Vuletic and used, which is laser cooling methods from atomic physics, where we use scattering into an optical cavity to remove the motional energy of the particle. So finally, of course, in the long term, what would you like to do? What we have done now is we have prepared a pure wave packet, pure state wave packet of the particle. So we have a quantum object, if you want. However, the wave packet size is, of course, still much smaller than the particle itself, because the ground state wave packets are extremely small. They are, in our case, like a few picometers compared to the 200 nanometers of the object. So what you would like to do now in the next step is to increase the size of the wave packet, to coherently expand it to larger than the particle size. So is it possible to have wave packets, so quantum distribution of the objects that are larger than the objects themselves? So for example, you could switch off the trap now and have coherent expansion of the wave packet. And for our specific example, already after some 10 milliseconds, you would have a wave packet of the size of the particle radius. And once, of course, you have large wave packet sizes, you can also start to think about methods to manipulate this wave packet in such a way that you create coherent superpositions, which would be the starting point then for addressing the question, can we now use that to employ gravitational coupling to another object? Okay, so this is essentially what I wanted to tell you. You may ask, well, optical levitation, you are bound by the wavelength of your laser, so you only have 100 nanometer objects. Can you go larger? Yes, you can. So we have also a team working on superconducting levitation. So these are thin lead spheres on the order of the Planck mass, so 100 micrometer, that are levitated in an anti-Helmholtz coil configuration. So you have here the anti-Helmholtz coils, the particle is levitated in a dilution refrigerator, so at ultra low temperatures, and the motion is coupled to a SQUID, so a superconducting quantum interference device that allows us to read out the motion and characterize the system. The whole thing is inside a dilution refrigerator, where the whole experiment is actually suspended again here from 2 wires for vibration isolation. And we already have first promising results. So we see amplitude damping times on the order of 10 to the 4 seconds and dephasing times, which will be the relevant ones for quantum experiments, on the order of 80 seconds, and all of that in a 20 millikelvin environment. So this is a very well shielded environment. So this is my end. Of course, finally, you may ask, okay, but what is the actual limit for increasing the mass? And well, the answer is decoherence. Okay, so if I go back to Feynman's Gedanken experiment, there are right now in the literature several proposals how one could possibly implement that, how one could actually have 2 quantum objects interact with each other via gravity. And in all of these cases, you can compute then the rate at which entanglement is generated. And well, you see here's the m times mass times delocalization. But at the end of the day, this rate, of course, needs to be larger than decoherence rate. What is decoherence rate? This is the rate at which information about the position of the object is transmitted into the environment. How can that happen? Well, this can happen through scattering with gas molecules in the background. This can happen through scattering of black body photons from the environment, or by emission of black body photons from the object itself. So all of these are sources, one can compute them. There is a whole bulk of literature on how to compute them. And I just give you a few numbers to get a feeling for it. You see, for our glass sphere, if you want to get a large delocalization for experiments, you already see for black body radiation, you need both the particle and the environment at low temperatures. And the delocalization needs to be 6 orders of magnitude larger than the ground state size, which is something that has not been done yet and is going to be a huge experimental challenge. And well, you can go on for larger and larger masses. You see temperature remains the limit, and the fact that you need to delocalize your initial ground state wave packets to a large extent. And these numbers here are already done for preparing ground states with very low occupation and working at ultra low pressures. So I wrap up. Here's my summary. I wanted to show you the challenges in bringing together 2 domains. First of all, the domain of gravitational measurement, gravity measurements of objects of decreasing mass, smaller and smaller masses, with the explicit question, how small can we make a source mass and still isolate gravity as the relevant coupling mechanism? And on the other hand, can we increase the mass of quantum systems to the extent that they can produce a gravitational field that we can eventually measure? I have shown you that right now in a top-down experimental approach, we have demonstrated gravitational coupling of millimeter-sized particles, like our gold sphere. That's on the order of 10 to the 21 atoms at the moment, like 4,000 times the Planck mass. And we have in our lab on the quantum side, solid state particles with 10 to the 9 atoms that we have prepared in the quantum machine. And now our huge challenge for the future is to basically bring these two domains together. Thank you very much for your patience and attention.
Very, very impressive. Let's see if there are questions. And
may I ask a question?
Please.
Hi, Klaus.
Yes, Klaus. Very nice talk. Do you believe that the quantum mechanics has an intrinsic length or mass scale where quantum mechanics ends to be valid?
I would be surprised, to be honest. Yeah, I mean, this is of course, a very Viennese perspective, I admit. But somehow I have to say that quantum theory is a different perspective on nature, and I would find it hard to believe that this, let's say, new perspective that basically we have to now talk about what we can say about nature, right? So we basically, quantum theory provides statements about probabilities of measurement outcomes. It's such a radical departure of other theories that I would find it hard to believe that this is not a more universal principle that has to be applied also in general to the way we talk about nature and science.
Yeah. Mm-hmm. Yes. Okay.
Marcos, there is a question in Q&A. Could you please read and answer?
Yes, there is one by Jan Novak. There was an experiment where tested quantum states of neutrons in fixed gravitational fields. Now I cannot read the rest. Are there any advances in these types of experiments? Yes, very briefly to that. These are wonderful experiments, some of them performed by my colleague Hartmut Abel in Vienna, where you look at gravitationally bound states of neutrons. So the main idea is, if you have a neutron, you reflect it, you drop it and you reflect it from a surface, then it propagates in Earth's gravitational field against the gravitational potential. So if you then plot the potential landscape, so here as the height set, okay, and here the potential that the neutron sees, then what you have is actually here's the wall that the particle hits, and then when it propagates against the gravitational fields, then this is the gravitational potential. So what you have is actually now as a potential landscape a particle in a box. So you get quantization again of the energy eigenstates of the neutron, which means you will only find the neutron in well-defined places above Earth's surface. And the interesting part is now you see these are well-defined energy eigenstates, and you can now drive transitions between them. You can actually now, so what are transitions in atoms? How do you drive Rabi oscillations in atoms? What you need is, you need a little disturbance, a periodic disturbance from the outside of the coupling to the energy gap here. In atoms, these are electronic energy states of the electrons in the Coulomb potential. So you need an electromagnetic disturbance. So you have a laser light that introduces then transitions of the energy eigenstates of electrons. In this case, this is actually, you see, this is the gravitational potential, and this is the height above the surface. So it's enough to just shake the table on which your experiment is placed in order to drive Rabi transitions between these energy eigenstates. This is totally beautiful. And now you can do spectroscopy of this potential landscape. And this now allows you also to bound possible modifications here to the gravitational potential on a very small length scale. So they use this to confine some axions, pseudoscalar axions in their experiments. And there are updates to these experiments where actually the energy sensitivity, the energy resolution that they have is now much better. I think they improved that by 1 or 2 orders of magnitude, and this was just recently published. And there's one more. Oh yeah, fun question. You're able to get accelerations of 10 to minus 10 meters second square according to Mond. So modified Newtonian dynamics, there should be deviation from Newton's law at accelerations of about 10 to minus, about that order of magnitude. This is something that you may be able to measure. So there is literature about that. So one should say Mond is essentially a modification of Newton's second law. So basically you just, not only of gravity, but really it tells you whenever you want to measure small accelerations, you have to add, or you should add, an additional small acceleration to it. So in that sense, of course, once you have an experiment that is sensitive to small accelerations, in principle, there should be the option. But of course, you need to remember that our lab is actually accelerating towards the sun quite fast, actually. So we have and the solar system accelerating again. So we have actually we have extremely large accelerations in our experiments that typically makes Mond tests on Earth-based tables not viable. This is my understanding. I know there are some suggestions how to circumvent that, measuring at different points, different days in the motion around the sun, but yeah, so one has to be careful. But in principle, the sensitivity would be large enough. I agree.
Excellent. Maybe we can move to Klaus' talk now. Klaus, are you
sharing?
Okay, yeah. I will share my screen. Can you see the file?
Yes.
Okay. We'll come back again in a minute, in a second. Okay. So thank you very much. So I'm now leading this highly fantastic and interesting regime of testing gravity, the gravity and quantum regime together. I will go back to classical tests, and this is mainly about test of the Equins principle and the gravitational redshift. I will give some introduction to general relativity and how it is built up. Then I go to all the tests, and I will highlight the test on the Equins principle and on the redshift with Galileo and the microscope satellite. Then I discuss a bit whether a newer clock effect might be measurable, and then I come to a summary and outlook. So gravitational, or our theory of gravity, general relativity, may be derived, for example, by this axiomatic approach by Ehlers, Pirani, and Schild. the nice thing about that is that it is based on operational axioms. Each of the axioms you really can test in the lab. For example, you have axiom on light. That's mainly it is the uniqueness of light propagation. Of course, you can test whether there are 1 or 2 light rays in one direction at one instant. Then you would have birefringence, but this never has birefringence in the vacuum. But this never has been observed. So from that, we can then conclude that locally we have as conformally coherent metric, and locally, so to say, the main structure of special relativity shown here on the right-hand side in the slide cone here. And all the tests are of the order of 10 to minus 15 to 10 to minus 30, so this is very well established. The next is the University of Free Fall in this axiomatics. So this mainly by mathematical operational reasons designed axiomatics is really connected to real experiments. And now the other basis of the general relativity is the University of Free Fall, the weak occurrence principle. The best test in the lab was by Schlamminger in the group of Edelberger with the equilibrium quotients smaller than 10 to minus 13. Now in space, we have an improvement of eta better than 10 to minus 14, and the complete data analysis is not yet completed. There are also tests with this particles with spin for charged particles. They are much more difficult, and so the result is not as good. And we are looking forward to have tests of the equivalence principle with antiparticles, for example, with anti-atoms, making atom with interferometry with anti-atoms. Then we have, of course, to look for the compatibility of the motion of massive particles and light propagation, that there's no superluminal velocity. This then gives a compatibility between this free fall of material particles and light, and that the requirement is that all the particles have a velocity smaller than the velocity of light, and this has been tested in the lab with a precision of 10 to minus 6, and with astroparticles up to 10 to minus 21. And then there's finally a last question, which is mostly related to the nucleus of the gravitational redshift. This gives a scale or a uniqueness of the scale here in this axiomatic scheme. If you have one clock and you construct a duplicate and then move them along two paths and bring them together, then you may have two clock effects. One is the twin paradox, which is of course there and very well established, and the other might be the second clock effect, that the clocks tick in a different way. And this has never been observed. This is so to say the content of the local position invariance. And if you require that, and for that, the best test is of the order 10 to minus 7, with a long-term observation of a variety of clocks at an institute in the US. And if you take everything together, then this is then the Einstein equivalence principle, and together this gives in a kind of mathematical proof that we have that the underlying geometry has to be a Riemannian space-time given by a space-time metric, and from that we can then reformulate the equation of motion of particles of light, derive the curvature, and then have all the framework for doing general relativity. What is not yet clear is how to postulate or how to found the equation, the Einstein field equation, on an axiomatic basis. There are the PPN formalisms, there are other formalisms, and each of them work, of course, but they are assuming from the very beginning some additional effects which they do not formulate how this could be tested in experiment. So for this part of gravity theory, no constructive axiomatic approach is existing. But of course, there are several parameterizations of deviations from that, which are very, very helpful. In a historical timeline, so we had Newton and electrodynamics and non-compatibility, then gave special relativity, the non-compatibility with Newton then gave general relativity, and now we are asking for the resolving the non-compatibility between general relativity and quantum mechanics. And I think it's really a triumph of Einstein that he really made these two conclusions here and just looked for a compatible formulation of the theory, and that this has been proven, or the motivation for that was, of course, given from the structure of the theory, and the experimental basis was in the solar system with this very, very tiny effects, but nevertheless, he predicted black holes, and today black holes are now real. And this is really, really a triumph of theory here. And so there are other issues which has to be tested. This is the structure of the Newton potential. So there are one kind of parameters, and this is related to the question of the field equation. These are just two aspects. I will not go to all this PPN parameterization. So here we have the Yukawa parameterization of deviations from Newton potential for large scales, for small scales. Here the satellite test and lunar laser ranging gives the best experiments, and here all these small scale experiments up to a micrometer distances are also giving nice results. But here it is interesting that theory, higher dimensional theory, string theory, and so on, predict deviations from Newton's law at small scales. There are also ideas, different deviations proposed in the framework of the Kosteletsky standard model extension. These are deviations from the rotational invariance. So we have an isotropical addition here, and this has also been tested by atom interferometry and by lunar laser ranging, and the estimates are given here. I'm also very often looking for the real basics, and one of the real basics is the question of actio equals reactio. So one other has to look, so to say, at the full range of the Newton axioms, how they are founded. And there was a proposal, goes back to Bondi, to introduce 3 masses for each body, and these 3 masses are really realized, operationally realized in completely independent way. So the inertial mass is the resistance to be accelerated. The gravitational mass, the passive gravitational mass, is, so to say, the weight of the body. And then the gravitating mass, this is the mass, the substance which makes the gravitational field. These 3 masses are completely independent from each other. When we are introducing them, so inertial mass is here, active gravitational mass makes a gravitational field, passive gravitational mass reacts on the gravitational field. And if you are now analyzing this two-body problem in a Newtonian way, of course, then we see that there will be an acceleration of the center of mass of the system if you introduce the center of mass in the traditional way during the inertial masses, which can be defined experimentally. Then we see that the center of mass will be not constant. So there are a self-acceleration of the center of mass, and this is, so to say, a violation of the principle of actio equals reactio. If this is equals 0, then the statement is that masses of the same weight also creates the same gravitational field, independent of their composition. And this is another equivalence principle on the same level, in my opinion, as the equivalence of the inertial and passive gravitational mass. There were also experiments for that in the lab by Kreuzer in the group of Robert Dickey. So there the idea was he has 2 masses of different composition, of the same weight, and he looks whether these two masses create the same gravitational field. So there's a torsion pendulum, which which reads out the strength of the gravitational field, and if the red mass creates a stronger gravitational field, then this should start to move, and he interchanged these masses, and then the torsion pendulum should start to move. Since here are moving parts, the accuracy is not as precise, but nevertheless they reach an estimate on the C12 of the order 10⁻⁵. There's also an experiment with the lunar laser ranging. So the moon has a silicon mantle and an iron core, and this is, they do not have the same center of mass, and so can be thought as being composed of two masses, a silicon mass and an iron mass, and the line of the two center of masses are here given by S as a certain orientation with respect to the Earth, and then one can calculate the self acceleration of this of the center of mass of this system, and this depends on the self acceleration which is here really active is the horizontal self acceleration. This accelerates really the moon. And this then would lead to an increase of the angular momentum, which then would lead to a larger distance of the moon with respect to the Earth. And this has not been observed, and lunar laser ranging is very precise, as we know, so that they could arrive at an estimate of this on the level as the usual occurrence principle. This might be improvable by new lunar laser ranging and moon orbiter data. This gives a better model for the interior of the moon, and they are improving the measurements principle here. Okay, now I will also give some theoretical construction here, which are important for the following. So general relativity tells what is a good clock. Yeah? This has been, for example, worked out by Volker Perlich, and the idea is that if you have an observer and a particle passing the observer, and you measure the distance by means of light ray. Yeah? You have light rays sent from the observer to the particle, and this will be reflected. So by means of and this then gives a certain parameterization here. You can use this here as a parameter, or you can use this, and now one can require that if the particle is freely falling, that all the accelerations of all the freely falling particles should be the same. So from this distance, one can derive the relative velocity. From that, one can derive the relative acceleration. And this acceleration is the same for all the particles, only for a certain parameterization of the auxiliary clock here. And this clock then shows the proper time as we know it. And with this proper time, one can define a proper distance, of course, and also rotation can be defined by means of the Pirani bouncing photon construction. You have a central particle, two auxiliary particles, light rays going between all these particles, always hitting the particles. So at least the auxiliary particles have to be adjusted in their orbit. And then this defines a spatial distance, a spatial direction. And the spatial direction then is called non-rotating by definition. And this agrees with all the kinds of rotation we are used to define. Okay, so deviations from this non-rotation then will be called rotating. Okay, and these clocks are standard clocks, and it can be shown that atomic clocks are really standard clocks. Yeah? So it has been shown by Parker and Pimentel that, for example, the influence of gravity on this clock is of the order curvature tensor times the Bohr radius squared. This is of the order in the frequency rate in the relative frequency of the order 10 to minus 42, which is of course far beyond experimental reach. Nowadays they are at the order 10 to minus 18, approaching 10 to minus 19. Only near to astrophysical black holes, atoms lose their property to be standard clocks. And these are the clocks which are taken to define the gravitational redshift, gravitational time delay, and other effects, and also all these special relativistic clock effects. So everything is very well defined in terms of the theory. There's no additional input in our notions. Okay, so this is then our result. So we have the Einstein field equation, the equation of motion for point particles. There's also, of course, a huge industry for deriving equations of motion for extended particles. And we have the standard clock, which is given by the proper time, which is again given by the geometry of space and time. And now one can derive or formulate and derive all these effects and tests. So the deviation of light, gravitational lensing, the shadow of black holes as a special case of that. And this was really a very important event 2 years ago. Then you have the perihelion shift, the Lense-Thirring effect as orbital effect, and then the back reaction, which is also a very involved effect because it's really the nonlinearity of the gravitational field which plays here a role, and this also has been observed with the Hals-Taylor pulsar very precisely, and I think in a few years they will have all in each respect the best values. Then we have also a test of the spin-spin coupling. That is a spinning top orbiting the Earth. This is the gravity probe B measurement, and all these effects on clocks. The gravitational redshift has been measured, the gravitational time delay, and maybe perhaps in a few years also the gravitomagnetic clock effect may be visible. And of course, all the observations of gravitational waves and the special relativistic effect. So I will here now focus on two effects: this equivalence principle effect test and the test of the gravitational redshift with Galileo. This has been carried out, or the launch of this mission was in 2016. The idea is to have a test of the equivalence principle of the order 10 to minus 15. It's a small satellite, was the development of 20 years of this experiment. It depends on differential accelerometers. There are two test masses here with made of different composition, and the measuring scheme is shown here. So we have here the Earth, and the two test masses are cylindrical test masses, one cylinder inside the other. And if the red test mass would be accelerated more than the blue test mass, then there would be an additional force with respect to the other test mass towards the Earth, and then you would see that the inner test mass starts to oscillate, and this oscillation then is the subject of the measurement. The instrument is very complex. There are material cylinders covered by electrodes, and you have to, and these electrodes have a capacity here, and this changes if the position changes, and from that you can read out the position and the orientation of the inner cylinder with respect to the outer cylinder. Here are two test masses inside. Here are two test masses inside. I should pick more pictures. And this is the orientation of the test masses inside the satellite. Again, the scheme of the mission scenario. So we have two pairs of test masses. One is the reference test mass pair, both made of platinum, and the the science unit of the unit of the equence principle test is made. One is of platinum and the other of titanium. And the measurement is the differential acceleration between the two test masses. There's an additional trick here. One can rotate the satellite, and this is of course important in order to decouple the motion of the frequency of the motion of the test mass from the orbital period. Yeah? Otherwise, also the gravity gradient will play an important role here. So this is and one can adjust this spin test mass. One can choose it as one needs it, and so there's a lot of freedom here. And this is also an advantage of space, that you really can adjust your experiments as you like it. This is a drawing of the satellite around 1 × 1 × 1 meter large. This is the here you see a cut view of the main instrument. Here the red one are the two test masses. There are other masses here in. So it's a complicated thing. These are the main, or the central parts here. The test masses, they had to be manufactured within micrometer precision, and this has been done by the PTP in Braunschweig. The main issue of this mission was that they needed a decharging device, and they have chosen a gold wire with a diameter of 7 micrometer, and this was 22.5 centimeters long between these two test masses and the housing. That one avoids that if by some of cosmological proton also the test mass will be charged up, then the measurement will be distorted. And this was a major concern, also led to some delay of the mission. But finally, in 2016, the satellite has been launched. And here again, the main principle of the measurements, you have a capacitive measurement. This is one test mass, the red one is the other test mass. And if this goes back and forth, the capacity here of this sensors will change, and therefore by reading out the voltage of these capacitors, you can determine the force, and you can also reposition the inner test mass so that gravity gradients and so on are no longer so dominant. This is the power spectral density of the measurements of the science unit and of the reference unit, and you see nevertheless that 2 times the signal frequency, there is the influence of the gravitational gradient. The science signal should be here, but you see nothing, and that is then the confirmation of the equence principle. This is the evolution of the amplitude of the signal in terms of the fast Fourier transform for the science unit, for the reference unit, and this was the targeted systematic error here, and they just read it after 100 orbits. And finally, so all this huge modeling and calculations then led to the calculation in 2017 and end of 2017 that we have something like 1.5 10 to minus 14. So you have to add up this here, and the next publication is just on the way with an improvement of that. Here for this publication, only 9% of all the science data have been used. Now for the gravitational redshift, this has been measured the first time by Pound and Repka in the 60s. And then soon after that, and soon after the development of the atomic clocks, they put atomic clocks on a satellite, on a rocket, and then tested the validity of the gravitational redshift. That is, this frequency change related to the difference of the Newton gravitational potential. In order to quantify this test, one introduces an extra parameter, and this then gives that, and the result here is that that the parameter is smaller than 10 to -4. This is the emission scenario, and now there was, and this was the best test of the gravitational redshift valid till now, since 40 years. And then you know that in 2014 there was a launch of Galileo 5 and 6, and unfortunately due to a misfunctioning of the frigate upper stage of the Soyuz rocket, they launched at the wrong orbit with a large eccentricity, and but with a considerable height. But this means that that there was a height difference 2 times a day of almost 12,000 kilometers. They decided to correct the orbit in order that the satellite do not go through the Van Allen belt. So after the correction, the eccentricity is smaller, but the height difference still is almost 9,000 kilometers 2 times per day. And if you see here, the height of the rocket of the orbit was 10,000 kilometers. So that means that we have here 2 times a day practically a GPA experiment. Okay, so here is a figure of the orbits. This is the wrong orbit. This is the targeted orbit, and blue is the corrected orbit. But it's still an elliptic orbit. And we think that Einstein would be really happy for this misfunctioning of the rockets. And because on these Galileo satellites there are rather precise clocks, so we have a passive hydrogen maser, or with a stability of the order 10 to -14. They also have numbers for the temperature dependence and so on. And there's also a rubidium atomic frequency standard there, which has also some precision of 10 to -14. Both, of course, we have to take into account, if you determine the proper time of the clock, the velocity of the clock, and the gravitational potential of the clock. These two effects add up. And if one describes the frequency difference, the relative frequency difference by changing the height of the orbit, what comes out is this here, and this can be replaced by means of the Kepler orbits by this equation here, where R and V are the Keplerian solutions of the orbits of satellites, and that means that that we have here per orbit something like 317 nanoseconds time gain. And we now analyzed the orbits of the satellite and the clock reading, and for that we had all this. Had to interpret all these pseudo ranges and the carrier phases with all the influences from the clocks, from the instrument delays, from the atmosphere, from noises, and so on and so on. And and it's clear that 1 nanosecond is related to 30 centimeters, and we need something in the nanosecond regime. So you have to know the satellite very well. And if you want to improve the redshift, then even better. This is the clock data, the performance of the clocks. Green is good, light green is not so good, and so on. You see that the clocks are not perfect. But if you take the clocks and just plot the time here, and the red curve is what is predicted by general relativity, then it's a perfect coincidence here. So it is certainly confirmation of general relativity. But if you if we subtract from the data all the gravitational effects, then we see some noise, and this now has to be interpreted, has to be discussed. So we took our modeling was at least square fit in the taken into account the quadrupole moment of the Earth, of course the Newton parts, the velocity of the satellites, and the clock offset and the clock drift parameter, and this is and the clock residuals, and what we have to determine is the alpha. And yeah, we have all the clocks, all the data. Two clocks are not good, so we could use these clocks, putting everything together. You see clock data like that, so there are a lot of glitches and so on, which are not really understood. So at the end, we choose this clock here, and also could get some information about these on these outliers here. So this is so to say what the clock we took here, and we could derive from that the Allen variance, and of course then one has to do the systematics, temperature effect, magnetic fields on the orbit, whether the radiation pressure of the solar radiation plays a role, tidal potentials from the sun and moon, other systematics on the ground. So everything we discussed, we made a modeling of the satellite in terms put into the computer in order to really be able to calculate the solar radiation pressure. We also had some extra ranging mission, a laser ranging campaign in order to precisely measure the distance between the Earth and the satellite, and this all then together then leads to that to the conclusion that the orbit could be understood within 2 millimeters. This then could make the understanding of the clock better, and now we have to discuss the temperature effects with the characterization of the clock made on ground. You could see that the temperature effects give a variation of the alpha less than or of the order 10 to minus 5. Also, the effects of the magnetic field based on ground data of the clock gives an effect also of the order 10 to minus 5. Other effects also turned out to be not really important, so that we had for the clock 5 with all the things here discussed a uncertainty of the order 1.5 times 10 to minus 5, and since we double this, we have to 2 times 8, and this is a factor of 5 improvement with respect to gravity probe A. So this then is a result of this measurement, and we did this in a friendly competition with our colleagues in France who also got the same result, and this has been published as a back-to-back paper in a PRL 3 years ago. We have new data, and we are still looking for a further improvement of this effect. Maybe there will be soon another effect which could be tested. This is the gravitomagnetic clock effect. So since the Earth is rotating, it creates a gravitomagnetic field, and this gravitomagnetic field may also influences the clocks. And if you have 2 clocks counter-propagating in the equatorial plane, then the effect is of the order J over mc squared, where J is the angular momentum of the Earth. This does not depend on the radius, does not depend on the gravitational constant, so it's a kind of topological effect. It is of the order 10 to minus 7 seconds, so it's huge. Could be also for inclined orbits, but we need it for different orbits, really different orbits, and there we defined an observable in an analytic way, where S1 is the time of the first satellite, and S2 is the time, the proper time of the second satellite, and And the alpha is given by the functions S1 and S2, where J is put equal to 0. If one calculates this for eccentric orbit and inclined orbit, then the first order effect is then this alpha is of the order 0.5, and the effect for typical typical constellations of the order 10 to minus 7, still 10 to minus 7. We also, and if you here's a list of a clock comparison. If you compare various GLONASS clocks, then this is the time difference between these two satellites, which you may observe in nanoseconds. So you have here the best is between a geostationary between a GLONASS clock with this inclination and the geostationary orbit satellite with this inclination. There you have 99 nanoseconds of a time difference between these two clocks. It is not so easy to confirm this because we need an absolute stability of the clock of 10 to 100 nanoseconds of the order of 50,000 seconds. But they drift several microseconds per day, so this has to be analyzed whether we can understand this drift. Although we need better clocks with a better frequency stabilization, and so perhaps people are now discussing new clock missions in order to modify the Galileo system. And here, if we are doing error estimations, then this also means that that the orbit has to be known up to 14 micrometers. So this is also a challenge, and it's not clear whether this also can be met, but we are discussing that. Okay, so I will come to the end. So at the moment, there's no single test contradicting special or general relativity. We have not yet measured the gravitomagnetic clock effect, which is, so to say, somehow in reach. The big problem, of course, is the incompatibility between general relativity and quantum mechanics, the topic of the previous talk. And the big unknown today is dark matter. So with that, I would like to thank you very much. Thank you.
Fantastic overview and very, very exciting, Klaus. And let's see if we have questions. Yeah, questo per la danza. Yeah. Can you see any question on the chat?
Oh, I do not see any question. Okay.
Too clear. Was really very, very clear, very beautiful. Thanks again, Dan.
Okay, yeah, thank you.
And then let's see Gerhard Heinzel if he's ready.
Yes, hello. I'm ready. Somehow I cannot start my video. Something seems to be wrong. Anyway, let's start.
Gregory, can you see? Oh, questo è molto.
Can you see my screen?
Yes.
Okay. So thank you very much for giving me the opportunity to present the status of laser interferometry in space. And we are using that for two different applications. The one is gravitational waves, and the other is measuring Earth gravity. I don't think I have to say much about gravitational waves here in this audience. Of course, you know, first detection and present measurements. Noteworthy here is that the highest mass of an object that was discovered or measured with gravitational waves is of the orders of hundreds of solar masses. And now, why do we want to go into space? And that is because on the ground, our instruments are limited to frequencies above 10 Hertz by seismic noise and gravity gradient noise. But for many of the most interesting signals, we want to go to much lower frequencies in the millihertz range. And that will give access to some of the most violent events in the universe. And so there are also some technical reasons which limit our possible sensitivity on ground, for example, the arm length. And that's why we want to go in space. There's a plot of the sensitivity of advanced LIGO and LISA. And you can see that they cover a very different frequency range and therefore a very different set of sources. And so Earth-based observatories and space-based observatories are not in competition, but they complement each other. This is, for example, one plot of the LISA sensitivity with some of the sources that we expect. And in contrast to the ground-based experiments, we expect for some of the sources a very high signal-to-noise ratio. We will not measure a few events per day or so, but we will have hundreds or thousands of events all the time, and we have a problem of disentangling all the sources that will be there. Here's another plot showing some of the expected sources of LISA that include galactic binaries, black holes, ultra massive black holes, MRIs, but also sources like stochastic background, and some tests of general relativity will be possible. Now, because of that, there are now several plans to launch gravitational observatories in space. The one that I will talk most about is LISA, Laser Interferometric Space Antenna. It's a joint project by ESA and NASA in an orbit around the sun, trailing the Earth by about 20 degrees, a triangle of 2.5 million kilometer length. But there are also other projects that I will briefly mention. For example, in China, there's a Taiji project and the Tianjin project, and another one in Japan called DISIGO, which aims for a shorter arm length to cover the gap between ground-based detectors and LISA. So what do we have in space so far? Laser interferometers, precision laser interferometers that have been launched. So the first one was LISA Pathfinder that I will talk about. And then we have Taiji 1 and Tianjin 1, both of which launched about a year ago or 1.5 years ago, around the same time. And we have GRACE follow-on that is still in orbit and still measuring. Taiji and Tianjin are two competing projects in China, and their next steps will be to launch future Pathfinder missions with 2 satellites, and then maybe eventually they might merge into a single project, but this is not an official statement from anywhere in China. This is just my personal expectation that this might happen one day. So the status of LISA is that it was selected as a large mission by ESA with a smaller contribution from NASA. The instrument will be delivered by a consortium of the ESA member states and possibly Japan. The spacecraft and some payload units come from ESA and NASA. We are now in phase A. That means we have 2 parallel industrial studies that look at the spacecraft and the mission. And we have the institutes that form the consortium working on the payload. The launch now is foreseen for mid-2030. And the next relevant milestones are the mission formulation review end of this year, and then in 2024, the mission adoption. The critical technologies for LISA are first a free-falling test mass at the level of 10 to the minus 15 meter per second squared per square root hertz. That has been demonstrated with LISA Pathfinder, including drag-free control that needs micronewton thrusters, the discharging of the test mass without a gold wire because it's really free-floating, and the ultra-stable environment in terms of thermal stability, for example, and others. And the other challenge is low noise interferometry in space, and that has two parts. One is the local interferometer of order of 30 centimeters to read out the test mass. That has also been demonstrated on LISA Pathfinder. And then we have the long arm interferometer. Part of that has been demonstrated with Grace follow-on on a length scale of about 200 kilometers. But to go to LISA, there are further developments needed and also ongoing. Limiting noise sources of LISA are shown here. So at the lowest, at the bottom of the curve, we have the interferometry sensing noise that is composed of shot noise and others. Then at the lower frequency, we are limited by the residual force noise on the test mass. And if we go to higher frequencies where multiple wavelengths fit into one arm length, we get some cancellation of the signal. So LISA Pathfinder was an ESA mission, also with some smaller NASA contribution in orbit from 2015 to 2017. Some pictures are shown here. It was launched in 2015 in a Lissajous orbit near Lagrange point L1, about 1.5 million kilometers from the Earth. And after it overachieved its goals and 2 mission extensions, it was then switched off 2017. Its main purpose was to demonstrate the force-free test mass, including drag-free control, caging mechanism, and the contact-free discharge, and that has all been achieved. And it was the first laser interferometer in space, including aspects like an ultra-stable optical bench, fiber optics, a laser in space, acousto-optic modulators, a phase meter, differential wavefront sensing, and the subtraction of tilt-to-length noise. I'm talking mainly about the interferometer here. And so the principle of the LISA Pathfinder interferometer was a heterodyne Mach-10 interferometer. In the case of LISA Pathfinder, in the audio frequency range with kilohertz heterodyne frequencies. And in such a heterodyne interferometer, a path length change is translated into a phase change of electrical signals, which can be easily measured with electronics. And it has a number of advantages. It is independent of the operating point, as opposed to, for example, a homodyne interferometer like LIGO, which needs to operate at the dark fringe. And it has a wide dynamic range. It can track length changes over many fringes. It doesn't need any log acquisition. You just turn it on and it starts measuring. And it doesn't need any calibration. The conversion to length is just given by the laser wavelength, which is known good enough and is also constant. The development took quite a while. We started in laboratory experiments now almost 20 years ago. And then the interferometer was ready well before launch. The launch was then delayed by other things. But still, it takes quite a while to go from a concept to something that is ready to fly. One important aspect of laser interferometers is the measurement of angles, because we need very good beam alignment and beam pointing in order to hit with the beam the remote spacecraft. And that is achieved by a technique called differential wavefront sensing, where the heterodyne beat node is measured with a split photodiode. And shown here, if the wavefronts are tilted to each other, then you get a different phase change in the two halves of the photodiode. In reality, we have quarters to measure 2 dimensions. And the sum of them gives the longitudinal signal, and the difference of them gives the tilt, in this case of the test mass, but also of the spacecraft. That has a very large amplification factor from the test mass angle to the electrical phase change, which makes it very sensitive. Moreover, there's a big cancellation of common mode noise sources. So we get excellent sensitivity of the order of less than a nanoradian per square of hertz. And that is a key to achieve the alignment of an interferometer. When we launched LISA Pathfinder and turned it on, we were really happy and surprised to get a contrast of 99% immediately after turn on. And that's better if you ever built an interferometer on ground. You know this is a very large number. On ground, we actually never achieved better than 93%. So the environment in space is very favorable to do precision interferometry because it's very, very stable. The final result of LISA Pathfinder then was the acceleration noise. The requirements are shown here in this little gray triangle for LISA Pathfinder. The requirements for LISA are here, this other black line. And initially, we immediately overachieved the requirements for LISA Pathfinder, but after some optimization and debugging, we even went below the requirements for LISA by a considerable factor. And the acceleration noise in the end was limited by residual gas pressure noise, the Brownian noise in the mid-frequency range, and then actuation and radiation pressure in the low-frequency range, and in the high frequency by the interferometer, which was, however, still 100 times better than anything we ever measured on ground. So in summary, the free-fall test mass performance has not only exceeded the requirements of LISA Pathfinder, but also the levels needed for LISA. And so the test mass as such and subsystems is basically ready to go for LISA. The interferometer also worked perfectly with a much lower noise than required or ever measured on ground, which allows us to investigate many minor effects, like the coupling of residual intensity noise at twice the heterodyne frequency, some effects of polarization, and others. And so the local interferometer is also ready to go. And the other aspects like drag-free, defux, and so on, they also work very well. The other two pathfinders haven't been launched are Taiji-1. The Taiji project is a project centered in the Chinese Academy of Science. They launched around the end of 2019 and demonstrated successfully a local laser interferometer, a free-floating test mass, and drag-free control. And the next step will be a Taiji Pathfinder with 2 satellites and an inter-spacecraft interferometer. And similarly, the other project, Kenqing, is centered in the Sun Yat-sen University in southern China, coming out of a group with a long experience in torsion balances and gravitational reference sensors. They also launched a Pathfinder around the same time and also demonstrated the local laser interferometer, free-floating test mass, and drag-free control. And similarly, their next step will be the Tianqin-2 project with 2 satellites and an inter-spacecraft interferometer. The other interferometer, which is relevant in laser interferometry in space and laser interferometry for gravitational physics, laser ranging interferometer, LRI, on Gray's follow-on. And that is a different purpose. It's nothing to do with general relativity, but with classical gravity. And its purpose is to measure the gravity field of the Earth. And for that, we have to realize that the Earth is not a sphere, but is described by a geoid, which is a hypothetical construct that represents a surface of the same gravitational potential, or in other words, if the whole Earth were covered by water, it would be the height of the water around that. And so it's a function of the mass distribution, and it changes when, for example, rocks move in earthquakes or so, but also when water moves, for example, when ice melts or water accumulates. And that's the most interesting application for that. And it has been observed from space multiple times already. There's a series of missions to observe the Earth's gravity field, starting with CHAMP. Then we had GRACE, GOCHE, GRAIL on the moon, and now GRACE follow-on, which is a follow-on mission for GRACE, as the name says, again in the same constellation as a US-German bilateral collaboration with the same team. With the special points that it implemented the first inter-satellite laser ranging interferometer. So the principle of GRACE and also of GRACE follow-on is that you have 2 satellites in a low Earth orbit, roughly 400 kilometers above the Earth, that follow each other in the same orbit, but trailing each other by about 250 kilometers. And now if that pair approaches a large mass, for example, here a nice mountain in Nepal, then the first satellite will be first attracted a little bit earlier than the second satellite, so the distance between them increases. When they are centered above the mass, both are attracted and the distance decreases, and then finally the trailing satellite is pulled back a little bit. The principle was pioneered by the GRACE mission, which used microwave ranging with about 2 micrometer per square root of hertz. And it's also important to realize that it's no absolute ranging, but also only measurement of the variation. And because it's a low Earth orbit, there are non-gravitational forces which need to be measured and subtracted with an accelerometer. So what do you get then? If this pair flies over, for example, here the Himalaya, these are real data from Grace follow-on, you get a wiggle in the separation of a couple dozen microns. But this is a static gravity field coming from the Himalaya. What we are interested are the variations due to changing water and so on, and they are much, much smaller than that. There are many, many disturbances, such as ocean tides, solid earth tides, aliasing, etc. So the data processing is very difficult and still under development, even after such a long time of operation. What you then get in the end is a gravity map of the Earth with about 200-kilometer resolution for the static field, or 350 kilometer spatial resolution for the monthly gravity field, which is most relevant for climate research, and a vertical resolution of the order of millimeters of equivalent water height. And some of the results here show how relevant it is for climate research are, for example, the change of the Greenland ice mass, which shows a drastic melting of that mass, similar in the Antarctic, or large river basins here, for example, the Amazon basin. This is the yearly amplitude of how much the water level changes over every year. But you can also see that it's limited right now to only the largest events and river basins. And of course, we want to improve the resolution to also look at smaller events. Another picture of the annual variation just to the rainy season and dry season in the Amazon basin. You can see that the water level changes by plus minus 10 millimeter as averaged over a big basin. The GRACE mission ended in 2017, long past its design life. And because the data is so relevant, it was decided to make a follow-on mission. Basically the same technology and the same team. And the main innovation was to include a laser ranging interferometer instead of on top of the microwave as a complementary experimental demonstrator that measures the same thing, the distance between the two spacecraft. The laser ranging interferometer is a very simple interferometer compared to, for example, LISA, with a simple optical bench, and it includes a very elegant and efficient beam steering mechanism that aligns both the transmit direction and the receive direction with a single actuator, which is moreover outside of the sensitive path. So the optical bench doesn't have to be very fast or anything like that. It may not look very simple here, but if you compare it to other interferometers, it is indeed very simple. You have one laser on each spacecraft. On the master spacecraft, it is locked to an optical cavity to stabilize the frequency. And then the light is sent out through triple mirror to the other spacecraft. At the other end, order of nanowatt are arriving through a small aperture. And there the beat node is formed with the local laser, which is then locked, phase locked to the incoming light with an offset frequency and sent back. So this is the so-called transponder principle, as opposed to a passive retroreflector, because in a passive retroreflector, the power decreases with the force power of the separation. And very soon, after 100 kilometers or so, we would not get enough light to do any good measurement. But with a transponder, you measure the light here and then regenerate a strong beam with a new laser, which is phase locked. And so we can overcome this distance limitation. Noise sources include mainly the laser frequency noise, and that comes because we basically have an unequal arm length interferometer, and it turns out that the requirement is by accident very similar to the requirement we have for LISA, and it's achieved by having a reference cavity on one spacecraft. Pointing jitter is always a big issue, and we deal with that by the differential wavefront sensing measurement and then the beam steering mechanism to fix it. Then, of course, we have thermally driven effects and a number of other noise sources, the noise of the clock, shot noise, laser power noise, etc., but none of them are limiting. But of course, we need to study all of them. Results from the LRI So one has to realize that the final gravity field is recovered by combining not only the ranging data from the ranging measurement, but also the non-gravitational forces measured by the accelerometer, orbit determination, background models for the Earth types, with Earth types, ocean types, etc., etc. And we only deal with here with the ranging noise. And because all the ranging is now so good, well below all the other noise sources, so we have only a modest improvement in the gravity field due to the laser ranging, because all the other noise sources are dominant at the moment. But that means we have a huge margin for coming improvement in all these other noise sources. And because we have two measurements, with both the microwave ranging and the LRI, we can perform cross-instrument diagnostics. So Grace Follow-on was built in a relatively short time and on schedule without delays and schedule overrun or cost overrun, and was then launched on a Falcon 9 rocket. And shortly after, we tried the initial acquisition. That's always a big problem in these interspacecraft interferometers, because there's no way to align everything from ground such that you will hit the other satellite on the first attempt. You always need to perform some kind of scanning in a spiral or something like that, or some auxiliary sensor in order to hit the other satellite. We did that in a scanning procedure that lasted 9 hours, and we immediately got these nice data here in the downlink, which told us the magnitude of the misalignment, and then allowed us to program this misalignment, upload the computed data, and immediately we acquired log and got the first light, and saw immediately that we measure a meaningful data variation of plus minus a few hundred meters over one orbit, which corresponds to the microwave measurement and the expectation. And that happened on the first attempt, and the LRI stayed in log for many orbits without interruption. And this is a noise curve here. So the pink, or the magenta curve, is a raw spectrum of the raw measurement of the LRI. And it's dominated in the low frequency by this gray area here, which is not noise, but is the expected signal, the gravity signal itself, which includes the plus minus a few hundred meters from the orbital variations. And then here in the mid-frequency range, around 10 to the minus 2, this is where really the information is that we want to get at. The requirement is the green curve, and you can see that at low frequency, at high frequency, we are much below the requirement, and we are limited by laser frequency noise as expected. And at high frequencies, we have something like 200 or 300 picometers per square root of hertz, which is about the size of an atom. So we can measure variations of the order of the size of an atom over a separation of 200 kilometers, while we are racing above the Earth with thousands of kilometers per second. That I find quite impressive. The noise, not so easy to get at, the noise of the ranging itself. Here's one attempt made by Graz, where they tried to disentangle the measurement noise into 3 contributions. The common mode noise in blue, that includes everything that comes from the accelerometer, non-gravitational accelerations, etc. And then the KBR, the microwave noise, is the gray curve, and the red is the laser noise. And you can see that, as expected, the laser noise is much more quiet than the microwave ranging. And so it is reasonable to expect that the LRI will produce better gravity fields to some extent than the microwave. Here are some very preliminary results, which are not yet published, which show a gravity map derived from the microwave instrument and from the laser instrument. And without going into the details, I think it's clear that there's some improvement, but the details of where exactly the improvement is still a work in progress. So in summary, the LRI is the first intersatellite laser ranging interferometer. It works as designed on the first attempt. It's very low noise. It stays in log for hundreds of orbits. Well, after I wrote that, I had to revise it. It's more than 1,000 orbits without any interruption. And it's a technology demonstrator not only for future gravity missions, but also for LISA, because some of the aspects are very similar to LISA. And even so, there are only moderate improvements in the monthly gravity fields. There's lots of margin for further improvements. Now coming to LISA, main LISA interferometer is along one arm, and it is split into 3 parts for technical reasons. A local interferometer similar to LISA Pathfinder, where we measure the separation of the test mass to an optical bench, and similar on the other spacecraft. And in between, over the millions of kilometers, we measure between 2 optical benches. So this is also shown here in a sketch. Long distance measurement is, in contrast to GRACE follow-on, realized with a telescope of about 30 centimeter diameter, because otherwise we would never get enough light to the other end. The local test mass interferometer can basically be taken as is from LISA Pathfinder with only minor adaptations. And so the main development is in the long arm interferometer. Parts of that have been done, as I said, with the LRI on GRACE follow-on, which is not exactly the same, but has many similarities. The challenge is that we need to measure picometer variations over a separation of millions of kilometers at frequencies of sub-millihertz, so timescales of many thousands of seconds. This is possible at all, because huge orbital effects are separate in frequency. So if you look here at the separation between the 2 satellites over a timescale of 10 years, we have something like 2.5 million kilometers. There's quite some variation of the order of 1% coming just from solar system orbital dynamics. If we zoom into 1 year and now not just look at the variation, we still see tens of thousands of kilometers. But we want to measure picometer or nanometer. And that's only possible because these large variations are very, very, very smooth. I mean, the pull of Jupiter is nothing that changes over thousands of seconds. And so only as an illustration here, this is not a real signal. If we now zoom in a short piece of that smooth curve, we see on top of these smooth curves, these small variations, and they represent our gravitational wave signal. Now the challenges are measuring picometers. And their shot noise is a fundamental limit because we only receive hundreds of picowatt or nanowatt. And also a picometer is a millionth of a wavelength. So daylight with an amplitude of the millions gives us noise comparable to our required sensitivity. But millionths of an amplitude is 10 to the minus 12 in power, and typical stray light is much larger than that, coming from parasitic reflections or diffuse stray light. So we have to deal with that very carefully with the optical design by using baffles, beam dumps, etc. Another recurring headache is tilt-to-length coupling. That is a problem in all laser interferometers. And we deal with that with very precise alignment along the line of sight, the movable aperture, with calibration in flight and subtraction in ground processing. There are other noise sources that limit the picometer measurement, the electronic noise in photoreceivers, for example, the laser residual amplitude noise or the noise of the phase meter, but those can be dealt with by tests on ground, which are happening right now. We want to measure over millions of kilometers, which means that the beam expands to something like 15 kilometers, and we cut out only a small fraction of that, of the order of a nanowatt. We also need very accurate pointing to sub-microradian, which requires a complicated link acquisition procedure when we first turn on the interferometer. Once we have acquired the link, we use the differential waveform sensing to maintain the link. The light travel time is about 8 seconds while the spacecrafts are moving. So we have a difference between the transmit and receive directions because the other spacecraft has moved in between. That requires a point-ahead mechanism in the optical path, which is something that we have demonstrated already. And another problem is that the laser frequency noise couples into the measurement with an enormous amplification due to the arm length difference, which is 1% of 2.5 million kilometers, which requires then a technique called time delay interferometry to deal with that. Now, we also have Doppler shifts because the spacecraft move, the separation is not constant, they move with respect to each other with several meters per second, and that Doppler shift of several megahertz. And so we have to fix our laser frequencies such that we get measurable heterodyne beat nodes all the time. We have a total of 6 lasers in the constellation. One of them is locked to the cavity, and we call it the reference laser or the master laser, and 5 transponder lasers, which employ offset phase locking. So we have to keep the 9 node frequencies that occur in total between 5 and 25 megahertz, which is the bandwidth of our photoreceiver. So we need a frequency plan, optimize those frequencies over the duration of the mission. And we've done that, and it turns out that there are 6 possible topologies how you can knock the lasers onto each other. If we fix one laser as the master, and because we can pick any of those as master, we have a total of 36 possible locking topologies, and all of them are now implemented in our simulators. Frequency stabilization is a big issue because, as you know, in any unequal arm length interferometer, we have a direct coupling of laser frequency fluctuations into the phase measurement. And it would be totally overwhelming if not mitigated. And so we have the free running laser noise shown here, the red curve, and we have to go down to the green curve in order to meet the measurement requirements of LISA. With a stabilization on a cavity, we get only to the blue curve. And then to get from the blue to the green, there are 2 possibilities. One is the so-called arm locking, and the other is a time delay interferometry. But the baseline at the moment is that TDI alone is enough, so we will not employ arm locking. And what is TDI? TDI is a way to generate a virtual equal arm length interferometer by data processing on ground. So you construct a virtual photon path where the photons travel first the one arm and then the other arm in the first generation, or twice that in the second generation, and that allows to compensate static arm length differences or even moving arm length differences for the second generation. In practice, what that means is you take the laser measurements from the phase meter on board, which are called SI, and they are downlinked, and then what's shown here happens on ground. And then you form linear combinations of those, which are delayed by the travel times along the arms. And in practice, what that means is that we have to know very precisely, to sub-nanosecond accuracy, both the travel times along the arms and the time when the measurements were taken, the timestamps. That gives quite some challenging requirements on the measurement system on board that I will come to in a second. So this time delay interferometry is essential to remove the frequency noise in post-processing. It's based on pioneering work at JPL, end of last decade, last century. We need the second generation. It turns out that the transfer function for the gravitational wave signal is also not flat anymore, but has a complicated shape. And so that has also been taken into account in the data processing then. And it requires measurement of the arm length, the absolute arm length, sub-meter, timestamping to sub-nanosecond. That can be done by auxiliary modulations on the laser beam, pseudo-random modulation similar to GPS, and gigahertz phase modulation to measure relative clock offsets. And it puts special requirements on non-standard requirements on the timing and clock subsystem on the spacecraft. So the ongoing work at the moment in that respect is to simulate the whole data processing chain, starting from simulated downlink data and its pre-processing in something called INREP, the initial noise reduction pipeline, to study the requirements on the clock noise and the mitigation, to study the tilt length subtraction, and the timing system on board of the spacecraft. Now, the next challenge is to measure at sub-millihertz frequencies. So we aim to measure down to 20 microhertz, at a period of 14 hours. And on that time scale, many things changes. For example, the breathing angle between the arms. Because the arm length changes, the angle is not exactly 60 degrees, but changes by plus minus 1 degree over a year. And so we need to compensate for that. And that's why we have not one fixed spacecraft, but we have two independent so-called MOSAs, moving optical assemblies per spacecraft, and a mechanism that slowly moves them with respect to each other. Also have the Doppler shift along the arms, which gives us very tight requirements on the linearity of the photoreceivers and the phase meter. Over those timescales, temperature is always a challenge. Temperature always changes and affects the precision of our measurement. So we have a very challenging thermal design of the spacecraft. And at the lowest frequencies, the GRS noise, the gravitational reference sensor, the test mass is dominant. But that has been shown by LISA Pathfinder that it's good enough. In the mid-frequency range at millihertz, we have the interferometer noise, and that must be very carefully controlled. So my conclusion is that laser interferometry in space is now a well-established discipline, with several missions having been flown or flying even right now. Grace Follow-on is flying right now and measuring. It's used both for the local test mass readout and for the interspacecraft ranging. It can be applied both for gravitational waves and for Earth observation. We can achieve noise levels of picometers per square root of hertz, can track over long times and many wavelengths. We do not normally do absolute ranging, but only changes over time. But the absolute ranging can be achieved by auxiliary functions that also allow clock synchronizations and data transfer. And the next big thing that we are working on is, of course, LISA. Thank you. I don't see, do we have any questions? Here's one question by Colin McLaurin. What is the magnitude of radiation pressure from the laser on the satellites? The radiation pressure is an issue for the test mass, because the test mass is about a kilogram or 2 kilograms. And their radiation pressure is indeed a problem, but it's not a big problem. We need to stabilize it to the order of 10 to the minus 4 relative intensity noise, which is not completely trivial, but also not very hard. It can be done. Radiation pressure on the satellite is negligible. I don't hear anything. Maybe something is wrong with my audio.
Everything is okay, I think.
I'm sorry, if somebody is saying anything, I cannot hear anything. I may have a problem with my...
Yeah, if there are no further questions, you can end this talk.
There are questions in the Q&A part. Probably you can read yourself and answer.
Well, let's congratulate Gerhard again, and let's move to the last meeting of the day, the last contribution.
Good morning, can you hear me?
Sì, Ignazio, ma siamo fuori tempo massimo, quindi rispetta i tempi, mi raccomando.
Sì. Allora, potete vedere la presentazione?
It's okay.
Ok. Okay, frame dragging and its tests with laser relativity and geodesy satellites. This is our team Can you see the slides? This is our team made of theoretical physicists in red, and there are space geodesists in green, and aerospace engineers in black. This is at the top the Lares satellite that was launched in 2012. At the bottom, we have the Lares 2 satellite that was, this picture was taken in 2020, and the satellite will be launched in March 2022. And this is our team, and there is, of course, also ASI. Overview of the talk, brief introduction on frame dragging of inertial frames. The Lares satellite launched in 2012 with its main results, test of frame dragging with about 1 to 3% accuracy, and test of the weak equivalence principle at a new range and with new materials at the level of 1 part in a billion. And finally, I will talk about the Lares 2 satellites to be launched next year. So there is an intuitive characterization of dragging of inertial frames, frame dragging, as Einstein named it in 1913. In electromagnetism, by the Maxwell-Ampere equation, you have a magnetic field that is generated by electric currents, J. However, in Newtonian gravitation, by the Poisson equation, only mass generates gravitational fields. However, in general relativity, space-time curvature is generated by mass energy currents. So, for example, if you take a perfect fluid, you have this mass energy currents, epsilon times u alpha, the force velocity, that is generating a space-time curvature. This is an intuitive characterization of frame dragging. It plays a key role in high-energy astrophysics with the Kerr metric. And there is a better characterization of frame dragging by scalar curvature invariance to distinguish between the intrinsic frame dragging phenomena generated by the angular momentum of a spinning object, such as the Kerr metric, and the effect simply due to the motion on a static background, the so-called de Sitter geodetic effect. We propose to use the following pseudo invariant called the Chern-Pontryagin pseudo invariant that for the Kerr metric is given by this expression here, that is a function of the angular momentum of the central object. So you can also write this pseudo invariant in the post-Newtonian approximation. And there is a recent comprehensive characterization of gravitomagnetism using scalar curvature invariance in a paper that is going to be published by Costa and others. There is an interesting analogy of weak field and slow motion general relativity with electromagnetism that is called gravitomagnetism. You have in electromagnetism, you have a magnetic field that is generated by the magnetic moment of an electric current, and there is the Larmor precession of the magnetic pole of a magnetic dipole, a magnetic needle. In general relativity, there is a gravitomagnetic field generated by the angular momentum of a mass current here, gravitomagnetic field, and there is a precession of a gyroscope. You can see here the precession of a gyroscope, very similar to the Larmor precession of a magnetic needle. This is true in weak field and slow motion. You can find more in this textbook about gravitomagnetism. Now, frame dragging is playing a key role in the analysis of the emission of gravitational waves due to the coalescence of two spinning black holes to form a Kerr spinning black hole. And now there is a great and fascinating 20th century discovery, the acceleration of the universe, the acceleration of the expansion of the universe. Now, dark energy and quintessence plus dark matter might constitute about 95% of the universe. Now, there is a theory, Chern-Simons gravity, in which there is a scalar field that is possibly related to quintessence. There is an interesting paper by Smith, Erichek, Caldwell, Kamionkowski in 2008. And these are the field equations of Chern-Simons gravity. You see there is a term that is not included in general relativity. This part here, minus 16 pi divided by 3L C alpha beta. This is the new part of Chern-Simons gravity. The rest is general relativity. And this is the so-called Cotton C alpha beta is the so-called Cotton York tensor. And this is the action of Chern-Simons theory, where there is again this Chern-Pontryagin pseudoscalar, and there is this scalar field theta. Now, what is interesting in this theory is that all post-Newtonian tests agree with Chern-Simons gravity, but not frame dragging. Frame dragging has a different prediction from general relativity. In the weak field and slow motion approximation, indeed, we get this equation in Chern-Simons gravity. We have the Laplacian of the gravitomagnetic potential, H0I, that in general relativity is equal to 16 pi rho VI, and there is this extra term that contains the D'Alembertian of the gravitomagnetic potential divided by the so-called Chern-Simons mass. This is the gravitomagnetic potential, is just the curl of the gravitomagnetic, this is the gravitomagnetic field, just the curl of the gravitomagnetic potential. And for a homogeneous sphere with mass density rho and radius r, rotating with angular velocity omega, there is an extra contribution due to Chern-Simons gravity. Now, this is the contribution of general relativity, and this is the contribution of Chern-Simons gravity, where we have these Bessel functions. And if we take the geodesic equation in weak field and slow motion, we have the Lorentz force equation for a test particle, this equation here, and we can find the ratio of the nodal drag of an orbital test particle with semi-major axis A between Chern-Simons gravity and general relativity. And this is the ratio of Chern-Simons gravity to general relativity. And you see here, we have the Chern-Simons mass that contains the time derivative of the scalar field that might be related to quintessence. Now, Smith, Erichek, Caldwell, Kamionkowski said that this theory, published that this theory is equivalent to a type of string theory, and they have been able to place limits on the Chern-Simons mass based on our previous measurements of frame dragging. And this is their picture. They have been able, based on a paper we published in 2004, of a 10% measurement of frame dragging, they have been able to place limits on the Chern-Simons mass that must be larger than 2 times 10 to the minus 2 GeV. Now, if now we reach the last year and this year we reach almost a 1% verification of the length steering drag, so this limit will be now Chern-Simons mass larger than 4 times 10 to the minus 23 GeV. Now, this is a brief history of the tests of frame dragging. Gravity Probe B proposed in 1960. Lajos is a satellite that was launched in 1976 by NASA for space geodesy measurements. Then Lajos 3, we propose a new satellite, laser ranged, called Lajos 3, identical to Lajos, but unfortunately it was never funded. Then Lajos 2 was launched by ASI, Italian Space Agency, and NASA for space geodesy measurements, and we had been able to publish some observations based on the study of the orbit of Lajos and Lajos 2 in 1997 and 98, very rough observations of frame dragging. But the breakthrough now came with a launch of GRACE that was accurately launched to measure the Earth gravitational field. On the basis of GRACE, using Lajos and Lajos 2, between 2004-2010, we published results for the frame dragging test at the level of about 10%. Then we had the gravity probe B results in 2011, between 2011 and 2015. And then there were LARES first results in 2016, LARES results, almost final results based on 7 years of data analysis published in European Physics Journal C in 2019 by a 10%, with a 10% test of frame dragging, independently confirmed last year by an independent group. And now we are publishing a recent measurement of frame dragging based on 9 years of data analysis with an error between 2 and 1%. Now, GRACE follow-on was launched in May 22nd, 2018, and LARES 2 will be launched in March 2022 to reach 2 × 10⁻³ accuracy. This is the well-known gravity probe B experiment. We use a different technique. We use pellet laser ranging. We send laser pulses to satellites such as Lajos, Lajos 2, and LARES. And we can detect, we can measure very precisely the position of the satellites with an error that will be less than 1 millimeter, especially for the LARES 2 satellite. With the other satellite, we have an error of about 1 centimeter. I will show you about LARES 2 in a moment. And this now is the main source of bias in our experiment. These are the event-zonal harmonics. These event-zonal harmonics are the harmonics that are axially symmetric with respect to the Earth axis and are also symmetric with respect to the Earth equatorial plane. Of course, the Earth is not a perfect sphere, so we have these event-zonal harmonics that are the large source of bias. Indeed, the classical precession of the node of a satellite is due to the event-zonal harmonics. You see here J2 and J4, the next event-zonal harmonic, and they produce a large classical precession. However, the frame dragging effect doesn't depend on the inclination of the satellite. Dragging doesn't depend on the inclination. And this is the idea we proposed back in 1984, between 1984 and 1989, to place 2 satellites with supplementary orbits in such a way that the classical effect will be completely canceled out and we will measure only frame dragging. Unfortunately, this Lajos 3 satellite was never funded. There were many papers starting from 1984, 1986, and so forth, describing this experiment. But since we didn't have the Lajos 3 satellite, we also proposed back in 1989 to use a number of satellites to get rid of the uncertainty in the event-zonal harmonics, and 1 satellite to measure the lens steering effect. So we can get rid of n-1 errors due to the n-1 largest event-zonal harmonics. And unfortunately, we described the use of the node of Lajos and Lajos 2 to measure the lens steering effect in this paper, but unfortunately, in 1996, the 2 nodes were not enough to measure the lens steering effect. Just there were some rough observations. But fortunately, now in 2002, we had the GRACE space mission that was launched by NASA and DLR. And the use of GRACE to test the lens steering effect at a few percent level was predicted by John Rees and Enrico Sparlis. And this is a picture of the gravity field anomalies derived by GRACE. This is one of the first gravity models of GRACE in 2004, Eigengrace S. These are the gravity field anomalies. That means the deviations of the gravity field of Earth from the field of a perfect geoid of a perfect ellipsoid. And this is another picture of the gravity field anomalies derived by Grace. And you can see the correlation with the mass distributions. For example, here we have the Andes, okay? And now this is an artistic view of our experiment, first experiment, Lagos 1 satellite, Lagos 2, the Grace space mission, and an artistic view of the space deformation due to frame dragging, and the picture of the gravity field anomalies of the Earth derived by Grace. So using these two satellites, we were able to eliminate the uncertainty due to the quadruple moment of the Earth. And there were a number of measurements published between 2004 2010 using a number of different using different orbital estimators. For example, here you can see the triangles are the results of CSR University of Texas at Austin using the orbital estimator Utopia. They obtained this measurement. Then the squares are the results obtained by the Germans of GFZ Helmholtz Institute with the orbital estimator EPOSOC. And the circles are our results, University of Salento, University of Rome, Maryland, NASA Goddard, with the orbital estimator Jodine. And our results were published in Nature. They dedicated us the cover in 2007. And these are our results in 2004. This is our result for the lens steering effect. We fit the linear trend, and we found a 99% of general relativistic prediction. Here below is the general relativistic prediction. And this was taken from a paper in 2004. Then in 2010, we published very detailed papers on Lagos results and LARES, and on the forthcoming LARES experiment launched 2 years later. And it was these papers were published in this book dedicated to John Archibald Wheeler. Now, let's go to the LARES satellite. The LARES satellite was successfully launched, then very accurately injected in the nominal orbit on the 13th of February 2012 with a Vega launching vehicle, as I told you. And this is an artistic view of our experiment. The Grace satellites, the LARES satellite, the two Lagos satellites, and this is a gravity field model based on Grace observations. And what is this? This is the J4 even zonal harmonic, greatly exaggerated, of course. And the J4 harmonic is the source of the error after the largest source of error after J2 in the measurement of lens steering drag. However, in a scale, here in red is the lens steering drag, and this is the size of the largest error source due to J4. Now, with 3 satellites, we have 3 observables. Therefore, we can eliminate the 2 uncertainties due to J2 and J4, and then measure frame dragging. So we have 3 quantities to measure, let's say, and 3 observables. So these are the even zonal harmonics that we were able to eliminate, J2 and J4, and we obtained the results between 1 and 3%, depending on the estimate of the systematic errors. And using LARES and Lagos, Lagos 2, we were also able to get a test of the equivalent principle at the level of 10 to the minus 9 accuracy. This is a gravity field model, GGM05S, based on Grace. And before showing you the results of the LARES experiment, we made a large number of Monte Carlo simulations with a large number of runs. And these are the source of main bias in the measurement of the lens steering effect, the GM of Earth, the mass of Earth, and then these are the even zonal harmonics. These are the normalized even zonal harmonics, J2, J4, J6, J8, J10, and the rate of change of J2, the rate of change of J4. And then these are the CR of Lagos 1, Lagos 2, and Lares. They depend on the reflectivity of the satellites and the geometry of the satellites, and they measure the push of the satellite by the radiation pressure. So we have these parameters. These are the nominal values, and we have the 1 sigma associated with each one of these parameters. We randomly generated a number of values with mean value equal to these nominal values, and sigma given by this right hand column. So this is the result of our measurements, of our simulations. Sorry, these are just simulations. So in green, we have the simulated frame dragging effect. That was 100.25% of his theoretical general relativity value. But what is important, that in red, we have the general relativity prediction. The standard deviation is at the level of 1.5%. And this is due to all the error sources I showed you before, GM, even zonal harmonic, etc. This was published in 2000. The results, the real results of that analysis were published in 2019 in APJC, and this is our result, experimental result. We obtained 99.1% of general relativity theoretical prediction of frame dragging. This is the black line, and the red points are the residuals, cumulative residuals. You see there is a fantastic fit, experimental fit, and the error due to the error source I showed you before is estimated between 1 and 3%. APJC dedicated the cover to our tests. And finally, about Lares, I want to tell you that we obtained the test of the weak equivalent principle using Lagos 2, and Lares. And we obtained a test with new materials and at previously untested ranges. The range was between 8,000 kilometers and 12,000 kilometers. Material aluminum and brass for Lagos 2 versus tungsten for Lares, and the accuracy was at the level of 1 part in a billion. Okay, now let's go to the new mission, Lares 2. Lares 2 is basically the previous experiment Lagos 3, but is a new satellite with a new structure. And with this new satellite that will be launched next year, we can measure, hopefully, we test frame dragging at the level of accuracy of about 2 times 10 to the minus 3, plus other tests of general relativity and fundamental physics, and also useful for measurements in space geodesy and geodynamics. These are the main papers we published based on earlier proposal in physical review letters, etc. So we have papers that goes from theoretical physics to space geodesy, orbital analysis, material study of the materials, etc., etc. This is a picture of the Lares 2 satellite on the separation mechanism. And this is again the picture I showed you before for Lares 3, but now we have Lares 2 instead of Lagos 3, coupled with the Lagos satellites, supplementary inclinations. This is basically the same orbit, we proposed back in 1984-86. And this is an old picture taken almost over 35 years ago in the office of this physicist, great physicist, John Archibald Wheeler, with a picture of the experiment with the supplementary orbits. supplementary inclinations orbits. LARES-2, what is new with respect to LAGEOS 3? Allora, the Earth gravity field knowledge and the event-zone harmonics determination are today extremely improved with respect to 1984. Thanks to these missions I showed you before, GRACE and GRACE follow on. Thanks to these missions, the Earth quadrupole moment is improved by a factor more than 100 with respect to the Earth gravity field determination in 1984. So this is a very important point. The knowledge of other orbital perturbations, such as the Earth tides, is also greatly improved with respect to 1984. Then the satellite structure is quite improved with respect to all the other laser-ranged satellites. Indeed, we are using now the new 1-inch retroreflectors, and we can today reach less than 1 millimeter precision in ranging. Finally, the satellite LARES-2 can be ejected with a new launching vehicle Vega-C into the special orbit supplementary to LAGEOS with better accuracy than in 1984. This is a beautiful GRACE follow-on mission launched in 2018 for the study of the gravitational field of Earth, for the determination of the gravitational field of the Earth. And here are the retroreflectors of LAGEOS, LAGEOS-2, and LARES on the left, and the 1-inch retroreflector on LARES-2. Thanks to these new retroreflectors, we can improve the accuracy in ranging, and we can reach a precision of less than 1 millimeter. Here again, I showed you LARES, the LARES satellite already orbiting the Earth, and the LARES-2 satellite on the separation mechanism. This is another picture of the LARES-2 satellite on the separation mechanism, ready for launch.
2022. Okay.
Yes, and just error budget. Give me another couple of minutes. Okay, this is the error budget. The error budget, okay, there is no time to enter in details. Is at the level of 2 × 10⁻³ of frame dragging. We have done also Monte Carlo simulations, a large number of Monte Carlo runs. Again, with the same technique I showed you before, with the main parameters, mass of Earth, even zonal harmonics, rate of change of the even zonal harmonics, odd zonal harmonics, reflectivity properties of the LAGEOS satellite, of the LAGEOS and LARES satellites. And this is our result. If you use only one satellite, you have a large spread, a large error. And you cannot measure frame dragging if you use only LAGEOS or only LARES too. But when you combine the two orbits, you see the spread. I don't know if you can notice here, there is a small spread, and the size of the lens steering effect is about 200 milliarc seconds over these 3 years of data analysis. So we have a very, very small spread. I'm finished. We got an error of 1.5 times 10⁻³ with these Monte Carlo simulations. And then similarly, we performed covariance analysis and we got an error of 1.9% of the lens steering effect. Conclusions, so we measured the frame dragging at the level of 1 or 2% using 7-9 years of LARES data observations. LARES-2 should bring us to 2 × 10⁻³ test of frame dragging, and then we could also test the equivalence principle with LAGEOS, LARES, and LARES-2. Thank you to organizers for inviting me, and thanks again.
Most welcome. And in view of the, you can see on the chat if there are any questions, and Ignazio, and if not, we are very much over time. I would like to thank all the speakers of this very, very long session, which started at 6:30 Italian time and ends now, and especially to thank TFA, Yuan, and Wang Yu.
Thank you.
In China, who have been chairing the session beautifully. And thank you again. And at 4:30, we will go on the parallel session.
Thank you.
Bye.
Bye-bye.
Bye.
Bye, Gerard.